which is what we are in here. And the first talk is by Professor Dhruv Batra, and he's going to talk about emergence of maps in memories of blind navigation agents. So let me quickly, this is the quick introduction to Professor Batra. I think he needs no introduction. He is quite well known in the community, and he is a research director at FAIR Labs as well, in addition to holding the academic position at Georgia Tech. He graduated from CMU with some links to Cornell, I guess, but otherwise you can see all his stellar credentials. I think instead of me reading it, I would rather hear from you his talk, because this we will make available these charts as well online so that you can see. So we are very, very privileged to have him this morning. And without further ado, let me welcome Professor Dhruv Batra.
Small crowd, please you can take us at our own pace. If you have any questions, I think it relates to what this talk is really about is this organization that built what are known as collective. We all do it. The species do it as well. And there is a organisms, brains of organisms build internal spatial representation. So this morning, when you came to you have a sense for what this building is laid out. Please sketch out a map of your path, but maybe it will be different. Maybe some we would probably point to where the exits are, which may
You try again. Can the online attendees hear me now? I can hear the echo.
Yes, much better.
Yeah.
Much better.
Here to me. Are they able to hear? Because
But I think I heard it. Yeah.
Yes, we can hear. We can hear you through.
I can hear. Okay, that is the cognitive map hypothesis. The idea that brains of organisms build some sort of internal spatial representation through which you can answer queries like, which way is the exit, which way is water around us, how do I get out of this building? And this goes back to work in 1948 by Edward Tolman, and he did this experiment on mice. He had this apparatus where he would release mice at point A. There was food placed at point G. It was a fairly simple apparatus. You can in today's term, you can think of it as learning in the modern machine learning, reinforcement learning sense of things. But this is where reinforcement learning comes from, because if you happen to reach the food, there is positive reward waiting for you. After some amount of time spent in this apparatus, the rats get better. They basically figure out when they're released in this environment, how to get very quickly to point G. Then what Tolman did is he made modifications to the environment where the path that they're used to taking, the one dead straight ahead of this opening, is now blocked. And instead, there are just multiple paths that are presented as options that the rats can take. Now, if you've memorized a path or a sequence of actions to take, then you are stuck. You do not know what to do, and you have to regress back to exploration. However, if you've built a mental map of where G is with respect to this point, you know that 6 roughly points in that direction, always 6 points in that direction. And this is a histogram in that paper where he's showing that, more often than not, rats end up taking pathway 6 on their first attempt. They just go there. And this was, in Tolman's mind, evidence that rats are building a spatial understanding of where they are. They're not just memorizing their paths. This was 1948. And since then, this is there's an industry of this. There is, we know ants build cognitive maps, bats build it, blind mole rats build cognitive maps. So they're effectively blind. They have no sight, but they do. Chimpanzees build cognitive maps. The chimpanzee experiment is particularly interesting, which we'll come back to. I promise we'll come back to this in a machine learning context. A human carries a chimpanzee, walks along the path shown with arrows. So this is the start position. All the numbers are where food is located, and the human walks along this path shown along the arrows. Then the chimpanzee is released in this environment and handed over control, if you will. The chimpanzee does not retrace the steps. Or maybe I'm getting my thing other way around, that maybe the arrows are what the chimpanzees does and the numbering is what the human followed. The point being that those are different. The numbering is different than the route shown through the arrows, which is again evidence that you are not retracing steps. You are you have built a spatial representation of your environment, and the chimpanzee is exhibiting control and taking through shortest paths, if you will. This line of work led to a Nobel Prize in 2014 for the discovery of what are known as grid cells and place cells in the hippocampus, which effectively are giving brains a GPS or a positioning system. So we know brains build spatial representations or maps. Machines, now we're getting into computer vision and machine learning. Machines use maps all the way from the history of some of the earliest robots that were built to modern autonomous driving cars, and even more recent sort of indoor navigation systems in simulation. And so now finally we get to the work that we talked about at ICLR this year. We studied this question of emergence of maps. We were also fortunate enough that this was recognized as an outstanding paper award at ICLR. We asked the question, do AI agents learn to build mental maps or implicit spatial representations in the course of learning to navigate? And the question, of course, you should ask is, why should we care? Do you know of a roboticist who does not already use maps? And no, that is not why you should care. You should care because it would explain a curious phenomena in modern machine learning. If you haven't been working in navigation in modern machine learning context, there are these models appearing that look essentially like video captioning models. They do navigation without ever building a map. These models are called pixels to actions models. You take in RGB or some sort of localization sensor in, and you output an action, and they're trained end to end, and they have no concept of a mapper or a planner. And so it would explain what's happening in these models. And frankly, for me, what I find particularly interesting here is this notion of convergent evolution. So in biological systems, convergent evolution is the idea that unrelated organisms evolve structures that have the same function. So there are 3 completely different families of organisms that fly. Birds fly. There was a dinosaur, pterodactyls, that flew, and bats and flying foxes fly. The common ancestor of those does not fly or did not fly. Bats are mammals. That's a dinosaur, that's a bird. Their common ancestor did not fly, which means flight and wings evolved 3 completely independent times. And when that happens, what you are getting a glimpse into is an underlying physical pressure of the ecology that the organism is responding to. And this happens all the time. Wings are an example, poison is another example, echolocation is another example, antennas, streamlined shapes, photosynthesis has evolved multiple times. And that's telling you something about the underlying laws of physics and the environment that you're dealing with. And so if maps emerge in artificial systems, just like they do in biological systems, then what you are getting a hint at is maps are a natural solution to navigation, which is not what you can make a claim by just creating a mapping system. Okay, so with that, let's get a bit more details, lots of high-level stuff. The task we're going to study is called point goal navigation. So there is an agent. This is both in virtual and real settings, but all our experiments are going to be in simulation. There is an agent that is initialized in a 3D environment. This is a house whose top-down view we are seeing. The agent does not get the map. The blue position is where it's initialized. It is told that it needs to navigate to this red position. It is told through relative coordinates, 10 meters north, 15 meters west, relative coordinates relative to the start location. It is equipped with a egocentric depth camera, Intel RealSense, whatever, egocentric RGB camera, and a localization sensor. So it knows how to do ego motion relative to, as it's taking a step, it knows how far it's moving. Not in absolute coordinates and relative to where it started from. Now, if I gave you the map on the right, actually, let me go back. If I gave you that map on the right, this is a intro to computer science, intro to AI homework 1 problem. This is a path planning problem. This well understood, solved. We don't need to spend time on it. But if you don't have the map and you have to operate in a new environment from first person egocentric perception, then this is an open research question. This is what an episode of this task looks like. The agent is outputting actions like turn left 10 degrees, turn right 10 degrees, move forward, and it's receiving percepts and so on. The goal specification of r comma theta, by the way, is biologically plausible. Turns out when bees discover honey in flowers, they will go back to their hive and do a little bit of a waggle dance where the direction they're pointing to indicates which way the flower is, and how fast they are dancing tells you r. So they're conveying r comma theta. So there's some biological plausibility here. In natural organisms, though, there are plenty of mechanisms to explain navigation, right? You can navigate because you recognize landmarks. You can navigate because there are magnetic fields in the environment. You can navigate solar and chemical navigation as well. What we are interested in is, are these intelligent agents building maps? So what we're going to do is a fairly extreme setting. This is going to be a blind agent. There's no depth, no RGB. The only sensing this agent has is ego motion. As it's moving forward, it knows how far it has moved forward or how far it is turning, and where the goal is therefore relative to itself, because the goal was provided initially. And so you can just do basic linear algebra and integrate and know where the goal is. So this is what an episode in the life of this agent looks like. I want you to see this again where, let's see, does this video play? Yes, this is what that episode looks like. That's all you see. There's r comma theta, a sequence that is the input to this organism. And what we're going to do is we're going to construct an architecture which is just task agnostic. I'm going to, if I have sight, I'm going to take this RGB image, process it through a CNN. This work was done a few years ago. If I was doing it today, would use VITs. Sure, that's not the important bit. We embed the r comma theta of the goal into a recurrent policy. This is a GRU. Again, if we were doing this today, we would probably use a transformer, not the important bit. The important bit is that this is task agnostic. There's no mapping here. There's no planning here. There is just a generic, this could be a video captioning model that outputs a action like turn left 10 degrees, turn right 10 degrees, move forward 0.2 meters. And we just, for a blind agent, don't give it sight. It just operates on a sequence of r comma thetas. And what I want you to notice is there are no other mechanisms possible to explain navigation. There's no inductive bias towards mapping. And there's no spatial supervision, no spatial memory, no auxiliary tasks. The only thing we're going to do is on policy reinforcement learning. You take a sequence of actions, we will tell you whether you're getting closer or farther from the goal with rewards. The rewards look essentially like this. If the goal is reached, you get some positive reward. At every step of time, we'll tell you hot or cold. Is the distance to the goal going up or down? And just a penalty for existing, because we want you to be efficient. That's it. This is the only reward. This is about as simple as it gets. And so the first question you have to is, can blind agents navigate? And the answer is yes, they can navigate quite well. On the x-axis is steps of training. You can ignore the units if you want to. It's basically how long are these agents trained. On the y-axis is performance. The solid lines are success. This green dashed line is a sighted agent, and the green solid line is a blind agent. And what you see is that the success rates are very similar. The black lines are path efficiencies. So blind agents are almost as successful as sighted agents. They're just very inefficient. This is an inefficient path, and I'll show you visually what that means. This is a sighted agent. It goes from blue to red in a path that looks essentially like the shortest path. It's a new environment. It's never seen this environment, but it traverses essentially the shortest path. This is what a blind agent does. It goes and smacks its face into a wall, and then basically follows that wall along. Because all of this is just for visualization. It has only access to r, thetas. And so it's backtracking, following the wall along. It'll not forget that it had traversed this part and will execute this episode, succeed, but you notice that the path is obviously not very efficient. Here's another environment where, again, this is a sighted agent. Starting here, we'll turn around, pass through door number 1, turn right on a hallway, door number 2, hallway 3, and get to the target, traversing essentially what looks like a shortest path. This is a blind agent that will, again, do wall following. And wall following is a fairly regular phenomena that emerges completely independently. It's not written there in the reward function. There's nothing in the reward that encourages wall following. It just emerges because that's the strategy you have to do, because you have to succeed on new environments. Okay, so finding number 1 is blind agents can navigate. And in fact, what we find is the emergence of what are known as bug algorithms. So bug algorithms are these algorithms that are famous from path planning literature in the 1970s, where a bunch of mathematicians sat down and proved that if you have any 2D surface with piecewise convex obstacles with a agent which is a point mass that can only sense contact, you basically can prove that you will always reach the goal. It's just a question of how efficient, and you can prove bounds on how efficient and inefficient your path is going to be. We are essentially finding the emergence of algorithms like that start moving towards the goal. When you reach a target, you basically have to decide, do you go right or left? And then basically you have to decide when to leave that wall that you're following. We actually implemented a optimal version of a bug algorithm that's going to try to do that. So from start to goal, it's going to try to move in that straight line. When it hits an obstacle, we will tell it what is the optimal direction to turn into, right or left. And even with that optimal or oracle bug algorithm, you only get what is known as 46% SPL. SPL is a measure of path efficiency. The agents that we're training, our blind agents, are 63% SPL. So they're more efficient than an oracle bug algorithm, if you will. Okay, so blind agents can navigate. Now you got to explain why, like what is the mechanism that explains it? And the mechanism that explains it is memory. They're blind. The only thing they have is r, theta coming in over a sequence. This is where the power is coming from. And so one question you can ask is, how much memory are they using? How much do they remember? We saw an episode where they follow all along one direction, backtrack. And so you've got to remember not to thrash, not to go right, left, over and over again. You've got to remember you've explored a path. And so one way of sort of showing that is that you take the sequence of r, thetas and you chop it at some point in the past. And you basically train bounded memory methods. And this is what the memory length is showing. Memory length of 1, 10, 100, 1000. And on the y-axis is performance, success rate at this task. I believe this is SPL, not success rate. And what we're showing is essentially that performance does not saturate till you have reached effectively 1,000 steps in the past. You have to remember the past 1,000 steps, and you have to actually have access to them. Because if you chop the memory, even at the 100 steps, you see a sharp drop in performance. And so these agents are remembering fairly long sequences, which is really promising, which is beginning to explain what's happening here. And turns out the memory is used to detect collisions. So what you can do is you can take the LSTM cell state or the GRU cell state, and you can try to predict at time that just happened in at the previous time, did the agent collide or not? Collision is when the agent tries to move forward and it is unable to accomplish the full distance of its action because there was something in the environment that prevented it. And so you predict from this HT whether AT minus 1 was a collision or not. And turns out you can do it at like 98% accuracy in a 2-class balanced problem. So it is essentially there with a linear classifier, with a frozen classifier, with a frozen hidden cell state. More importantly, you can do a fairly easy projection to a 2-dimensional visualization space. So this is a 2-dimensional space of that of the LSTM cell state, where we're showing that the emergence of roughly 4 clusters, one that corresponds to moving forward and not colliding, one that corresponds to moving forward and colliding, and 2 that correspond to turning right or left where you cannot collide. And so what you see here is an episode of the environment on the left, and the black dot is showing exactly what neurons are firing. And so the agent is keeping track of when it's moving straight, when it has collided, when it's moving left or right, when it cannot collide. And so this is, again, completely emergent. There's nothing in the reward function that encourages the detection of collisions. Okay, what else what other information does the memory encode? We're going to go back and run an AI version of this chimpanzee experiment. What we're going to do is we're going to take this agent, initialize it at start, ask it to go to this goal location T. It will traverse a path where it will do some exploration in this room, come back out, follow this wall. It'll be inefficient, as I'm showing. Then what I'm going to do is I'm going to take the hidden cell state of this LSTM at the end of this episode. I'm going to use that as the initial memory of a new agent. I'm going to call this a probe agent. So I'm going to initialize a new agent in this environment with the memory of the memory created from this episode by the previous agent. Right, so H0 is going to be HT, but there's going to be a stop gradient here. This agent is not learning to help this agent succeed. It just does what it does, and then I'm going to pass its memory forward. And when you do that, this is what happens. The blue line is the first agent, and the purple line is the second agent that's starting with the memory of the first one. It is going to take shortcuts. It cuts out excursions. It does not do as much wall following as the first one does. It did not go into this room. It is almost as if it knows what this environment is like. It is going to move through free space, even though it is also blind. And this is also a new environment as far as it is concerned, except the memory of the previous agent. So this is what that looks like. This is the first agent in blind, zero clean initialization of memory, wall following, doing explorations, excursions, turning back, coming out of rooms. It is being asked to go somewhere here. The red dot is hidden with the zoom controllers. And you'll see it's a long episode. It's struggling. It's following walls. It will eventually succeed. And then I'll ask it to go back to the starting location. And you'll notice that it is far more efficient in going back. It cuts out excursions. We've done it both ways, S to T, T to S. There's essentially no difference. And so here is a quantitative comparison of these things. Here we're measuring path efficiency. And so this is how difficult the episodes are in general. This is how this probe agent performs when it's augmented with the memory of the first one. You see a jump from 72 to 85. This is effectively the same degree of jump as if you had given it sight. So when you train RGB agents, this is where the path efficiency peaks out. And so effectively the memories of blind navigation agents are equivalent to having vision in the environment. They're telling you exactly what to do in the environment, going S to T or T to S. Okay, so this is already telling us that agents are building implicit spatial representations? What about explicit ones? Can we just predict a map of what happened in the environment? And so that's what we did. So have an agent operate in a new environment, take the memory from the episode, decode a map. So this is what that looks like. You have a bunch of r, thetas coming in into an LSTM. You're going to take the last hidden state HT. We are going to crop a region, a 2 meter by 2 meter, a region around the path traversed by this agent, which is within 2 meters of wherever they happen to go in the environment, because far away from where they went, they have no basis of knowing. It's just impossible for them to know what happened. This is the ground truth, and this is the prediction. There are two classes that they're predicting at every cell. Is this occupied or is this free space? And again, the agents are not learning to create maps. There's a gradient stop here. So this is just with the representations that are built to succeed at navigation. We're going to predict explicit maps. And we find evidence of that as well. This is an entire histogram of intersection over union. So that's the map prediction accuracy. And this is a histogram of the difference between two agents. One is a trained agent, which succeeds at navigation, and one is an untrained agent. So, and just a LSTM with random parameter initializations to function as a control, like what is the baseline here. And what you see is that the entire histogram shifts forward. The means shift from 12.5 to 32.4 accuracy at predicting the maps. Qualitatively, I want you to notice that sometimes it makes mistakes. It predicts that the agent is passing through occupied space. But what it gets right is it passed through hugging one wall. It predicts that there is another wall somewhere farther from where it was, but it is there because it has figured out that there is a natural structure in these houses of corridors. And the existence of corridors suggests that there must be another wall, even though the agent did not traverse close to that wall. And that's cool. Okay, so what have we learned about blind navigation agents? We've learned that first, that they can navigate. They're not very efficient, but they're effective. How? Well, they remember the past 1,000 steps, and that is enough information to not thrash. That is enough information to do backtracking and so on. Why? Because they're building map-like representations that enable shortcuts. The memory contains metric maps. It contains neurons that are effectively predicting whether they've collided or not. And even though I didn't tell you this one last experiment, there's sort of a few other experiments in the paper that the memory is task specific. The agent effectively is forgetting excursions. When it goes into a room, comes back out of the room because there's nothing out there that leads to the goal, the memory just erases its existence. It is unable to predict that it ever went there. Its map prediction accuracy is lower there. And that is kind of why when you transplant this memory, the second agent doesn't go into that room, because there's just no memory of having gone there in the first place. And there's a memory of the path that emerged. Okay, so that was this body of work on the emergence of maps. This was work done entirely in simulation, and this was effectively just what happens when we train blind agents. We will not be deploying blind robots. That's not going to happen. But this is not just a simulation work. This is not just about blind agents. At CVPR this year, we have trained these agents with sight, with proprioception, not just for navigation, but also for mobile manipulation, not just with geometric coordinates, but also with language input. We have Spot here. We're going to give a live demo of neural networks, pixels to actions, no mapping, no planning, running on the robot, doing things like this, which is bring me the chocolate box, cereal box, pill box, put them on the bedroom table. And so this is a new environment. The agent's never seen this environment. It is operating from a depth camera on its face, if you will, and a RGB camera on its arm that's doing object detection. It's going to navigate, pick up an object, navigate, place the object at the target receptacle, and repeat. And this is very similar underlying neural network structures, pixels to actions. There's no planners in here. There's no mappers in here. Just raw sensory data to actions, trained entirely in simulation, deployed effectively zero shot, sim to real. And you can come see this at both at the Meta booth and at the CVPR demo track on Thursday. And with that, I can stop. Thank you.
your questions, please ask now, and please, if you could come up to the microphone, it would be great for this one.
For the Zoom folks, I can hear you.
Hi, thank you for a great talk. So I wanted to ask a question. So regarding reconstructing the map, so from the gradient, I was trying to ask analogy problem where in image classification, you could reconstruct a test image or current training image from its gradient. So it's often used in privacy preserving image classification where you are trying to reconstruct the current image. So, and the evaluation is sort of related where you are comparing the reconstructed image with the original image. So do you have any comment on this kind of things? So yeah, just my comment.
And the question specifically is, are the techniques similar or?
It's not the question, it's
I
just
see.
the comment.
Yeah. To be honest, I haven't done a lot of work in privacy preserving methods. I did some work in explainable AI and saliency methods for detecting where neural networks are looking, but that was like 5 years ago at this point. So I don't know what the most recent techniques are. This is a purely supervised learning approach, though, where you take a hidden representation here, and you're training. You have ground truth because it's in simulation, so you know what the true map is, and you can predict a map through a decoder network, and you can supervise at each pixel location what the right answer should be. And then what you're measuring is not really the quality of map prediction for its own sake, but what you're trying to see is that if good maps can be predicted, that tell us that the input representation contains this information. But had we not been able to predict maps, that negative experiment does not tell us anything about the representation, because maybe our decoder networks are bad. That's sort of the subtle difference there in the goals. But yeah. So there are implications on privacy, of course. You deploy these agents, even though they're blind, they're building maps of the environment.
Yeah, absolutely. Thank you.
Any other question? Anything online? No. Yeah, so I maybe had a general comment and question, maybe others similar, maybe thinking about having not coming from this kind of area. When you say blind, it has vision.
No, it has
no camera input.
No camera input. R, theta. That's the only input. The only input to this LSTM is R, theta at each time step of where the goal is.
How does it see what is in front of it, and does not see?
It does not see what's in front of it. It just tries to move, and based on how that R, theta is changing. So, it's trying to go at this R, theta location. It outputs an action left. It's going to turn left in place. That's fine. At some point, it's going to say forward. Forward implies forward 0.2 meters or so. It's going to try to go 0.2 meters and not actually traverse 0.2 meters. And that will be reflected in the R, theta. But it's not told that you collided or this is how far you travel. It's just you have to infer based on R, theta. The pixels are just for display. The pixels are not being input to the agent. It's truly blind. The demo that we're giving at CVPR is not blind. It is operating with sight. It's an architecture that looks effectively like this. I did have an architecture where I was providing in visual input. I just turned the visual input off.
So could you talk a little bit about your simulated data?
Yeah, sorry, I didn't go into a lot of details. So these are simulated, these are scans of 3D environments. We've done this work over many years. There are standard data sets in the community. There are some that are known as MP3D or Matterport data sets. So these come typically from real estate agents going into houses that they want to sell. There's this little 3D camera device that they place at various locations. Matterport, the company, does 3D reconstructions of these. And so what you're seeing are textured meshes of real 3D environments that this agent is being trained in. The simulator is called Habitat. That's a project that we've been working on for 5 years at this point. It is a fast renderer combined with a rigid body physics engine that we didn't write. We basically used Bullet. The physics in itself is not the hard part here. Rendering is also in some sense not the hard part because these are textured meshes. You're basically rendering whatever was captured from the 3D reconstruction camera. The interesting bits here is how do you make this simulation fast? Because some of the things that I didn't go into is if you look at the very first result that I showed was actually this plot where I said, don't worry about what's on the x-axis. What's on the x-axis is steps of experience. What is an experience? You say forward or you say turn left or turn right. That's a step that the agent takes in simulation. These are measured in hundreds of millions, getting to billions of steps of experience in simulation. The only reason why this works is because simulation is orders of magnitude faster than trying to run these experiments in reality. We are at this point, we can effectively run our simulators on the order of 25,000 steps of experience per second of real time. Because you have to get to 10 to the 9 steps of experience for training. You cannot get to 10 to the 9 steps of experience with a simulator which is based on a game engine that runs at 60 steps per second. That 10 to the 9 gap is not going to happen. So you have to get to like 10 to the 6 in terms of the frame rate of your simulator, and the rest you fill with GPUs and wall clock time. And this is massive amounts of pre-training and simulation. This is the work that we've been doing in building that simulator, and then we deploy these things sim to real. Some of them are annotated with 3D bounding boxes and semantic segmentations of objects in the world. But for this particular task that we're doing, which is point nav, where the task is, you just have to go. So this task of point nav, you start at a random point and you have to go to r, theta. You don't actually need any human annotations. You can programmatically generate episodes because you just randomly initialize an agent somewhere, pick another random point in the environment, ask the agent to go there, and you know whether it reached there because r, theta, and where the agent is in simulation, you can always figure out programmatically.
That assumes the map is available during the simulation,
which you always have access to in simulation. The map is only telling you free space versus not. If you needed to know where a chair is or where a table is, then you need to have semantic annotations of objects, but this is not navigating to an object, this is just navigating to a location, and you always know where locations are in simulation.
Thank you for all the clarifications for me.
Next, so the next on schedule, are presenting learning on bias. Okay. Which one is in there?
Yes.
Have you shared on Zoom?
No, yeah, right.
Yes.
Okay, good morning, and thanks for the opportunity. My name is Pietro Morerio, Italian Institute of Technology, and I'm presenting today the paper, Learning Unbiased Classifiers from Biased Data with Meta-Learning. So let us first frame the problem. So we all know that any data set has intrinsic biases, and this has been studied in many works, and many biases can affect the data set. You have a small example on the right-hand side. So for instance, you have this action recognition data set, and you have the climbing class, and most of the pictures of climbing people have a rocky background, but sometimes you have like climbing on snow, and this underrepresented like portion of the class is since it's underrepresented can represent the problem. Actually, the problem is not the underrepresented, but the overrepresented part of the class. And same holds for diving. So most of the pictures for this diving class are underwater diving, but you happen to have some other cases. Problem is models learn very well the bias. So if you want to train a classifier for action recognition, the model will likely learn that rocky backgrounds are always related to climbing, and when it comes a white background, it will misclassify the example. Another big problem is that the bias is always or often unknown in your data. I mean, some data sets are annotated with extra notation, telling you there are like domains in the data or extra characteristics of your data, but often the data, the bias is unknown. So in this work, we basically try to set is a framework to classify bias data. And what we figure out is that class labels may be affected by what we call spurious correlations with other properties, which we call domains. So if you see the example on the right, you have the triangle class. Most of the data belongs to some domain, like domain 0. But you have a few data points which are green triangles, and same holds for the circle class in the opposite way. So these correlations can often result in shortcuts that a neural network learns, which is a good shortcut to minimize the error of the neural network, the empirical risk. And in this case, a model may learn the color instead of the shape, or may learn that a combination of color and shape is what is best for classifying the data rather than simply classifying the shape. This is important to point out. This happens when most of the data belongs to what we call the domain. I mean, if the data was balanced between blue and green, that probably wouldn't happen, because on average, the network would not rely on color to classify the data. But when there is a significant portion of the data with some like spurious characteristics, it may be the case that the network actually learns shortcuts, and you have a poor generalization to, let's say, new triangles of new colors, or even only green triangles. As I was saying, the bias is often unknown, which means you don't have information about domain 1 and 0 in practice. Okay, if you have, you can use it as extra information to train your classifier, but in principle you don't have. So you don't have because it's not practical to, of course, to label data sets with extra labels. And also it could be the case that the bias itself is difficult to identify. So it could be a kind of bias which does not make any sense to us. So in this case, it does make sense, it's color, but there could be a bias related to some like hidden characteristics we don't even know, we cannot like describe in words, or as a human we cannot tell. In this work, we propose a two-stage pipeline. So the first step is to identify the bias, which means try to like assign a label of bias, unbiased to each sample. This is to, let's say, in case you have a ground truth, of course, you can use a ground truth label for that. If you have domain 1 and 0 labels, you can do that. But the first step we would like to accomplish is that for each sample, we would like to tell, okay, this is likely to be a biased example. So belonging to a class of examples which probably generate shortcuts in the network and which one are not. And after we have this rough subdivision of the data set, we devised a bias invariant representation learning technique, which is based on meta learning. The intuition is that meta learning is suitable to learn different tasks. And in this case, the different tasks are learning from two different kind of data, biased versus unbiased. Okay, so for the bias identification, what we do is we first train a model with very standard ERM, in this case, classification loss, for example. So until you reach a target accuracy gamma. So gamma is usually reasonable accuracy, like 80, 90%. We have ablation studies on that. But the idea is that the majority of the examples are usually biased. Otherwise, the bias would not even be there. I mean, there is no problem if, as I was saying, the data is like half and half, like belonging to domain 0 or 1, which means that when we reach a target accuracy gamma of like 85% or something, you stop training. And at this point, you assign a pseudo labels. So since on the training set, you have the ground truth for the actual class label, you assign to the biased split of the data set all the examples which are correctly classified, and the rest which the model is not able to recognize correctly are assigned to the unbiased. So what is the intuition? The intuition is that the biased examples are those for which a shortcut exists and so can be easily fitted by the network. They're fitted faster usually, and like we can say overfitted. And here's a picture which maybe clarifies this fact, which is, so this is the loss, and which is of course on a training set for which we know the bias. This is done on synthetic data set, of course, but the idea is that the loss for the biased examples drops faster than the loss for the unbiased example. So if you stop the model when it reaches a target accuracy of like 85% or something, most likely the samples which are correctly classified are those which contains the shortcut, the bias. Here is the actual second stage, so the bias invariant representation learning algorithm based on meta learning. The idea is that, as I was saying before, you first identify, can you see the mouse? Yes. You first identify what is biased and what is not in stage one, and then you sample lost the mouse. You sample one example from the biased set and one from the unbiased set, and you compute a gradient update, based on equation 2. Equation 3. Equation 3 is simply a weighted empirical risk minimization. So you have a gradient update based on a loss which contains the bias and the unbiased examples. Of course, you would like to give more importance to the unbiased examples. So those examples which represent the minority of the data set and are not well represented by the data, you give it a higher weight. And so you calculate theta star. And this is the inner loop of the meta learning optimization. Again, you sample from biased and unbiased, and you construct a mixed version of the two examples. And lambda is a weighting factor, which is, as in the standard mix-up algorithm, is drawn by a gamma distribution. And you construct X mix and Y mix. So you both mix the sample and the label, as in the standard mix-up. And then the final loss is a combination of the weighted ERM loss plus this, which we call a regularizer, which is the standard classification loss, but calculated on X mix and Y mix, which are the two mixed examples. You have to note that here, actually, the neural network is evaluated in theta star and not in theta, because that accounts for the inner loop step of the meta learning optimization loop. And this mixing stage can be seen as a kind of data augmentation step where you're trying to mix bias and bias to create more like neutral data, more diverse and neutral data. And here's a visualization of this. So basically, this is a gradient update for the unbiased, for the biased, and what you want to obtain by mixing is basically have a direction which somehow averages the two. Okay, results. These are results for two synthetically biased datasets. So colored NIST is a dataset for which you have the NIST digits, and for each class you have an average color for the digits. So let's say ones are on average reddish. So you sample red and with a Gaussian distribution, and so they're more light red. And same holds for the other digits, while the test set is randomly colored. So the idea is that the network will actually, if you do nothing, the network will learn that red equals 1, and all red figures in the test sets are classified as 1. And our method is actually working pretty good. Ours with zeta equal to 0 corresponds to the absence of the regularizer. So it's just a weighted ERM. ERM performs quite poorly. Weighted ERM, which is ours with zeta equals to 0, performs pretty well, but we get a good boost in introducing our meta-learning based regularizer. And this is the accuracy on the whole test set, but what matters is actually the results on the unbiased test samples. So those test samples which do not contain the bias. And sorry, I forgot to mention the other dataset, which is CVPR 10, which is for each class you have noise corruption by a very specific kind of noise. So the idea is that the network learns the kind of noise you injected in each class. So let's say class plane has random speckle noise, and class car has salt and pepper noise and different kind of noises. These are results for two datasets, which are actually real datasets. One is constructed based on the waterbirds. It's called waterbirds and construct based on places and the CAB dataset. So you take waterbirds and birds living on Earth, on the ground, let's say, and you basically you combine them with a background, which in case of waterbirds is 95% of the time water and 5% of the time like woods or something. So the network will actually learn the background rather than the actual class. And you of course do the opposite for the other bird class. BAR is a biased action recognition, is the example I gave at the beginning of the talk, and is composed of like classes where there is an underrepresented portion of the class, like the climbing example. And here you have the results for the what is mostly important is actually the accuracy you get for the unbiased example. So the underrepresented portion of the class gets a great boost with our methods. As a reference, we have group draw, and group draw is actually a supervised debiasing method, which means they actually have the bias label. Here is an interesting ablation, and the ablation refers to the stage 1 of the pipeline, which means let's suppose we have an oracle telling us the bias, and this is the two middle columns. The F1 score for the bias identification is of course 1, because you have a perfect knowledge of what is domain 1 and domain 0 or whatever the bias is. And the test accuracy has some values. If you do a random splitting, so let's say stage 1 is random. So instead of assigning based on the accuracy criterion, you just randomly assign to biased and unbiased. You have a poor performance, 50, very poor performance compared to the oracle. What our method does is, even if we don't have a perfect F1 score, which means the stage one of the pipeline is not able to perfectly identify what is biased and what is not, you get a pretty decent test accuracy as well. Okay, so in this work, we have proposed a novel solution for the unsupervised biasing problem. And this relies on meta learning and is based on those two stages I've been talking about. So we have seen that identifying the bias as a first step is quite crucial. So if you don't know the bias, I mean, if you don't even try to identify the bias and you just random assign a bias label, this leads to poor performance. However, even you don't have a perfect knowledge of the bias, but you just have something roughly reflecting that, this is a good proxy for the let's say the classification. And what basically is the take-home message is that if you properly mix bias and unbiased examples, this provides the model with unseen data. So as a kind of a data augmentation strategy that can break those shortcuts, those spurious correlation between the data and the class labels. And yeah, that concludes the talk. And if you have questions, I'd be happy to answer.
Questions? I guess because the people on Zoom can.
Hey, great work. So one question about your tables. Do you have results on the worst case group accuracy, or is that sorry, the worst group accuracy? Is that what you mean by
the worst group
accuracy
accuracy is yeah, it's not actually the worst group accuracy. I mean, I'm not sure what you mean with the worst group accuracy. I mean, these are the results for the what we call the unbiased test samples, which is the underrepresented part of the class. So
yeah, usually you just so yeah, sometimes on waterbirds people evaluate by just finding the worst subset in the, but you could do the same split in the test.
Yeah,
right?
you can do the same. I think that is accuracy unbiased.
Accuracy and bias based.
Yeah,
okay.
because it's the under, I mean the worst is always the worst because it's the underrepresented in the training set. So the let's say the waterbirds with a wood background. That's it exactly. Okay. That is it.
So and then do you have any sense for why it seems like the regularization term matters a lot, right? That's kind of what gets you to outperform like group DRO and those other algorithms.
Yeah.
Do you have a sense for why that is?
Why?
Because the regular it is plain regularization, right? It shouldn't.
Yeah, well, it's like data-driven regularization. So I think what matters is the fact that you're providing the network with more information, let's say, and this information somehow it's like cutting these shortcuts and preventing the network to overfit on the bias, right?
All right, thank you.
Any other questions?
Just want to clarify a bit detail. So I just wanted to ask, when you are doing training and testing, you are just assuming that the label has distribution shift. The image themselves, the appearance don't have distribution shift. For example, if you are trying on CVPR 10.1, so then you are using CVPR 10.1 for training?
Yes.
Okay, so there's no shift in X, just shift in Y. You're assuming shift in Y.
No, I mean the shift is in the actual samples. So okay, so, these are like actually two splits of the CVPR. So in the training set you have well actually both in this case both the training and the test set. Well, no, actually just the training set. I think I have to check that. Is corrupted with noise. So you have very typical noise for each class. So each class is represented for the majority of the class with a very specific noise.
Right.
So the network actually, the risk is that the network learns the noise. And when it finds that kind of noise in the test set, it will classify, let's say, a car as a plane just because it has seen Gaussian noise with mean value 0 and some standard deviation you gave.
Okay, so your training set is corrupted. The test set is not.
The test set is evenly distributed, actually.
Evenly distributed. Okay.
So you apply noise, but evenly in these two let's say, artificial.
So let's say for example, for corrupted CFR 10.1. So how do you construct the meta train?
No. The training set is all of the same, the training, right? But the thing is, there is no meta train because you construct new data based on the regularizer. That's it.
Based on, okay.
So the regularizer is actually constructing new data for you because
Okay.
you're mixing the data. That's the thing.
Right. Okay. Thank you.
Are there any more questions? I had one general
Sure.
question. Have you tried it on most of the time people side face recognition with bias?
We have, yes, we have a follow-up work with which is actually a more a better version of this, where we try also on on face recognition. Yes, where you have the bias of like blonde people being mostly women and this kind of biases. Yes.
All right, there are no more questions. Let's thank the speaker again.
Thank you.
So next on the schedule, we have the paper presentation for a diverse large benchmark for measuring fairness and robustness in audio vision speech models. Have you connected to Zoom? Zoom?
No,
Yeah.
I have not connected.
Oh, okay. Could you please go to the CVPR virtual website?
Okay.
And then you go to the so that the remote and
Right. It's here, right? The internet works. I can do that. Can you show me where it is?
go to severe. Yep, here.
Yes.
Yeah. You click on the virtual side.
It's actually slow the internet. But I can do this now. I found.
You can use this.
Yeah, perfect. No shops.
Schedule. Control is trusted. Search the workshop name.
Yes, this one. Internet is very slow.
Are you using the CVPR?
I actually used it. Yes.
Okay.
Service unavailable. Can connect because I cannot find the source.
I think connected here.
It's actually not the internet. So the website is broken. Might be overloaded. I can give you the presentation if you want.
Yeah, sure.
Yeah.
Oh yeah, now I can actually connect.
Okay, great. Then click on the join Zoom. Yeah.
Perfect. Do you want screen share from the Zoom?
Yep.
Okay.
I already made you. The pictures.
Yes. Good morning, everyone. Sorry for the technical challenges. I'm Caner Hazırbaş. I work for Meta, and today I will present a new data set to measure fairness and robustness of AI models. This data set is designed with self-provided labels, and it's a consent-driven data set. The idea is that we collected data set in several countries with a through like literature review. So before I actually like introduce the data set, I would like to talk about its design, because that's where we actually spend most of the time for this data set. So for us, it was very important to understand why we need such a data set, how we can actually choose categories, how we can actually subcategorize those categories, and where we should be collecting this data set. So that's a research we have completed and published an archive paper that you can find. But after the research was done, we also like went on wild and collected this data set. So today I'm gonna like present the data set itself. It's a data set constructed with ethical considerations, and it's also a broader implementation of ethics in the construction of any AI data set. So the data collection is complex. Why? Because it's consent driven. We actually like went to several different countries and translated our guidelines just to make sure that people who actually participate in the study understand why we are collecting this data set, and they show willingness, and they tell us, they give us their permission to use this data set for measurements. So in total, we've been to 7 countries, including Brazil, India, Indonesia, Philippines, Mexico, United States, as well as Brazil. In total, we have over 5,000 participants, in total of 26,000 videos of recordings. Dataset includes 11 categories, 7 of them self-provided and 4 of them annotated labels. So on the right side, you see the first version, and on the left side, you see the new version, the second version. So in the first version, you can see that it's very limited. It's only 4 categories, only 2 of them self-provided, and the subcategories are not well designed. In the second version, we extended the data set to 11 categories. We collected data set outside US as well. And in our recording setups, we allowed speakers to actually like respond free form to our selected questions, or we also provided them text from the Idiot Book of Dostoevsky to read the text in the videos. So if you actually would like to detail like the differences, you can see actually like what is new in the new version. So like for me, like what's really important is the gender definition. So it took us almost like 6 months to understand actually like how we should subcategorize these categories. In the first version, the options were female, male, other, but we know that society doesn't actually like accept it anymore. So the definition of gender is actually varies very frequently. I am aware of the HCI guidelines to include 25 different categories of gender, but for this study, through research, we actually decided to lower down it to binary, trans, non-binary, and self-defined options. Moreover, in this data set, we have 7 different countries. We include geolocation information. We also like provide people to tell us if they have any disability. We collect information about their physical adornments, attributes, and we label the data set for both skin tone that are usually like used in the research studies, Fitzpatrick and Monk skin tone. And this dataset is the first application of the Monk scale, actually, that was published by Google. On top of that, we also label voice timbre. We also provide different recording setups for robustness measurements, and we also label the data set for action. This is just an example of annotation file, how it looks in the data set. For each video, we actually provide all the annotations. Activity comes in another file because it's just large. But you can see that we have skin tone, but we have also confidence for the skin tone from the labelers. So we divide physical adornments attributes because one actually like refers to the birth and the one refers to the preferences of people. So if you look at the data distributions, we could see that actually the data set is mostly cis men and cis women. And this is mostly because we did not want to enforce participants actually to be chosen from a specific subgroup, but rather we allow them to like self-identify their genders. So another data distribution I want to show is actually the skin tone comparisons. We know that Fitzpatrick has its problems. It's not well representing darker skin tones. Therefore, we actually want to provide both scales in the data set so we can do through comparisons in the studies. On top of that, in this data set, we also allow people to speak in their secondary language, not only first language. We also allow them to speak, to choose the language they would like to actually like provide the data, and we provide all the text and their translations for participants as well. So this is the web page where you can download the data set. So this is a data set protected with a license agreement. And our license explains on what conditions you can use the data set. Since it's actually a people data, we would like to protect it. We do not want to allow people to use this data for everything. For example, protected labels should not be used for training. This is a data set mostly designed for measurements, although we allow training for specific cases, but not for the protected categories. So I will just end my presentation here. Datasets available, accessible. You can download and use it for your research. And I would like to answer your questions.
Question.
Yeah, fantastic work. I have a question about how you get some of these annotations. So things like skin tone are very hard to annotate, especially self-annotate. So do you have a process along with?
Yes. So the skin tone is labeled by vendor, by our labelers, and that's why we call it apparent skin tone. And how we do it actually, like we provide the video, sample videos to the labelers, and we actually label it by multiple labelers and actually provide the most voted ones.
Thank you for the very nice presentation. I have actually two questions, maybe the second one first, because it relates to your question. So when you say that you have basically a majority voting for these labels, do you additionally provide like the spread, how far the different labelers like disagree? Because obviously my case, I think most labelers would agree very clearly, whereas other cases, there could be a way of wider spread. And a second question related to that, did you see anything that like cameras have a very big effect on how you classify the skin tone?
So the first question, we don't release it, but instead we release the confidence scores for the labels, the final labels. And the second one was the effect of lighting. Yes. Yeah. So there's certainly like lighting in the videos certainly create bias in labeling process. We did not process the videos actually to reduce that bias, but what we did, since we have multiple videos of the same participant under different conditions, different lighting, different environment, it actually helps labelers to provide more accurate skin tone labels.
Nice, thank you. And maybe to the very first beginning, like you increased the number of countries.
Yes.
How did you actually select these countries?
Yeah.
And I'm from Europe. Was there any reason why there is no European country involved?
Yes. So this is a data collection effort and there are regulations. So we have to meet the local ones, and GDPR is one of the reasons. Like you have to be very careful collecting data like from Europe. There are, for example, people who actually speak Italian, or like who speak German or like other languages in the data set. But since it's not collected in Europe, their geolocation is not Europe in the data.
Yeah, thank you. I was already thinking that it has something to do with GDPR.
Yes.
So I have the same problem. So thank you.
No worries.
Hi, so I just wanted to know that you mentioned you enforce not training on the protected attributes, right? So how do you enforce that?
So license protects it. Once you want to download a data set, you actually like sign our license, and then it's actually your responsibility not to use it. And of course, we have some tracking, like if you use it, we will be aware of it.
Okay, because I think currently it's a big problem that you cannot evaluate without the labels, and with the labels you are kind of leaking privacy. So those issues.
That's true. Our approach is actually like protecting it with the license.
Okay. And I think I noticed that there was no label regarding ethnicity.
Yes.
So was that dealt
Yes,
with?
there are two labels we on purpose excluded.
Okay.
One of them is facial expressions,
Okay.
because we don't believe that facial expression can be annotated or should be annotated. It has a lot of like issues, also like scrutiny in the academic society. The other one, race, ethnicity. So race is a social construct. We want to collect a like diverse data set, and we had to map the race to all countries. And so in some countries, the definition, not only the definition, but grouping is actually like very, very different. So we wanted to like stay away from race. Instead of race, we provided geolocation and skin tone, and we believe these two attributes are enough.
Okay. Thank you.
Yes.
Any other question? Yeah, so I had again the same geography question.
Yes.
Asia is covered through India and Vietnam.
And Philippines.
But I guess
There are more, yes.
the larger.
Yes, yes.
China context.
That's true. So
other similar legislative restrictions.
there are actually like, yes, a lot of like restrictions in those countries, but we also want to actually like you want to collaborate. So actually like we want to release the data set and look for opportunities to collaborate with locals as well as researchers to extend it. And also like, of course, meeting regulations is our primary concern.
All right, great, great job.
Thank you very much.
We will switch to our invited speaker. So
hi, everyone. Are you able to see my screen?
I presume, Alice, you can hear us, right?
Yes. Are you able to hear me?
Alice, we cannot hear you now.
Oh, okay. Let's see.
We can see you, but not hear you.
Oh, yikes. Let me see.
Kwanchan, but we can hear her on the Zoom call. Do you think there's a difference on site versus the Zoom call?
We still cannot hear you, Alice.
Yikes. Okay. Is there something I can change on my end, or are you able to hear other people on the Zoom call?
I can check maybe. Kwanchan, can you hear me? Alice, maybe let's give Kwanchan and Nalini a couple of
Alice,
minutes.
Alice, can you speak again? Sorry.
Yes, I can hear the workshop.
no, we can't hear you here.
They can hear on the Zoom, but not on site.
But I'm on the Zoom now here. We can't hear.
I think on Zoom it's
you turn
fine,
on the-
Nalini.
Everything is
You turn on Zoom.
So just to confirm, can you hear anyone else on the Zoom call?
Maybe let's give them a couple minutes, Alice.
And just a small note, my last name is misspelled on this slide.
Oh. Yeah.
The XI.
Maybe you do the introduction first.
Yeah, everything is, we need her.
Yeah.
So introduction is the easier part, right?
Yeah, Alice, can you say something again? Because we,
Sure. Hello?
we're all on Zooms, but on sites, attendees cannot really hear you though.
Sorry, can you hear me now? Hello? Are you able to hear me? Still no? Hello?
I can hear on Zoom. I think Zoom is not an issue.
I see.
Do we share yours?
And are they able in the workshop to see anyone able to see the Zoom chat? I wonder if we're not able to be in communication with them.
Yeah. Now we have to hear you. Just give me a minute.
The audio power, I think.
Okay, I will get started in a minute. I think it's okay. One more check, if you could just speak once more.
Sure. Can you hear me now?
Oh, I think it is this. I can this. Yeah, connect. I think that seems to be speaking.
Sorry, you can hear me now?
Yeah.
Great, awesome. Okay, should I go ahead and share my
Yeah,
screen?
just hold on a minute. Let me introduce you to the audience. So we are lucky to have Alice Wong. She is the global head of AI ethics at Sony. We were just talking about legislations and regulations, and she is the expert in the space. So she is not only a lawyer, she is also a practicing privacy and AI regulations at Sony. So she has been involved technically at several conferences. So I think this we are looking forward to her talk. It will be very exciting for all of us to see a very different perspective than building deep learning networks. So Alice, welcome, and we will look forward to hearing and her talk is entitled Being Seen versus Misseen, Tensions Between Privacy and Fairness and Computer Vision. Thank you, Alice, for joining us. And she was planning to be here, but she fell sick in the last minute. So thank you, Alice, even while you're recovering, to join us. Please go ahead. Please join me in welcoming Alice.
Thank you so much for the invitation to all of the organizers, and thanks so much to the attendees for coming to today's talk. I can't seem to share my screen right now.
Yeah, I'm going to unshare.
Okay, no worries. Yeah, I guess let me know when I can share my screen. I guess you might need to take down the current slide.
Yeah, I'm just
Oh, yeah,
trying
no
to do
worries.
that.
Sorry.
Yeah, go ahead. You should be able to share your screen.
Okay, great. Thank you. So yeah, thanks again to everyone for attending, and thanks to the organizers for the kind invitation. Apologies if it's a little bit difficult to hear me. I'm still recovering from illness. But today I'm very pleased to have the opportunity to share with all of you a presentation on being seen versus misseen, tensions between privacy and fairness in computer vision, which I published last year in the Harvard Journal of Law and Technology. And before we get into this presentation, I just wanted to provide you a very brief overview of the research lab that I lead within Sony. So our AI ethics research lab is basically oriented towards developing solutions to try to enable AI ethics in practice. And so what that means is that we try to focus on fundamental unsolved problems in the literature that don't have easy solutions. And the goal of our research is to try to address what's preventing implementation of more ethical or responsible practices and propose solutions that can be practically implemented. And so the scope of impact that we target is AI development across Sony, of course, but also academic research communities and industry best practices. And our research team is, constantly growing. So if you're interested in joining, please do not hesitate to reach out. But our team spans the US, EU, India, and Japan. So we have a very globally distributed, diverse team with a lot of folks working in particular in the computer vision space. And a lot of our research focuses on 3 specific areas, particularly questions of ethical data collection, bias measurement and detection, and algorithmic bias mitigation techniques. So many topics I'm sure are quite interesting to many folks in attendance today. And before I get into my talk today, which is primarily on this legal paper, I also just wanted to share with you a couple other papers that we have recently published this year as well. So one is A View from Somewhere, Human-Centric Face Representations, which we presented at iClear earlier this year. And in this paper, basically, we're tackling the problem that very often when you're trying to do fairness-related work in practice, you don't have access to ground truth labels about sensitive attributes. And this is especially true when you're talking about very large data sets that might be used for training purposes, for example. And in those contexts, of course, there's much research showing that having more diverse training sets can be quite helpful for addressing issues of bias. So to enable folks to be able to compare the diversity of unlabeled data sets, we leverage an odd one out face similarity judgments from human workers to learn a continuous human interpretable face embedding space to then enable greater scale of diversity representations and comparison of unlabeled data sets in terms of diversity. And we aren't explicitly learning any particular labels. And so this also helps ensure that these diversity metrics are not relying on stereotypical representations. In addition to that, we have a paper coming out in ICML next month that is looking at multi-attribute bias amplification. So this is in the image captioning context where a lot of the existing metrics are focused on, are focused on single attributes. But as we know, a lot of the problems within bias in the computer vision space come with spurious correlations that might span multiple attributes. And so we designed a metric that can help capture these sorts of biases with not just a sensitive attribute and one object category, for example, but with multiple attribute annotations. And we also show that on average, bias amplification from multiple attributes is actually greater than that for single attributes, and that if you use single attribute bias annotation methods in isolation, you can actually inadvertently increase multiple attribute bias amplification. And so I also encourage you to check out these papers if you're interested in any of these topics. So that brings me to the topic of today's discussion, which is this tension between privacy and fairness in computer vision. And for this paper, the topic is human-centric computer vision, which I define here as computer vision systems that rely on images of humans for training or testing. And this includes a wide variety of use cases, such as pose estimation, face body detection, face verification recognition, but can also include tasks like object detection insofar as images of humans or images featuring humans might still be included in the training or testing sets. And this is important because the core tension I'm discussing today is how we can collect appropriate training and testing sets in a context where there are strong privacy regulations. And one thing I always like to clarify at the start of this, and this is something that's really not news to anyone in this audience, but can sometimes be an important caveat for folks, which is that when we're talking about human-centric computer vision technologies, this is not just facial recognition technologies. And that's important because a lot of the regulations that we see in this space and a lot of the motivations for privacy regulations in particular are concerns around high-risk facial recognition use cases, particularly those involving public surveillance or law enforcement use of these technologies. But when we talk about the impact of these privacy regulations, it's not only on these high-risk facial recognition technologies, it also impacts other sorts of human-centric computer vision technologies, including those for entertainment. So for CGI for scene generation, visual effects on artists, for actors, for example. Sorry. Robotics in terms of person or object detection in the real world, or very benign use cases in photography, such as autofocus that might involve a face detection feature, or automatic filters or blurry bokeh effects that might also involve face detection on some level. So despite the wide variety of use cases that we see for HCCV, what we typically see what we see on the law enforcement side of things is three primary approaches here. So on the one hand, there's been a lot of movement to prohibit certain use cases of HCCV. In particular, in the US, we've seen a variety of state legislation, local legislation, and state moratoriums on the use of facial recognition technologies for law enforcement purposes. In addition, the EU AI Act would prohibit real-time remote biometric identification by law enforcement motivated by similar reasons. In addition, there's high-risk requirements under the EU AI Act for remote biometric identification systems more generally, so not just those that are used for law enforcement purpose. In addition to that, we have this key piece of biometric information privacy regulations. And these are quite interesting because they were developed by and large before HCCV became such a prominent technology, and indeed before AI became quite so common. And so even though these were not really necessarily designed with AI or HCCV in mind, they have had significant implications in that they have quite stringent consent requirements for the processing of facial or other biometric information, which is readily available in human images. And in particular, we've seen many lawsuits, in particular in the US around Illinois' BIPA, but also GDPR in the EU and other regulations that have been inspired by these. So in the context of that regulation, we also see on the AI development side an increasing awareness of both privacy and bias as key ethical concerns that must be addressed. And so on the privacy front, this has especially been driven by many lawsuits, particularly 2021 is when we started seeing a lot of settlements in the space, including a $650 million settlement against Facebook for their use of their tag suggestions tool, which didn't have sufficient consent in terms of processing people's face biometric information. But then on the other hand, we also see growing realization in the community that there are significant issues of bias and that many computer vision systems do not work as well on people based on their skin tone, gender, ancestry, or other features. And so given that we want to address both privacy and bias simultaneously, it's important that we look deeper into the potential tensions here. And so as an illustration of these tensions in practice, I like referencing the diversity in faces cases. So this was a data set that IBM put out in 2019. And the goal of the data set was very positive. It was to provide a more diverse and balanced face image data set to help enable folks to do more appropriate research in terms of addressing potential biases in computer vision. The problem, however, from a privacy perspective was that like many of the data sets that at the time were used and continue to be used in computer vision research, this data set was based on Flickr images that did not have explicit informed consent from the featured subjects. So for a long time in the computer vision domain, folks have relied on IP protections such as Creative Commons, but that actually has nothing to do with privacy or consent. So even if someone uploads an image with Creative Commons, that doesn't mean that the person in the image has actually signed an informed consent form for their biometric information to be processed. So as a result of this, there were a number of lawsuits that emerged against not only IBM, but also Microsoft, Amazon, and Google, who had downloaded this data set as well. And so this was a wake-up call in terms of the extent to which these biometric information privacy laws could make it quite difficult for folks to use data sets that have been web scraped for computer vision development purposes. So digging one layer deeper in terms of the nature of this tension, it's worth considering a few things that are very important for fairness research and that might create complications from a privacy perspective. So first off, ever since the seminal gender shades paper, there's been a lot of understanding in the computer vision community that underrepresentation in the image data sets used for training, but also for fairness evaluations can lead to biases downstream in the models. And so there's been a lot of push for folks to try to use more diverse data sets to try to actually address these issues, and also for folks to start checking for bias through using evaluation sets that are more balanced. Now, this, of course, creates some direct challenges from a privacy perspective, where the need to go out and source more diverse images can directly run into some of these privacy regulations. In addition to that, we're not just concerned about representation along one dimension. There's been a lot of work, including in the revised paper, which this graphic is from here, showing that a lot of biases are not just one-dimensional, but also related to how people and objects might be represented in very different ways. And so in this figure, we see that correct female classifications that are confident tend to be images of women in sort of portraits with beautiful flowers in the background and a very kind of pretty aesthetic, whereas confident correct male classifications are men in more formal stately occasions that are quite different and reflect additional societal biases beyond just the presence or absence of women or men in the context of flowers. And so if you're trying to really address not only diversity along one dimension, but all of these possible spurious correlations as well, this further creates a lot of challenges in terms of the amount of data that you might need to collect and the context in which you would need to collect them. And then finally, when it comes to bias detection and mitigation techniques, usually these do require access to protected attribute labels. And so this then triggers a whole other set of privacy regulations where not only are the biometrics in the face images themselves protected, but also there are, depending on the jurisdiction, specific protections around certain sensitive attributes like race in particular. And so if you're trying to do any sort of work on on bias detection or mitigation, that immediately runs into additional privacy concerns. So as a result of these issues, we see that there's a lot of challenges with ethical human-centric image data. So on the one hand, in the computer vision community for a long time, there's been a reliance on data sets that have been web scraped and not necessarily with informed consent. And then data sets that are collected with informed consent or that are with synthetic humans tend to have issues in terms of either lacking diversity or lacking realism. Because if you're collecting with informed consent, it's often in much more constrained settings. And with synthetic humans, there's still a significant domain gap between how they appear versus real humans. And indeed, if we look kind of more expansively at the challenges that are faced in terms of collecting new data sets, for one, it's a very expensive process, especially for smaller companies or labs. In addition, it's very difficult to define appropriate diversity specifications. This was elaborated on a bit in the CCV2 presentation just before, but it's quite difficult to say what are appropriate, for example, racial, ethnicity, ancestry categories or gender categories. These are all very difficult questions that don't have any clear answer that everyone can agree upon. In addition, there's a lot of concerns about representation versus exploitation of underrepresented communities. So for example, there was the famous case of Google working with some data vendors where they had specifications around the diversity of skin tone and race, but then it turned out that some of these vendors were preying upon homeless individuals in order to get more diversity in their data set. And these homeless individuals did not fully understand what they were signing up for. So that then led to all of these headlines about Google preying on homeless people in order to try to develop fair data sets. And so that's, of course, not what we want to encourage in this sort of context. But it can be quite difficult to just say in the abstract that you want to collect images of more diverse people without specifying how do you really ensure that people understand what's going on and are truly consenting, especially when money is being exchanged. In addition, there's a lot of challenges in terms of if in an ideal world, maybe we would have, these data sets available that are basically globally representative, because not only do you want diversity of the subject, you want diversity of background. There's been studies showing that objects look different in different jurisdictions. And so if you are just collecting data in one country, that's not necessarily going to ensure that models trained or evaluated on those data sets are going to sufficiently address bias concerns. But given that every country has different laws and regulations around privacy, even if you are earnestly trying to address these, it can be quite difficult because you need local counsel in every single country in order to evaluate whether your procedure is appropriate. And then finally, not only in many countries do you need to collect consent from people, but also particularly in the GDPR context, for example, you have to have consent revocation as well. And so that means at any point people can remove their data from your data set, which then can create some loopholes, especially if you're paying for people's data because they can be paid, but then remove their data shortly thereafter. So these are some of the kind of real world challenges that folks are facing in terms of collecting these data sets. So given these, so given these tensions that we're seeing between trying to reconcile a desire for bias mitigation and a desire for protecting and respecting privacy laws in practice, it's worth thinking, how can we try to navigate this space and try to find solutions that optimize in both of these directions as much as possible? So the first step towards that is to try to think about what are the actual harms that we're trying to prevent, because it's very easy to just say broadly, we want to prevent privacy harms, we want to prevent fairness harms, but what does that actually mean? So if we review the case law that we currently have. So in terms of privacy, there's not a ton of case law that is very specifically about this area of AI development, because this is still a relatively new area. Most of the cases in this area end up settling instead of reaching a decision. But if we review what legal materials we do have available, we see that there's 3 primary types of harms that have been surfaced by courts that they want to prevent when it comes to companies using people's face images. So for one, there's been a lot of concern about identity theft. So to what extent can the release or the usage of these face images enable folks' identities to be stolen? And one thing that's very important to think about within this is at what point does that harm actually take place? Is it at the point where the face images are used for training and evaluating HCCV systems, or do the images have to be publicly shared? Because it's not always clear that just using images for training or evaluating such systems necessarily leads to identity theft concerns, whereas the public sharing of such images can more directly facilitate that. The other concern, which is probably the biggest concern or most common concern in this area, is the extent to which HCCV can enable mass surveillance. And here there's a little bit of sometimes a conflation of two things, the use of HCCV in general versus the use of images to develop HCCV. And this is important because there's arguably a difference between the use of identifiable images and reference sets and the use of HCCV in deployment and the images ingested in deployment compared to the use of anonymous images in training and evaluation. And then finally, and this one is, part of what most strongly motivates the necessity for consent in this area is the sense that people can feel a lack of control over their information. And indeed, a lot of the news reports as well in this space have really emphasized the creepy or scary factor of people's images that they may be posted on Flickr, on Google Images, elsewhere, and then suddenly those images being used to develop HCCV technologies. And so the concern there is to what extent your personal data might be used to develop technologies without your knowledge or without your support. So that's on the privacy side. In terms of the fairness side, there's a variety of harms that have been identified that we want to address through tackling these issues of bias. And so first off is allocative harms. So this is probably the one that has most strongly motivated a lot of the prohibitions on especially facial recognition technologies in certain jurisdictions. So this is when HCCV inaccuracies lead to misallocation of goods or opportunities. And the highest stakes examples of this have been the wrongful arrests of Black men several times, like every single year this keeps happening in the US for crimes they didn't commit due to faulty facial recognition matches. And so in these cases, many of these individuals have had to pay substantial sums or even sit in jail for days or weeks before the misunderstanding was cleared up. In addition, there's a lot of concerns about representational harm. So this is when HCCV systems represent certain groups in negative, offensive, or otherwise problematic ways. So perhaps one of the most famous examples of this was back in 2015, when it became very public that there was an image of two Black individuals that Google Photos labeled as gorillas. And this is still a problem that hasn't been fully solved. In recent news reports, the New York Times reported that Google Photos and similar services simply avoid identifying gorillas, baboons, chimpanzees, orangutans, monkeys, so on and so forth, to try to address this issue, but they haven't actually fixed the fundamental problem of their identification systems. In addition, there's concerns about differences in service provision. So this is when individuals experience different levels of service because HCCV performs less well on certain groups versus others. So one example of this is some automatic blink detectors on cameras, which have been shown to often have very high false positive rates for Asian individuals, and asking them whether they blinked when they didn't. And this is especially offensive given a lot of the negative stereotypes around Asian eye shapes. And then finally, we have security threats. And so this is when worse performance of HCCV technologies for certain groups can facilitate unauthorized access. So an example of this is when the iPhone X first came out, there was controversy in China because a lot of individuals were finding that their friends or family members could unlock their phones. In particular, in one case, a woman found that her son was able to unlock her phone. So the fact that the face verification system was not able to correctly distinguish between different Chinese individuals led to these potential security threats. So in light of those as the harms that we're trying to prevent, it's worth considering what are possible solutions where we can try as much as possible to balance both privacy and fairness. So I will caveat this by saying that this is not a tension that's so easy to carve around. This is quite a fundamental tension. So none of these solutions are a silver bullet. And I would not say, you know, we need to run 100% in one of these directions. Each of these has pros and cons, which my paper elaborates on in much greater detail. But these are kind of my attempt of mapping out at least the potential options that are on the table. So basically, these can be categorized into three bins. One is so if we think of the goal is trying to create more balance between privacy and fairness, one is trying to create some carve-outs from privacy law to make it a little bit easier to balance these two. Another is to alleviate some of the concerns people have with having their data being used for the development of HCCV technologies. And then the final is kind of increasing some of the stakes around not having appropriate fairness protections. So to first start out with the narrow carve-outs from privacy law, I will say this is the category that is probably least likely to happen and most controversial because, you know, at a time when people are increasingly concerned about these privacy issues, the idea of having any sort of carve-out is extremely controversial. But I'll just put these on the table as possible options. So one is to try to distinguish between images used to develop HCCV technologies versus images being used in deployment. So again, this is assuming that mass surveillance is one of the primary concerns here. And so what this would imply is that there's a difference between images used in training and evaluation, which don't necessarily increase the risk of the individuals in those images being surveilled versus images used in deployment. So images ingested by the model or images in any sort of reference set. Those much more directly would lead to mass surveillance concerns. And this is also reflecting the fact that there's a lot of HCCV technologies that might be completely unrelated to mass surveillance. So especially if we're talking about HCCV technologies that might just be used, for example, for pose estimation in an entertainment or video game type of context. Other possibilities in this space include making biometric information privacy laws more domain-specific or sectoral. And so the idea here, right. The idea here is that one of the major challenges in terms of balancing privacy and fairness currently is that biometric privacy laws apply to any sort of processing of biometric information, and it's not domain specific at all. So it treats high risk versus low risk use cases the same. Whereas in contrast, anti-discrimination law, which is what's relevant for fairness concerns, is highly domain specific. So it's specific to domains like finance, employment, schooling, things like that, which have a higher risk profile. And so one possibility is to make some more distinction in terms of biometric processing for high versus low risk use cases. Another possibility is to make identifiability more of a salient concern when evaluating biometric data collection or processing. So arguably, in order to enable mass surveillance, identity theft, or some of these other considerations, some of these other harms, a key factor is at some point in the line, the individual needs to be identified. And so if that point of identification is where things become higher risk versus just the point of biometric processing, then that could enable more uses that are lower risk for development while preventing higher risk use cases in deployment. And then finally, there could be possibilities in terms of creating carve-outs for the processing of such information for bias detection or mitigation purposes. And this is especially relevant for the question of sensitive attribute processing. And this is actually something that the UK, for example, did provide guidance that would provide this sort of carve out in certain cases. So this is something that could potentially be adopted in other areas as well. So moving from carve-outs from privacy law, the other area would be trying to alleviate some of the concerns that people have with being seen. And what I mean by seen here is having their data ingested for developing HCCV. And some possibilities here include, first off, participatory design. So this is something that has been proposed in the literature in terms of trying to engage more directly stakeholders who use or might be affected by technology to build trust among the data subjects and collectors. And so this is quite important, especially in areas where you might need data that is serving a very specific community or where the technology involves quite bespoke data collection. So in those cases, I think this is quite a beneficial solution. It can be much harder, though, when we're talking about this for the development of, for example, large foundation models, where the scale of data collection is quite difficult to achieve while simultaneously trying to build these close stakeholder relationships. So that remains a bit of an unsolved problem on that front. Another possibility that has been proposed in the literature is trying to rely on trusted third-party data collection. So if the primary issue is a lack of trust of large companies in particular collecting people's data, then finding trusted third parties might be a way to alleviate this. Now, the challenge in this category is that it's not totally clear what the appropriate trusted third party would be. So oftentimes people point to government, for example, as a good option here, but there is a long history as well of questionable data collection practices by government entities. So for example, as useful as NIST's facial recognition vendor tests have been, a lot of the images they relied on for that were mugshots, images of visa applicants, border crossers, people, children who have been exploited. And so there was a lot of reliance on marginalized individuals who did not necessarily consent to their images being used for facial recognition vendor tests. And so this is still a very difficult space to navigate in terms of who would be the right trusted third party. And then finally, there has been growing promise in terms of technological advances, such as synthetic image generation and federated learning to help address some of these concerns. Again, none of these are necessarily a silver bullet in that for synthetic image generation, there's still a significant domain gap, especially if we're trying to consider not just the realism of the people, but all of the diversity of backgrounds, diversity of object-human interactions, human-human interactions, all of that. And then federated learning still requires on-device processing, which certain cases have deemed to be inappropriate if people have not really consented to their processing power being used for such purposes, especially if the processing is of their own personal biometric information. So the final category here is trying to provide a right against being misseen. And misseen in this context means misrecognition by a HCCB model. And so the idea here is that at the moment in practice for developers navigating the space, there's so much red tape on the privacy side. But on the fairness side, there's basically just, for the most part, not much in terms of legal incentives to actually address fairness. Of course, a lot of developers understand this issue and work very hard to address it. But from a legal standpoint, there's not much that pushes or enables companies to actually address this. So the idea here, there would be two possibilities for how this could work. One would be to have a right for HCCB systems to have some sort of minimum performance level. Now, this is unlikely to work super well in practice due to a lack of a common sense across the industry of what that minimum performance level would be, especially if we talk about more bespoke applications for HCCB systems. And so there's some limitations in terms of the extent to which existing product liability doctrine and negligence law could enable appropriate protections if this was the approach. Another approach would be to establish an anti-discrimination right specific to HCCB systems. And the goal here would be to ensure that, that these systems do not have disproportionate performance on one subgroup, and this could be enforced by an agency or through private right of action. And so the idea here would be to basically give some teeth to fairness concerns by having more of a right for folks to contest disproportionate performance. So those are basically some of the possible ways that in this paper I've mapped out trying to address these tensions. In terms of overall takeaways though, I think one very important overarching takeaway from this paper is that it's very easy to make a list of AI ethics principles and say the goal of AI ethics is to be as fair, privacy preserving, transparent, accountable, so on and so forth, explainable as possible. But what's really difficult about AI ethics in practice, and what often prevents the implementation of more ethical solutions in practice, is this balancing act where many ethical desiderata are in practice sometimes conflicting, which can be quite challenging to navigate. And in this context, often there is a bias towards focusing more on the ones that have strong legal or regulatory incentives. And so in particular here, there are very strong teeth, very strong incentives when it comes to addressing privacy concerns, but not really many when it comes to addressing discrimination or fairness concerns. And then finally, if we are going to try to move towards a space of more ethical HCCV, directly trying to tackle these privacy and fairness tensions and addressing them head on will be key to actually having solutions that practitioners can use in practice for such development. So that's it in terms of my presentation, and I'd be happy to answer any questions that you'll have.
Thank you, Alice. Any questions? Go ahead.
Great talk, Alice. My question is about, oh, sorry, I'm getting some echo here. All right, thanks. My question is about the definitions of biometrics and how it's interpreted by lawmakers and the legal system. It seems like there's not really much, agreement on this point. It's you've put us in your deck, you've pushed for, I guess, a more usage-based definition, right? What is the technology being used for? That's not really how the law seems to be stated today, right? It seems to be more from a technological perspective. Are you computing biometrics, and the interpretation of what that word means seems to be at least fraught. So could you comment on how you see that playing out? Like, are we heading towards a more consistent definition or consensus definition that most lawmakers agree with and technologists agree with? Do you think that that's going to diverge from or oppose the viewpoint that you put forth?
Yeah, great question. So yeah, I mean, basically one of the reasons, so BIPA in Illinois especially has been, the primary source of most of these lawsuits in the HCCV domain. And partially that's because it's quite expansive, because it talks about basically facial geometries, any sort of measurement, like distance between the eyes, like things like that would count as biometrics in this case. And so it's very difficult for any application of HCCV to not fall within this. So even like TikTok got sued for their filters, which of course you'd think if someone is putting the filter on their face, they would it's a relatively low risk use case. But it still counts as processing people's biometric information. And so, part of the motivation for writing this paper is I don't think from a regulatory perspective, people quite realize that this is a problem, and partially because it's not the most sympathetic audience. If you think about it, it's like, okay, the companies getting sued are large companies that lawmakers are often upset about for other reasons as well, like especially social media companies. There's a lot of concerns that lawmakers did not necessarily take action quickly enough in terms of a lot of concerns around social media, and so now there's not a lot of desire to back down in terms of regulating those companies, even though this is technically something that's not really specific to social media or not necessarily directly related to that. But I think, part of what I want to point out with this is, there's a lot of us working in this fairness space. There's a lot of us working in this computer vision space who, earnestly want to make these models less biased and are kind of looking at our array of options. And there's not super great options, especially, if you are working in a context where you are trying to very strictly follow relevant privacy laws, it's quite difficult. Even just, publishing papers in the computer vision space, you basically have to use data sets that, have various issues from a privacy perspective. And so it would be great to get to a point where we don't need that. My hope in this space would be, as we start seeing more AI specific regulations, such as the EU AI Act, there might be, there might need to be more acknowledgement of these sorts of tensions. What would be really bad is if these laws just kind of stack on top of each other without any sort of consideration of the challenges of navigating these tensions in practice. So if you're just like, okay, under GDPR, you have all these strict privacy requirements, and now under the EU AI Act, you have all these requirements around the representativeness of your data and the free and your models being free of errors and all those things. So if those just kind of stack on top of each other, I think it's going to be quite difficult in terms of what do we do actually in practice. But the hope would be to confront those tensions head on and to get actual regulatory guidance in terms of, how should, companies or developers working in this space address these issues? Like, are there going to be data sets that can be provided? Are there going to be carve outs, from existing laws? What should be the weighing of this rather than each developer basically trying to weigh this on their own?
Thank you. I think since we are running a little bit late for the coffee break, which is already kind of finishing here soon, let's stop here and thank Alice again, and we will regroup here in 15 minutes. Thank you, Alice.
Great. Thank you, everyone.
I guess there are other things that will catch up as on the schedule. So the post-coffee break session starts with the talk on Schrodinger's camera, first step towards a quantum-based privacy-preserving camera. And Hannah will present her work.
Now you can share the screen.
Thank you. So I'm Hannah, and this is, like we said, Schrodinger's camera, first steps towards a quantum-based privacy-preserving camera. And first of all, okay, there we go. First of all, we know that clear images are really useful, right? We can get lots of categorical information from them. So in this example, I have like a little pose drawn out, but machine learning algorithms can also infer private information. So in this case, I represented that by my facial recognition. But then on the other hand, completely blank images, you lose on both fronts. You don't have the privacy task being identified. You can't identify my face, but you also don't get any useful information from it. So part of the goal with privacy preserving vision is to still have that public categorical information, but not the private identity information. So we were investigating with quantum computing if there's any specific way that quantum computing can be used to do privacy preserving vision. So in this case, we had to use very small images. And we used EMNIST, and our public categorical task was whether something's a letter or a number, and the specific identity task is which specific letter or number. So in this case, we'd want to know that this is a letter, but not that it is a D. So why should we care about this though? For one, quantum computers offer incredible speed ups, especially for some classic computer vision or image processing algorithms. So one example here is edge detection can be done in 01 time. It also has increased security. One fundamental property of quantum computing is that eavesdroppers can always be detected. This is like the basis of quantum key distribution. And also there's quantum image sensors that are developing. So for one, there's quantum dot image sensors and there's photon counting cameras. Both of these right now are mainly connected to classical silicon computers, but considering that these sensors are developing and quantum computers are developing, in the near future, they're going to be combined. And then in that scenario, we're going to need new algorithms, new methods for privacy preservation on quantum computers. So some basics with quantum computing to be able to understand what we're doing in this project is, for one, the quantum analog to a bit is a qubit. The difference here is instead of encoding just a 1 or a 0 like you would on a bit, a qubit encodes a probability distribution. So it's what's the probability that you're going to measure a 1 or measure a 0. And this measurement is what basis that the wave function collapses to when it's observed. So this is usually corresponding to some physical property of the qubit. So if you're using electrons, that might be spin up and spin down as your 1 and 0. And since this is a probability distribution, you have to run these circuits multiple times to be able to recover that probability. And that's usually referred to as the number of shots. And then two other ones that are important. Entanglement is basically when those states, so those probability distributions, those equations can't be described independently of each other. This is the quantum superpower, I like to kind of call it, because that's what enables us to encode more information on one qubit than you would on a normal bit. And then the type of quantum computing that we're using here is quantum circuits. This is compared to some other methods like adiabatic computing, which also has some quantum computer vision applications. And you can have these gates that are similar to digital logic gates, but now are being applied to quantum circuits. And if they are in series, you use typical matrix multiplication. And if they're in parallel, you use a tensor product, which I have as an example here of what that does, since at least when I started this, I had never seen it before. Basically what you do is you take the vector, the first one, so psi, you take the values there, so the alpha and beta, and you multiply them by the entirety of the second vector, so in this case phi. So then you get like alpha times the entirety of phi, beta times the entirety of phi, and that represents the overall quantum state. So how this applies to what we're doing is the method that we use to encode these images onto quantum states is called FRQI. Basically what's happening here is the color information is encoded as the angle. So that was, if you remember the picture I just showed a second ago, it's the distance kind of between the 1 and 0 in that representation of a qubit. And then you need one color qubit and 2 n location qubits for a 2 to the n by 2 to the n pixel image. So we're also getting a major, I guess, like size or footprint size decrease compared to on classical computers, since all of the color information is stored on one qubit and there is less location bits. So then once we had our images on the quantum computer, we had to figure out how we can actually have a privacy preserving effect on these images. So one method that we found is that you can add additional quantum gates after you've encoded the image. We found that controlled rotation gates were the most useful. So if we see the column that's in blue, part of the image is redacted or changed. Part of it's inverted. It's complex. Additionally, on the bottom here, there's one with 3 different gates applied to it. And There are still some features there, but they are obscured to the point where at least a human looking at it can't determine what letter it is. And so then that's when we need to bring in the machine learning algorithms, but that's in the next few slides. The second thing that we can do is control the number of shots. So if we're trying to recover that probability distribution, if you run it more times, you get more precision on the probability distribution. But if you run it less times, you get more noise. Typically, this might be considered a con, especially if you're trying to encode images. But in this case, we can use it to our advantage and have it be a way of adding noise to our image before we even see it. So to implement these methods for privacy preservation in a way to actually like preserve privacy, we used reinforcement learning, specifically double deep Q learning. We treat our quantum camera system as a black box. So this is because this is done in simulation. So we assume there's a scene coming in, which in our case is this EMNIST data, and we encode it onto a quantum state. And then the agent sends actions to the quantum camera system. After that, the image is measured, and then we grade it on whether it can identify the public or the private task. And from that, we generate our reward, and it goes back into the loop. That's a classic like reinforcement learning setup. So as this is the first steps towards privacy preserving vision, first of all, we found that we can build this hybrid quantum computing model for privacy preservation. And we also found that our system kept the private task private. The other thing we found is that it only performs slightly better than Gaussian noise for the public utility task in our setup, which I'll get to in the results in a minute. So like I said, we use double deep Q learning, and we also used EMNIST, with the public task being a letter or a number and the private task being the specific letter or number. We experimented with different reward policies, which I'll also show in the results. And then for training, we trained until convergence, which is very standard, and then we froze the model. Then what we did was we ran our test set through the frozen model and generated all of these images that hopefully have our privacy preserving effect on it. Then in order to tell if our privacy preserving effect was actually there, we calculated the public utility and private task accuracies. And then we fine-tuned those models on the data because we are assuming that our attackers could retrain on our data. And we look to see, are those accuracies the same or do they change? Because if when you fine tune on our results, if the private task accuracy goes back up to where it was, you haven't actually really preserved the private task. Another thing is for this, we're assuming that our data is temporally consistent, like frames in a video. This could be thought of as a camera scanning text on a document, for example, where you're trying to apply a privacy preserving effect to each image. So the green line here is our best result. The top two, the first one is the initial CNN accuracies for the greater CNNs, and then also what we use to test our data set on. This was EMNIST that scaled down to 16 by 16 pixels and is augmented with random quantum gates. Then the Gaussian noise is the scaled EMNIST data that has just a standard amount of noise added to it. So this public-based reward policy, the reward was based purely on how well it did on the public task. And as we can see here, 2.5 was at chance, or below chance actually. And the public accuracy meets the Gaussian noise, which is good as a first step, especially considering that Gaussian noise performed above chance for the privacy task. So we can see here that it did actually learn a policy on how to use these quantum privacy preserving gates. Some challenges that we faced with this is that both reinforcement learning and quantum simulations take a lot of training time and power. So for example, our best performing model took almost a month to train. And also on the right here, I have a little graph of how long it takes to simulate each of these images. So it's a 16 by 16 image with 4 extra gates added to it. Already takes 20 seconds to simulate, which takes quite a long time with the size of data sets, and then also adding into that the reinforcement learning training. And then also the quantum circuits, they rise in noise and complexity with the circuit length. So right now on current quantum computers, the largest image you can actually run and then recover is a 2 pixel by 2 pixel image. And then even in simulations, the largest is 16 by 16, which is why we had to scale it down. So some future work that we'd like to do is some additional hyperparameter tuning and additional training with either more powerful hardware or just able to do longer training times. Maybe even experimenting with different reinforcement learning or different other different types of learning algorithms. And then also applying this framework to other privacy preservation problems, like different data sets. The only constraint here is that it would have to be able to be scaled to a small image size. And then another thing we would like to experiment with is constructing a toy problem that would be a 2 pixel by 2 pixel image that we could actually run on a real quantum computer. So I have an example here of what that could possibly look like just in terms of what gates could be added to it. So yeah, that's kind of where this is at as a first steps. And I'll take any questions now if you'd want, or right here I have also a QR link to the code.
Quantum computing lovers, experts or novices like me.
Yeah, that's why I went over some of the basics. I was
We have one question online, so let me ask on their behalf. How far are we from commercializing this, and what would be the major obstacles?
Well, it's probably still quite a ways away considering the largest image that you can actually recover on a current quantum computer is a 2 pixel by 2 pixel image. And the biggest hurdle is noise. That's literally why it's only a 2 pixel by 2 pixel image right now, which is the major hurdle that most people are researching right now, either in terms of new technologies to implement quantum computing or new ways to just keep computers cool, keep them isolated from all noise at all. So there's several different strategies going on to address that problem.
Please go up to the podium. The microphone.
You have to go here.
Microphone.
So when you implement your circuit, how many shots does it take to recover the image from the probabilities?
It kind of depends on how precise you want it, but usually what's standard is about 1,000 or 2,000.
Okay.
Yeah.
And how long in real time would that be?
For this, it would be, well, it'd be like 20 seconds times 1,000, I guess. But it kind of depends.
Okay.
It also depends on your hardware too, if you're running the simulations.
All right.
Cool.
More questions?
Thank you.
Thank you.
So next on the schedule, we have a paper presentation of robustness against gradient-based attacks through cost-effective network fine-tuning. Have you joined Zoom already? Please share your slide.
Hello.
Yeah, you can start.
Okay, good afternoon, everyone. So the paper title which I'm going to present is Robustness Against Gradient-Based Attacks through Cost-Effective Network Fine-Tuning. Basically, cost-effective means we want to propose fine-tuning based networks where we don't have to train a network for a longer time, or using any or basically using any adversarial training kind of approach, which requires a lot of computing resources and all those things. But still, we want to obviously provide a trustworthy and secure environment for deep learning based mechanism. So the agenda of the talk will be, first I will briefly talk about the introduction and the motivation of the approach, and then the contribution and what exactly we have proposed in this research paper, and then the experimental results and analysis. So obviously, as we know, training a deep neural network requires a lot of computing hardware and a lot of time. And on top of that, once we know that our network is not robust against the adversarial perturbation or common corruption or anything, it will be very problematic for us because we want to deploy the network at the end. So again, we don't want to retrain or we don't want to do anything to provide another level of robustness or security. So one of the popular defense towards adversarial attack is known as adversarial training, basically where we need to develop the adversarial example and then use those examples for retraining the entire network. Or another popular attack is, or defense is basically where you need to completely change the structure of the network which you already trained. But here we don't want to do all those things. We don't want to incur any heavy cost to fine tune or retrain the network, or we don't want to change the structure of the network. As we can see, AlphaGo, which requires 1920 CPUs and 2080 GPUs, and it's cost around $3,000 electric bill pay for game uses. And then the resonant architectures on M40 GPUs, it requires almost 2.5K, 2.5K to get the accuracy on the natural examples. But when we see the adversarial example, the accuracy will drop to 0% even. So the motivation is basically when I need to develop my deep networks, I need to train the networks, and it might require maybe a day or 2 weeks. But someone attacker will come and it will fool your network. But that will be your dilemma, like what now need to do. So the proposed idea is we already have a trained network. Can we just do the little bit fine tuning, maybe for 20 minutes, 5 minutes, or 10 minutes? And can we get the same kind of robustness towards the adversarial examples as well? So for that, we already have the clean data, basically the natural examples, and then we can have some kind of data which can provide the robustness. Basically, we are talking about the data augmentation technique. So in this research, we have proposed a novel data augmentation technique to just fine tune a network for a small amount of time, and can we somehow get the adversarial robustness. So it is already seen that the adversarial examples or the robustness or the filters of the convolutional neural networks slightly or heavily depend upon the properties of the input image, basically the local properties of the input image. Like the upper in the MNIST image, if you will see that upper round portion of the digit and spiky flowers and all those things in the CFAR images or color object images, the filters will be looked at that only. So can we modify the local properties of the images to provide the non-randomness to the network, so that when the network will see some non-random structure in the adversarial pattern, it might be robust towards those changes. So for that, we went into the image domain, and in place of perturbing the entire image, because of this observation that the filters of the convolutional neural network might be affected because of the local properties or local structure of the images. So we went into the local domain, and suppose these are 2 blocks of the images, which we only want to perturb or modify through the some kind of data augmentation techniques like a rotation, Gaussian noise, or the corruption noises, and then all those other changes. Let me describe that as well. So different kind of common corruptions, because not only the adversarial attacks, but the common corruption is also a problem. Common corruption is basically the natural noises like Gaussian noise, salt and pepper, speckle, and all those kind of noises, And obviously in the natural environment, when we capture the images, it might not be exactly frontal image. Some kind of rotation might be there. And rotation can be possible in the certain portion of the image. So those boxes which I was showing earlier, so we rotated those boxes as well, like 10 degrees, 20 degrees or 15 degrees. And then the translation and all those rotation can also be provided. So once we got those augmented images, we fine-tuned the network using those augmented images for 20 minutes and 5 minutes only. And then those networks we are claiming that are robust towards the gradient-based adversarial attacks. To showcase that and to prove that this approach is effective, we have taken a multiple data sets and popular object recognition data set, basically MNIST, CIFAR-10, and the ImageNet. And the network which we have used is BGG, ResNet, and a couple of custom models. The architecture of custom models is like shown below in table 1. And then the popular gradient-based attack, basically fast gradient, FGSM, PGD, and all those things. So as you can see on the natural images, BG16 is getting an 83% accuracy on CIFAR-10. But as we know that when we give the adversarial images, the accuracy can drop to even 0%. That you can see from the second row. Like the accuracy is almost 0.87% only. So in this study, we have performed a couple of evaluation studies as well. Like 7P1 basically means P1 basically means the one patch if you want to modify. 7 is basically means 7 cross 7 patch. So we found that in place of modifying multiple patches of larger size, basically 11 means 11 cross 7. So we are seeing a local patch of small size, 7 cross 7 only, will provide better robustness as compared to providing the global modification to the image. Which basically means in place of modifying the entire image, you should only modify the small portion of the image. The same can be found out for the resonant architecture as well. Where the small modification, 7 cross 7, and a single patch modification is more effective as compared to modifying the larger patch and the multiple patches. So again, we perform the comparison with existing several state-of-the-art techniques, and we found that the proposed technique is more effective as compared to existing techniques, which are not only computationally demanding, but requires a lot of computation time as well. Similar to CIFAR-10, the robustness can also be found for the MNIST dataset and the subset of ImageNet dataset as well. Which basically means that the approach is not only effective for small scale images, color images. MNIST is basically the grayscale image, and the ImageNet is basically the high resolution image. So one more question which can come into the mind, like, because we are fine-tuning the network and we are using the pre-trained models. So the one question might be the pre-trained model might be trained on different kind of optimizers. So is it possible that at the time of fine-tuning, do we really know the optimizer which we have used for pre-training? So in the first study, we have performed the fine-tuning using the different kind of optimizers. So, and we found that when we are training with different kind of optimizers, our approach is more effective and can provide the robustness to the networks. And the second thing is because we are doing fine-tuning, and for that we are developing a novel data augmentation technique. So the question can be, why not just pre-train the model using the augmentation images only? So clean images only means we are training the network using the clean data only. And then proposed data augmentation, third column basically means we are training the model from the sketch only using the proposed data augmentation. Here we are not doing any kind of fine-tuning. But the last column basically means we already have the pre-trained model and then we are doing the fine-tuning. So that fine-tuning is more effective as compared to the training the network using the initial data augmentation, whatever we have developed. So fine-tuning is more effective as compared to training the network using clean data and the augmentation data. And why the model is cost effective? Because as I mentioned, that adversarial training is one of the most popular and effective defense. And you can see the reduction in the computation time is like approximately 12 times, 6.4, and all those at least 5 times we are getting a reduction in the defense mechanism. And another popular concern towards adversarial defense is while we are getting a robustness, we are reducing the accuracy on the clean images, which should not happen. So the proposed approach is while providing the robustness, is not downgrading the accuracy on the clean images. As you can see from the popular adversarial training defense, the proposed accuracy is higher than the existing popular and effective adversarial training approaches. So obviously, we propose a fine-tuning approach. We can train the network from the initial augmentation technique also, but we found that the fine-tuning is more effective, and we are just fine-tuning or changing the local structure. And on top of that, we don't have to modify the multiple patches of different size and all those things. We just need to modify the single patch of small size. So proposed approach not only providing the robustness, but can also improve the accuracy of the clean images as well. Clean images basically means we are not adding any kind of natural noises or any kind of corruption on those. So I think, yeah, that's all.
Let's thank you.
Question. No questions, I guess.
Yeah. Not online.
All right, so let's thank him again.
Yep.
We'll move on to the keynote talk.
Please, I'll share your screen.
It's good, right?
Yeah.
Okay, so now we'll move on to the keynote talk from Professor Jayashree. She is now a professor at University of Colorado School of Medicine and chief of the Division of AI in ophthalmology, or AI, artificial medical intelligence in ophthalmology. Before that, she was at Harvard, and she has been working in algorithms or in the clinical area of radiology, oncology, and ophthalmology. So over to you, Professor Jayashree. We welcome you remotely.
Thank you very much. Can you hear me? Can you see me? Hello, can you hear me?
Yes, we can.
Okay, great.
Can you say something? Maybe we were not able to hear you before.
Can you hear me? Hello?
We can hear you online.
Yeah, I think we had this issue earlier, I think so.
I guess we still don't hear you here.
The online attendee can hear.
Okay.
Can you hear me now?
Yes, that's great.
Excellent.
Please unmute.
I can share my screen as soon as it says I cannot share screen while it's being shared.
We're trying to unshare our current screen so that you can share. Please give us a minute. Thank you. Yeah, you can share your screen already. Yeah, we can share the screen. Thank you so much.
So yeah, thank you so much for the invitation to speak here today. I'll be touching on some of the issues of fairness, bias, and trust in medical imaging. I'll start off with a few of the clinical use cases that we've been working with, where medical imaging and computer vision has shown a lot of promise, and then pivot to some of the challenges that we face in getting these algorithms to work when we sort of deploy them in the wild, so to speak. So first example is COVID. So we saw a huge explosion of the use of computer vision and AI and machine learning during the early stages of actually throughout the COVID pandemic, with what seemed like hundreds of papers being published almost every day. Besides being used for diagnosis and prognosis, we saw that these algorithms could be used to manage and triage emergency rooms, hospital planning, and so on. So in this work, some of the one of the applications that people had been looking at was actually disparities research. So what they showed in this publication was that non-white patients hospitalized in early stages of the COVID, especially in the Boston area, were more likely to have much higher severity of disease than equivalent white patients. So one of the things that we were looking at to seeing is if we can train an algorithm, again, to look at severity of chest X-ray findings. And then what we came up with is a system to classify our chest X-rays, and we've been running this on every single chest X-ray in our hospital system, actually since May of 2020, and it's still being run. And essentially the output of the algorithm is a score that looks at the severity. And looking at that, for instance, we can see that we can see the differences between severity. This is again from early 2020, the April, May, June timeframe. We saw that the severity is much more severe with the non-white patients compared to a matched control of white patients. We were able to again monitor the epidemic as the pandemic as it came through the Boston area in 2020 April. And then we've been subsequently able to look at a variety of things, again, in terms of monitoring of the pandemic. So we saw the number of cases come and go as we saw the various waves, the original and the Delta and the various waves. We saw the severity of the disease change over time as we saw vaccines come on board and so on. So again, it seemed like a great application of using a computer vision to do a variety of things, including helping with looking at disparities research, looking at trying to understand why it was that the outcomes varied in different subpopulations and so on. Switching gears, the next clinical use case that I was going to touch on is a disease that we've been working on for more than a decade now. This is retinopathy of prematurity. It's a disease affecting low birth weight babies, and it's the leading cause of preventable childhood blindness worldwide. Given that there's a wide range of treatment options and a severe shortage of pediatric ophthalmologists, especially in low and middle income countries, there's a great potential for AI-based approaches to be used in screening and triage, looking at disease progression, treatment response, and so on. The one way in which, again, we're looking at it is for the timely and accurate screening. The way we diagnose this disease is actually looking at photos of the back of the eye. As you go from left to right, you can see that the vessels in the back of the eye are more and more tortuous or wavy. They are dilated, meaning they are thicker. And so it's a relatively straightforward problem for computer vision to try to solve. People have been trying to solve it for many years, but once we start getting to more CNN type approaches, we were able to get much higher performance of this diagnosis of this disease. And again, we were able to show that we have pretty good algorithm for doing so. One of the reasons we were able to do this is we had access to almost a 10-year cohort of babies that had been screened across the US and across the globe. And we also had access to multiple expert clinicians nationally and internationally who were able to provide a sort of diagnosis of the disease. We've been talking a lot about questions of skin tone and fairness. We have the same issues in fundus photographs. The pigmentation of these photographs can be quite different in different populations. And so again, it's quite important that we evaluate the performance of these algorithms in different populations. The diagnosis of ROP is quite subjective. And we see this we've done multiple rater studies, and we see that there's a substantial amount of inter-rater variability, more bias than noise, but we have a lot of inter-rater variability as well. The exams are quite stressful, and so if you can minimize that, that would be a great help. It's especially challenging in many parts of the world where, again, you can look at the number of ophthalmologists per population. The picture is much worse if you look at number of pediatric ophthalmologists. But again, having this algorithm might be quite useful, especially in low and middle income countries. The other thing that we've shown is that having sort of quantitative, objective measures of disease severity can be quite useful and can really help in things like assessing quality and safety, improving concordance, improving outcomes, and so on. The final use case I'm going to touch on is cervical cancer. Again, it's a leading cause of child cancer morbidity and mortality worldwide. Most cases are associated with HPV viruses. And the screening currently in many parts of the world, though not recommended, is still done by the use of visual inspection after the application of acetic acid. So we are, as part of a large NIH-funded study, what we're hoping to do is screen over 100,000 women in the next 1 to 2 years. This is a multi-stage process where people will come and get sampled, get tested for HPV first, and get extended genotyping of the most concerning kinds of HPV, and then also have a cervical cancer, cervical exam with acetic acid. If there's concern, people get treated right away. So this was work that was done a few years ago and showed great performance of the algorithm with almost perfect discrimination for cancer versus not. And so again, we've seen these multiple use cases. It's getting really easy to train our algorithms. If we have good data, good training data, we essentially take the data, we take the annotations, we take whatever today's flavor of AutoML is, we take ChatGPT, you train your algorithm, you take ChatGPT, you write out your abstract, you write your paper, your grant, and it all seems to work miraculously well, especially for many of these cases where it's a relatively straightforward classification task. The challenges, of course, are when we actually then try to go from having a publication to doing something that is literally going to work across the globe for millions of women or babies or whatever the disease is. And so soon after the original publication, as the investigators were looking to scale up the algorithm into a real life translation, they found a number of considerations in terms of how the algorithm may not necessarily work as well as originally published. So the reproducibility of the algorithm is a challenge, the validity, internal validity, device portability out of domain and in-domain performance was substantially different. So all of these led them to sort of have this publication that said, okay, think of these things before you take an algorithm that seems to work well on paper, and then before you deploy it in the real world. So some of the challenges that we've seen for all of these algorithms are listed here, and we'll go into some of these in more detail in a minute. So generalization, the algorithms are brittle and may not generalize across populations, scanners, disease presentation. So, shockingly to us, the model predictions were not repeatable. So if you take this a test retest sample, meaning you take the same person, you image them twice, you hope that the algorithm will give you the same answer, but it was not the case. Many diseases lie on a spectrum, but very often we treat it as a binary classification. And the intermediate zone the algorithm performance in that gray zone can be a challenge. Very often we don't calibrate our models well. There can be a lot of silent failures, standard problems with explainability, overfitting, and especially bias. So we'll touch upon these in a second. So the first problem I want to touch on is the notion of brittleness. Very often deep learning models don't generalize well. This was a study from radiology showing very few studies actually looked at it. And there's a variety of reasons why we might see this issue. So if you look at the fundus photographs, for instance, these are images of the back of the eye. You can look at the color and the pigmentation, and you can see that different populations and ethnicities can look quite different. Different camera systems might have both sort of obvious and subtle differences. You can have different field of view, different illumination characteristics. Even the quality of the images can be quite different. The reconstruction, how you go from raw sensor data to an image can be quite different. different protocols. We were expecting to see images at the back of the eye. Suddenly we saw sort of zoomed out versions of the eye, and that it, in some ways it looked like the back of the eye because it had these sort of circular things. And so the algorithm was getting a little bit fooled. We can have poor quality images, and the biology can be different. So again, very few algorithms, even those that have been FDA approved, are actually validated externally. This was a great publication, a living document that looked at both multi-site data sets as well as prospective data sets. And it's surprisingly uncommon to have multi-site prospective data sets, even in FDA approved algorithms. The portability challenge is a big one, as I mentioned earlier. For the cervical cancer case, when you train and test on the same data set, the algorithm performance is excellent. But when you train on a data set and test on an external data set, the performance is not much better than chance. This is obviously something that's really well known in this community, but it is quite a bit of the shock to the clinicians and the epidemiologists who are running the study, and sort of substantially different performance surprised and shocked them. So many different ways that we might address this, including data diversity, multi-institutional databases, good ways that we can measure out of distribution, especially measures that translate to a performance difference, we're seeing a lot more in self-supervision and other approaches, adversarial training and other things that might potentially improve the generalization, federated learning. So lots of different ways in which we are looking at this. This is some work that we did with conformal predictions and trying to predict what the accuracy might be in a new distribution, for instance. If nothing else, if you had a good way of measuring distribution differences that translate to the performance in the new domain, that would be helpful, especially as we start to think about pathways to taking something that's been validated in one domain and then testing it in a different domain. In terms of evaluating it, I think creating these multi-distribution, multi-scanner, multi-institution data sets are important, and thinking of different ways in which we might have out-of-distribution input. So, and sort of testing for that. The second problem that we ran into was this notion of repeatability. If you have two images of the same woman, you really hope that you get the same answer. They look very similar on the left. In one case, it said it was abnormal, and the second case, it said it was pre-cancer. And you can sort of see this as a flip-flop of the prediction of the algorithm's output. We see the same thing we had 4 different use cases, from cervical cancer, knee X-rays, and a variety of things. In every case, we saw surprisingly poor performance in terms of test-retest repeatability. Here are some examples, again, from a couple of different domains. What we did find is using things like multicolor approaches or ensembles or different ways of getting sort of better calibrated models can actually help reduce this test-retest differences. So the problem, of course, is in many cases, especially when you're subjecting the patients to things like X-rays, it's really hard to get test-retest variability, test-retest data sets. So to the extent that we can do that, it'll be great if it's ethically possible. If not, we have to think of artificial ways of augmenting these data sets. Obviously, we do the usual augmentations like flipping and rotation and things like that. But again, testing how well the algorithms work in these sort of realistic things would be great. The third problem I want to touch upon is that real life is a spectrum, and very often we treat it as a binary. And the top is from ROP, the bottom is from COVID, but essentially we give the same set of images to a group of clinicians. So experts are on the top to bottom. So each row is an expert, each column is an image, and the color is basically what they rated the image as. And you can see this whole range of whole amount of variability. Some people use a lot of red, as you can see in the top bottom row of the top figure. Some people are very reluctant to use red, and the same sort of thing happens across domains. So, and this you'll see very often in sort of if you look at an ROC curve and look at clinicians' performance along that curve, some are more sensitive and some are more specific. So the data is biased in that sense. So this is again data from a public data set with multiple raters. If you plotted the gradings of these images by these multiple raters, you can see that people lie on, these things are on one or the other side of the diagram. A way in which we've approached this is, instead of saying, is it mild or moderate or severe, we given a pair of images which is more severe, and that way we can create a nice quantitative severity scale where people are much more consistent. So if you ask them if it's mild or moderate, you see a lot of variability, but if you say, is this image worse or this image better, we see much more consistent. And we can use that to create sort of more, instead of, again, having binary classifiers, we can have a more smooth scaled output. And that allows us to do things like looking at disease progression within patients, looking at disease regression and response to therapy and so on. And we can use it for reducing the number of exams needed to be screened, for instance. We also use this kind of approach to come up with a quantitative measure of severity to look at population level and hospital level differences. So looking at a system in South India at the Arvind Eye Hospital system, we were able to see marked differences in the performance of different NICUs because we were able to sort of quantitatively look at disease severity. And we found, and then 2 years later, we went back and sort of they fixed the system and we were able to see that improvement. So thinking about, instead of having binary, having a more nuanced disease severity can be helpful. Another challenge that we run up against is that many models can fail silently. We often see publications that just report average performance, but they don't discuss the long tails that we see, especially of the failure cases. So how do we essentially come up with ways of identifying, without necessarily having ground truth, the cases where the model is likely to be incorrect? So again, we also see that many of these models tend to be not calibrated very well. And how do we improve the calibration? So things, again, Monte Carlo type approaches can really help come up with measures of uncertainty. These measures of uncertainty might actually, again, if calibrated well, be able to help you identify the cases where the model is likely to be wrong. What really bothers clinicians is if a model is confidently wrong. And this is something that when we think about translating our models into the clinical domain, we have to be very careful about is in helping building trust in these models, is making sure that the models have some sense of uncertainty and can say when they learn to say, I don't know, as opposed to saying I'm confidently wrong. So showing that we can improve our calibration by some of these approaches as well. So we don't see enough of model calibration in the publications in the medical imaging literature, really need to understand that. We need to sort of tabulate the silent failures and confidently wrong failures and try to understand what some of those defining characteristics might be. Overfitting is a huge problem in the medical imaging literature. There's many different things in which leakage occurs between the data sets, between the training and test data sets. And sort of, we've discussed some of these in the literature. If you look at the COVID literature, for instance, it was really bad. We saw these huge Frankenstein data sets that were assembled from pediatric and adult chest x-rays, and sort of all kinds of poor practices happened, which again led to a lack of trust by the clinicians in our AI models. A lot of shortcut learning happens again here. So in this particular case, for instance, they were showing that the models were actually picking up on things like markers that had, like in the top right in some of these images, you can see these markers that said if it was a portable X-ray or a not a portable X-ray, which was associated with the disease severity. So trying to figure out how to mitigate some of that is really important. Again, basic statistical rigor in terms of having really good hygiene in separating the tests and data sets, testing externally, giving it to somebody else to test it. All of those things can really sort of reduce the overfitting that we see very often. Black box nature, people are very, again, for medicine, very interested in having more explainable models. Many often the deep learning models are not explainable. Many of these post hoc methods that are often used for things like saliency maps are used in the literature, but again, people have concerns about that approach. So there's been a number of publications about the sort of some of these post hoc approaches to explaining black box models. we've looked at sort of one way to address that might be developing inherently models that are a little more explainable. So for instance, instead of just saying if this patient has this disease or not, at least try to say, here's a region where the model thinks the disease might be, or having a segmentation map. That way the clinician can very quickly assess to see if it is if it's even within the frame of reference that they need to be thinking about, or if it's looking at markers or looking at something external. So thinking about how to build explainable models is again quite useful. One thing we've looked at is ways of evaluating this. So saliency maps and other things are used quite often. Are they good localizers, meaning do they identify the areas where the disease happens? And so quantitatively assessing that is useful. One of the concerns that had been raised previously is if you sort of randomize the different layers and the map comes up with the same answer, that's not a good thing. So does the map vary with randomization? Or they all that they're doing is essentially a contrast, looking at the contrast in the image or edge detection or something like that. Are they repeatable? Are they reproducible? So a variety of different ways and thinking about explainable options. We've heard a lot about fairness and bias in medical imaging. This was a work by a large group of investigators trying to sort of come up with a list of places where bias can creep in and how to assess that. So looking at during the data collection process part of the pipeline, looking at model development, evaluation, deployment, and so on. So as we've heard today, very easy for bias to somehow creep into our models. In medical imaging and medicine itself, it's not good if the models are biased, obviously. And there have been a number of algorithms that showed looking at existing deployed algorithms in the medicine that happen to be looking at proxies that are not good proxies of disease severity or looking at other things and being quite biased. In terms of dermatology, for instance, they've shown that a lot of the data sets especially the public data sets, have been not diverse in terms of skin tone, and some of these algorithms have been shown to not work. We've seen a lot of issues during COVID around pulse ox, so where the pulse oximeters didn't work on darker skin people. If you haven't seen this is shocking. This was a recent work from a large group of international investigators showing that AI models are able to, based on just a chest x-ray, and especially a low resolution sort of chest x-ray, able to predict self-reported race from chest x-rays. It's sort of mind-boggling as to how that happens. And similarly, we've even trying to get away from that. We see that there's even if you don't use the fundus images, but you use segmentation maps, even those things can be biased. So really important to think about training your models from a diverse population. Unfortunately, it's been shown that most of the publications are restricted to data coming from essentially in the US, just the coast, and hardly any representation from the rest of the country. Fairness is really challenging in medical imaging again, especially because there can be an association between different characteristics. So for instance, we're looking at breast density and size and race and the outcome of interest are all sort of intertwined, and trying to figure out what is a fair model can be quite challenging. So trying to create data sets that are this is a large NIH-funded effort, but again, creating data sets that are diverse is important. Looking at model performance in subpopulations, looking to see if we have shortcut functioning and so on. We've seen, again, a lot of recent work showing that AI has superhuman capabilities and that it can do things humans cannot do. We've seen this in fundus photographs where we can predict if you're at risk for Alzheimer's, for Parkinson's, for cardiovascular issues. It can look at your fundus photos again, say what predicting sex. It can look in all kinds of things that the humans cannot do. So we know that the models have superhuman performance. We know that they are at risk for bias. So it really highlights the need for vigilance and a good framework in which we can assess the performance of these models as we start to deploy them. So sort of some things that we've been thinking about in terms of model deployment is looking at things like, here's our checklist, but what does the reproducibility performance in external data sets? Do you have good measures that will predict what your performance in a different data set is without the need necessarily for ground truth in that data set, for instance? What is the test retest performance of the model? What sort of out of distribution detectors do you have? Is the model well calibrated? How often does the model make grave errors? Meaning, if you have a disease severity and the patient is normal and the model says severe, that's a grave error relative to being off by one class, for instance, from mild to moderate. If there's a misclassification, that's not as bad. Is a model explainable? Does it need to be explainable? Is a model biased? Is it fair? How do we even define what fairness means in this context? So more questions necessarily than answers, but these are the sort of things that we think about as we are looking at the applications of these models in medical imaging. So with that, thank you.
Yeah. Come up to the microphone.
Yeah, hi. Thanks very much for the talk. When you look at the state of the art in like out of distribution detection or uncertainty estimation, a lot of it is still being evaluated on very simple data sets like CIFAR or ImageNet or whatever. What steps can we take to kind of reduce the gap between, okay, it works on CIFAR and then, okay, we could actually use this in like a medical context where I guess the notion of out of distribution detection is a lot more subtle.
It's a really, really good question. And we've tried to come up with more realistic data sets, but I think that you've identified a huge gap, which is the methods that seem to work on these more computer vision data sets really don't translate that well to medical imaging data sets. So there have been efforts to create large sort of multi-site medical imaging data sets, which are much more representative of the more subtle differences that we see, right? I mean, in a sort of real world data set, you might see things like the area of interest occupies a huge part of the image. In medical imaging data sets, you're looking for very subtle things, a tiny nodule that occupies maybe 1% of the image. And these measures of out of distribution sort of really fall flat when you translate to more realistic cases. So I think really good question. Don't know we have a great answer. I think trying to build these multi-institutional data sets, trying to use sort of physics-based models to simulate some of, we understand the acquisition of images relatively well for some modalities. So we can potentially simulate what that image might look like if acquired under slightly different attributes. So sort of doing that kind of work might be helpful.
Thank you.
Any other questions, comments?
I have additional questions. Great talk. But could you please share with us your insight about you show us some repeatability issues given similar input, and then from your experiences, so what will be the primary reason for this? Is it because algorithm, data scarcity, scanning noise, lack of augmentations, or label noise? Or what's your insight?
So in this particular case, it was not label noise. It was essentially the same woman that has the same true label. One of the issues we've seen is this: when you train a binary model and you sort of push the decision into either 1 or 0s, and the disease is somewhere in the middle, it does a lot of this flip-flopping. So if you think about, again, if you have something that's on a scale and if you have clear positives and clear negatives, it does a great job. But in the middle, it'll sort of switch between going from one, if it's close to the decision boundary and there's a very small change in the image, it can sort of flip-flop between one side of the decision boundary to the other side of the decision boundary.
I see.
If there are no more comments or questions, let's thank Jayashree again. Thank you, Stay, for this very insightful talk coming from a very deep domain expertise to now applying it to AI or applying AI techniques. I think certainly it's been very insightful to listen to your talk. Thank you.
Thank you so much for having me. And it's been a great session so far. Thank you.
We will now break for lunch and reconvene at
1:30.
1:30 local time. See you all.
Thank you.
Can everyone hear me? Hello?
Yes, yes, we can hear you online.
Okay. Let's start. I'm the Linzhi Huang of the author of this paper. I will introduce the paper of gradient attention balance network, mitigating face recognition racial bias via gradient attention. At first, with the development of deep learning, the accuracy of the face recognition algorithm has reached a high level. However, with the emergence of more and more applications based on face recognition.
Lindsay, hold on. So we cannot really hear you yet. We are resolving your technical issues. Can you speak again?
Yes, Guangchuan, we can hear you. We can hear Linzhi online as well.
Yeah, the Lindsay's voice is not there on site.
Can everyone see the PPT?
Yes, we can hear you right now. Can you restart from the beginning?
Okay.
Sorry for that.
Let's start. I will introduce the paper of gradient attention balance network, mitigating face recognition racial bias via gradient attention. I will introduce the background of this paper. With the development of deep learning, the accuracy of the face recognition algorithm has reached a high level. However, with the emergence of more and more applications based on face recognition, its potential racial discrimination is attracting people's attention. For example, Amazon's recognition tool incorrectly matched the photos of 28 US congressmen with the photos of criminals. This unfair prediction leads to unfair treatment of different population groups. Therefore, it is very important to solve the problem of racial bias in the face recognition system. Some studies propose new and more balanced data sets, such as RFW. However, other studies have proved that the racial bias of the models trained with such balanced data sets cannot eliminate it completely, as shown in this table. And therefore, we also need to mitigate this bias through algorithms. Some recent studies have used the grid cam for visualization and found that face recognition networks attend to different facial regions depending on the race, as shown in this figure. For darker-skinned people, the face recognition network will pay more attention to a local region, such as the region near the nose of Africans. For Caucasians, the face recognition network focuses on a larger region. Inspired by Wang and so on, we designed an image level map called the gradient attention map, as shown in the figure C. GridCam calculates the map based on the last convolution layer of the network and prefers to highlight the decision-making region. However, GAM can locate sensitive region more accurately. We used GAM for visualization and found a similar phenomenon. The sensitive region of darker-skinned people is smaller than that of Caucasians, and the sensitive region of darker-skinned people tends to be a local region. A brief comparison between the baseline and our method is shown in the figure. Comparing B and C in figure, we can see that our method enables the face recognition network to pay more consistent attention to different races. The successfully enables the face recognition network to allocate attention to a larger facial region, as shown in D. Our method not only enhances the overall accuracy, but also greatly mitigates racial bias. The formula of SDR and SSTD is on the PPT. And the previous racial DBS algorithms based on adversarial training mainly have two ways. First, the method of feature alignment. Second, the method of feature disentangle, as shown in the figure. Both of these methods delete racial features, resulting in the accuracy of face recognition lower than baseline. However, our method is to align the gradient attention map of different races through adversarial training. These are the contributions of our paper. First, we propose a new face recognition DBS algorithm called the Gradient Attention Balance Network, GABN. And to our best knowledge, this is the first work to mitigate the racial bias of face recognition by improving the consistency of gradient attention map of different races through adversarial learning, which provides a new perspective to improve face recognition fairness. Unlike previous work based on feature disentangle or feature alignment, our method is based on GAM alignment. Face recognition network pay more attention to local regions or darker-skinned people to further reduce the performance gap between darker-skinned people and Caucasians. We use GAM guided sensitive facial region erasure to force the attention of the network to be allocated to a large facial region. This method reduces the overfit of darker-skinned people and improves the fairness of the network. Third, extensive experiments on the BUPT global face, BUPT balanced face, and the RFW datasets show that our gradient attention balance network shows more balanced performance. We propose a new DBS algorithm based on gradient attention, which is called the GABN. GAM is the image level map. Each value of the GAM accurately represents the sensitivity of network ID to the corresponding pixels in the face image, as shown in steps 1 and step 2 in the figure. Forward propagation is used to obtain the probability value PI of each class, then calculate the relative magnitude TGAM of the max probability value Pmax predicted by network ID and the probability value PI of other classes. The formula is as shown in PPT. Where N represents the number of identity categories. And because any perturbation will affect PI and Pmax, we use TGAM as the objective function for backward propagation to obtain the gradient attention map. And we also use two methods to improve the fairness of the model. One, first is GAM consistent training, which we called GAM-CT. As shown in figure, we use the face recognition network ID as a generator to generate the GAM of each image. In addition, we train a GAM risk classification network, network GAM-CT, and use it as a discriminator. Then we improve the consistency of GAM of different races through adversarial learning. Second, GAM guided sensitive face region erasure. We try to use a special method to expand the sensitive region of the network on darker skinned people and reduce the gap between these regions. Under the guidance of GAM, we erase the top N sensitive regions in the image by generating masks, forcing the network to allocate attention to a larger region. And other details is as shown in this picture. The paper explains the calculation process of several loss functions we use. Here we use pictures and other ways to further explain so that readers can understand it more easily. The calculation process of LO final is shown in figure. First, the normalized features and weights are imported into the loss function of arc face to get the logit. Then we reweighting. And then we reweighting logit to obtain rescale logit. We use softmax function. Softmax function to get the probability variance VPI of each class. After that, get the max probability variance Pmax from it, which is called confidence. Calculate the number of samples which with Pmax less than the threshold T confidence in the current batch N confidence. Get confidence balance loss function is as shown in the step 5 and the step 6. And where N batch represents the number of samples in current batch, here arrow count is take as the penalty coefficient. In the step 7, network ID backward propagation to obtain gradient attention map. Then we use network GAM-CT as a discriminator. It provides an adversarial loss, LADV. We use LADV and LO count as the penalty coefficient into LOID to get the LO final. Consistent with the previous work, we train a ResNet 34 model on BOPT global phase, use the loss function of arc phase, and then report the results on RFW. As shown in table 1, compared with the SOTA results, we also use the same methods to conduct experiments on BOPT balance, as shown in table 2. Compared with the SOTA results, GAM-BN reduced the STT to 0.56. In addition, compared with step phase, which is also based on adversarial learning, our method not only obtains lower STD and SER, but also improves the overall accuracy of the model. And to investigate the effect of our method, we conduct a lot of evaluation studies. We use the framework of Arcbase 34, then trend balance, then trend baseline and GABN on QPT balanced phase, and test on RFW dataset. We can get better results than baseline when we use GMSCT or GMSFRE. This shows that these components can effectively improve the fairness of the model. When we use these models at the same time, we can get the best performance. In addition, to prove that our method improves the consistency of GAM of different races, we visualize GAM. We use the GABN in the RFW dataset and calculate the average GAM of 4 races, as shown in left figure. In the average GAM of the 4 races obtained by baseline, the sensitive region of Caucasians is large and that of darker skinned people is small. However, the sensitive region of GABN has a higher consistency and a larger sensitive region. This shows that our GABN has successfully reduced the attention gap between different races. In addition, we also visualize the GM of random erasure and the GMSFRE of single image, as shown in right figure. A random eraser can expand sensitive region, but the effect is very small. GMSFRE can expand the region to the whole face. And finally, in this paper, we propose a DBS network GABN based on gradient attention and adversarial learning to reduce racial bias. GABN improves the consistency of gradient attention map of different races through adversarial learning. In addition, GABN also uses GAM-guided sensitive region erasure to expand the sensitive region of darker skinned people, further reducing the performance gap between darker skinned people and the Caucasians. And that's all. Thank you.
Any question from the on-site audience? Lindsay, thanks for your talk. I have a question because in your talk you mentioned about you want to enforce similarity of the attention maps, right? And there are many attention map generating methods, for example, like GradCam or GradCam++. And I want to know, could you please comment on how sensitive your method is with respect to different attention map generating methods? Thanks.
For example, GradCam, it is worth noting that GradCam is based on the last convolution layer of the network, which tends to highlight the decision-making region. And our GAM generates a map at the image level to locate sensitive region. The position accuracy of GAM will be higher, but the attention distribution will be sparse. We have conducted experiments using GradCam and the results of our methods. The performance is slightly lower than using GAM. And
I see. So, is there any other question? If not, let's thank the speaker again. And next on our schedule, we have the paper presentation from the paper entitled MMRNet, Improving Reliability for Multimodal Object Detection and Segmentation for Bin Picking via Multimodal Redundance.
Right. Hello, my name is Yu Hao Chen, and I'm from University of Waterloo in Canada. And welcome to my talk on MMRNet, improving reliability for multimodal object detection and segmentation for bin picking via multimodal redundancy. This is a joint work done by the Vision and Image Processing Lab, and as well as the Karlsruhe Institute of Technology. So first, robotic bin picking is a very important problem in upgrading the industry into industrial 4.0. And then with modern computer vision technologies such as object detection and segmentation, the AI technology equipped robots will be very fast and very cost effective when in terms of speeding up the various tasks in the industry. But it also arises, some of the risk also arise during the process of upgrading systems into Industrial 4.0, which can cause expensive damages during abnormal events such as sensor failures. So reliability is one of the key things that prevent the adaptation or slow down the adaptation of AI, applying AI into robotic deployment. So existing literature has states that with more modality, you often get more performance, but does that mean that more modality also is more reliable or it's more risky? So we did a simple experiment on this. So basically we apply object detection and segmentation, we're taking work from one of the latest robot bin picking object grasping network, which is called UAIS, and then apply it into one of the latest robot bin picking data set called MetaGrassNet. And then we got 82.8% bounding box prediction, as well as 78.8 mass prediction. But then when we turn off one of the modality, such as we turn off the RGB, the model just doesn't work. It produces zero result. But when we turn off depths, there's a significant performance drop, which is around 7% for the bounding box prediction, as well as 10% for the mask prediction. So how can we solve that issue? And then here's the two criteria that we really want when it comes into network architecture as design when to address this issue. So the first is we want to design a network so that when one of the modality failed, the rest of the network can still carry on to execute the task, right? And the second is that when when more modality turned on, the network is supposed to work better. So here in this paper, we propose multi-model redundancy framework in order to improve the reliability of object detection and segmentation in robotic bin picking. So the core concept of multimodal redundancy is that we want to make sure that the modalities work both independently as well as collaboratively. So here, so one of the issues when it comes to designing the network is that oftentimes the features are entangled, and then it becomes very difficult when you want to select certain features from certain modalities. So one thing that we proposed here is to use a modalities feature selection module, which is a very simple soft gating mechanism. But in here, note that here we, instead of predicting using a sigmoid function, as appears in most of the gating mechanism, that we use softmax to ensure that all the modality weights sum to 1. And Another thing I want to point out is that instead of merging or a convolution at the end, here we actually use a concatenation in order to feed this into a feature pyramid network that is oftentimes used in a two-stage object detection network to allow better contextual information. So I'm going to talk a bit more in this slide. So here you can see that this G represents our previous gate fusion module. And then the goal for this multi-scale integration of information is that we want to add a bit more contextual information to when merging the features together. So in the particular, for a specific feature at a specific scale, we want it to get access to the contextual information from the feature from different modality, from different scale. So by directly feed into the concatenated feature into a feature proposal, feature pyramid network or other network architecture, we can allow that kind of contextual information exchange. So with this, altogether, we put into a standard mask-RCN architecture and then apply on the MetaGraphNet data set. And then we evaluate on the real data split and then also on the novel object split. You can see that this this is what we the name of this feature fusion module is called multi-scale softmax gates feature fusion, called MSG feature fusion. And then you can see that it provides a really competitive result compared to previous fusion method proposed in the UOAS network. And then but what's more important about this is that it enables us to select features in the middle of the network to control which features or latent representation to select during the training process, so that we can actually apply our next step, which is we call dynamic ensemble learning, to train the network dynamically to ensure that the networks are trained independently as well as collaboratively. So what this is actually a very simple training strategy, which we randomly select one or both modality to train by giving a random seed, and then that random seed will determine if we want to train RGB depths or RGB plus depths. So finally, those are the results from the dynamic ensemble learning. So if we take a look at the bottom of the slide, we can see that instead of when we turn RGB off, instead of outputting no object at all or having zero performance, it becomes much reliable. Although there's about some degree of performance drop, it's okay, because when both modality work together, they perform better. And then when we turn off the depths, the performance drop is about very subtle compared to not using this dynamic ensemble learning, which has about 6% performance drop. And then if you take a look at the top images, the left shows that if we don't do anything, the network focus more on the RGB side. So this is a weight visualized. We take the maximum operation of the weight visualized from the gating mechanism. And then on the right, if we apply dynamics ensemble learning and then we turn off RGB, the network instantly shift its focus to look at the depths. And then when we turn off the depths, the network instantly look at the RGB. So there's another problem in terms of reliability of the of this multimodal system or in general. So one of the issues is that when applying models trained on simulation to real data, there's often overconfidence in prediction. So but here, since we have disentangled output from modality, we can actually use this as a measurement to measure the alignment of the modality. Because in real world, all the modality are describing same object. So technically, all the output should be the same. And the model should converge on the output. But then if the model is not very confident, then the alignment between the output from different modality, they may diverge. So we take this as an observation and go ahead and design this alignment measure and then use it as our reliability measure for the system. So the concept for this alignment measure is very simple. So what we do is basically calculate the intersection of union between either the mask or between the detection bounding box. And then we calculate per model multi-consistent, and then we call it multi-model consistence score. And then we calculate per model model consistence score. So this in this second equation, we are calculating the consistence score of the output with respect to one specific modality. And then the MC score for the entire system is calculated based on taking the average of all the modality consistence score. So here are some visual results. As you can, so the left two images are from the training data set, and then the right four images are from the testing novel object testing data set. So you can see that it does pretty well, a good job on the training data set. Well, please note that at the bottom left, that it actually predicts two objects instead of one object. So that's the reason that MC score is a bit lower in this case. But like on the right side, you can see when I try to predict new objects, the peers are quite good. Like it aligns with the confidence score. But then when it comes to difficult object in the testing novel testing data set for object that it hasn't seen, especially in the bottom right, it's paper in a plastic bag. It's just too difficult for the network to detect because there's a lot of reflection on the surface, and then the depth camera is not right. The MC score produce a much lower score value than the network confidence. And then what's more important, I want to point out is that this is you can apply it directly to the output. You don't have to train a model to calibrate this confidence, like other work, to calibrate confidence score. So this is, you can directly, with our multi-model consistent redundancy framework, you can directly calculate MC score without training. So in summary, we propose a multi-model redundancy framework to address the reliability issue for object detection and segmentation in robot bin picking. We proposed a multi-scale soft gate feature fusion module to disentangle features that allows independent training of modality backbones. And we propose a dynamic ensemble learning strategy to train multi-model system to work both independently and collaboratively. And finally, we propose a multi-model consistency score to measure the output reliability of multimodal systems. And those are the references. Thank you for watching. Please let me know if you have any questions.
Any question from the audience?
In general question, does your confidence level that you saw directly indicate that it's going to result in a better detection, or the vice versa? Meaning, how do I use your, or when do I use the multimodal system based on the confidence?
Based on the confidence. Sorry.
If you were showing, if you could go back to your.
Yes.
So the MC score,
yeah,
is your new confidence measure, right?
Yes, yes.
So when I see that low, that means I should not use multimodal data. Is that the interpretation?
So basically the interpretation is that when you see low score, it means that the network is actually not confident. You shouldn't trust the result because the output doesn't really align. And then maybe you should call a human into the loop to check what's going on in the object. Because sometimes, like in industrial setting, that object may come with plastic bag setting, right? Yeah.
Does it mean if I were to use only one channel, you're using depth and RGB?
Yes, yeah.
Maybe RGB itself is good enough. Depth is causing the, or vice versa.
Yeah, and that's something that we will look into. It definitely it may cause some of the issue, but that's the case, especially for some of the objects that is really difficult with, for example, the transparent object. Depths always have problem with the transparent object, so you should rely more on the RGB. But this kind of framework is a setup so that maybe in the future you can add different cameras, such as like hyperspectral camera or like heat camera, that to maybe you can use different additional modalities to measure the confidence. But definitely for those simple objects, this is a very good measurement to say that, okay, this result is definitely trustworthy. And then for some of the difficult objects, then you might need to develop a better algorithms to ensure that it is reliable. Okay.
If there's any no further question, let's thank the speaker again. Thank you. Oh, yes. And please unshare the screen.
Yeah.
So that.
Yeah.
Sign off, just unshare.
Yeah, this is mine.
Oh, okay, they're mixing up too. And I have my charger there as well.
The next two speakers are now.
Subho, you can hear us, right?
I can hear you. Let me know when I can share my screen and test things out.
Can you hear us?
Yes, I can hear you. Can you hear me?
We can't hear you, so I guess
let me see. I'm checking my audio settings.
yeah, please go ahead.
Still nothing?
Oh yeah, we can hear you now.
Okay, thanks.
Give me a minute.
I just shared my screen. Please let me know if you can see it, and
Yes,
I can
we can
start
see
whenever
it.
you're ready. Okay.
Yeah, so I guess let me introduce our invited speaker, Dr. Shubha Majumdar. As you've been seeing, we have been having the day with academic industry. That's the pattern that we have been going through with our keynote speakers. So this is an industry speaker. So I guess the previous one we had was before lunch was an academic keynote speaker. So Subho Majumdar is a senior scientist in the security expert analytics and learning team in Splunk. Before joining Splunk, he was with AT&T Data Science and AI Research, or the AT&T Bell Labs, what is known as. And he focuses on trustworthy machine learning in the wide, not only proposing novel solutions, but also implementing them in real world. Trying to illustrate that, he has been working with UNICEF Office of Innovation, Chicago Department of Public Health, and he co-founded the Trustworthy ML Initiative as an effort to build a community and facilitating dialogue among the researchers and practitioners in the field. So please join me in welcoming Shubho Mazumdar.
Thanks for the introduction, Professor Ratha, and thank you for the invitation as well. I'm really glad to be here giving this talk. I actually left Splunk a few months ago, joined Twitch, but again in between jobs right now. So my current affiliation is AI Risk and Vulnerability Alliance, which I'm going to talk about later on in this speech. But the topic that I am going to discuss today is very much drawn from my own journey as a responsible ML, responsible AI practitioner, and what I have benefited from and kind of try to preach in the community is to have a security mindset to operational responsible AI. So that's what I'm going to talk about today based on my own past experience in this field. So a little bit about myself. I am a statistician by training, graduated with my PhD back in 2017, but then moved into machine learning, data science, AI, whatever we can call it, in the course of my own work. I've been doing responsible AI in the wild since 2019, since my time in the AT&T labs. But after I joined Splunk like a year and a half ago, there was kind of a paradigm shift in my own thoughts on responsible AI, because that's the first time I came into contact with the cybersecurity community. I was there in the security machine learning team of Splunk. I saw that how things are done in the cybersecurity side, how software risk management is done. And then I realized that responsible AI is operationalization part of that specifically is nothing but AI risk management, and we can learn a lot of things and concepts and best practices, technical best practices from the field of cybersecurity. So besides my own work, quote unquote work, I've also done a number of extracurricular community activities. I've co-founded these 3 things that you can see, and the last 2 things specifically are something that I'm going to focus on, and a lot of the learnings are there in the book I've co-written as well, which is released earlier this year. So these are the things, the work with Bias Buccaneers, AI vulnerability database. These are the things I'm going to talk about today, which again are articulate some ways of bringing in the security mindset in the field of responsible AI. So this talk is going to have 4 components. Firstly, I am going to discuss what is the security mindset and why does it matter in responsible AI, and then move on to examples of that, specifically red teaming and bug bounties, which are essentially crowdsourced threat hunting and mitigation in AI systems. Next, I'll talk about AI vulnerabilities, which are essentially ways to characterize failure modes of AI systems, and also technical best practices for AI risk management, and then how all of this can come together to operationalize responsible AI at scale. I'll finish with that. So what the hell is a security mindset? Well, this is a famous quote by Bruce Schneier, who says that security mindset is essentially the constant stream of thought that tries to find faults or tries to quote unquote break any system that you operate in the real life. This can be like a store. And he says that a security professional would instantly think of how can they bypass some of the security guardrails of a real life physical store to shoplift. They can't use a computer without wondering how to break a certain software system. They can't vote without trying to figure out how to vote twice, things like that. So essentially, what a security mindset is having intention about finding issues and flaws in a system that you interact with. and also having rigor in finding those flaws and figuring out frameworks to mitigate those flaws. So that's what I'm summarizing here. When it comes to software systems, what a security mindset would look like, as I mentioned right now, is essentially proactively looking for issues. They could be edge cases, they could be silent failure modes, like fairness related failure modes or robustness issues. They could be intentional adversarial exploits. So essentially proactively trying to figure out what could be the ways code breaks, and also trying to figure out tests to operationalize those. Not only that, we would want to build these kind of practices into the entire software development lifecycle, shift left. So essentially do a little bit of design thinking, think that how can a software system be developed to protect against these known failure modes, automate that build process as much as possible, and also simulate threats and incidents to prepare better for actual future incidents. The next two pieces are incredibly important, which is transparency and maintenance, essentially documentation and auditing of the systems that you build, and also educating your peers and other practitioners and product people on how to build better software, as well as keeping up to date with latest research and practices in the field and also in the field of security. So this is the more or less the gist of security mindset in software. For responsible AI, things are basically the same. You just change certain things, build trust into the entire AI lifecycle, and train your AI teams. That's basically security mindset for responsible AI. Everything else remains pretty much the same, proactively looking for issues, automate as much as possible, simulate potential threats, transparency and documentation, education, all of these pieces remain the same. So essentially, very much bottom-up way of building trust into the entire lifecycle of AI systems by proactively looking for flaws, as well as providing the technical teams the tools and education to mitigate those flaws. So let's look into a little bit of detail now of what security mindset would manifest as in real life. And these are the two ways that it can manifest as: red teaming and bug bounties. What these essentially are, and this is similar for software systems or AI systems. Red teaming would be pre-release internal feedback through which you can find out novel flaws and mitigate those flaws before releasing your software product into the market. And bug bounties would be post-release community feedback, where you open your product up to the developer community for them to tweak around, mess around, and find out a certain bug that would be critical for the functionality of your software or AI. And you incentivize them to find out these bugs. So essentially, if they find something that matters to you, you pay them. So that way, it's kind of a win-win situation. The company is protected against catastrophic downsides from these failures if they go unmitigated, and whoever is finding, they're also getting paid for whatever they're doing. So the advantage of having this kind of culture is threefold from the developer's side, in the sense that once you find some flaws, now it becomes the blue team's responsibility to develop mitigations for those flaws that prevents the current issue based on the flaws that are happening in the present system that has been found flaw in. And second, the next step would be to standardize mitigations to prevent future similar issues in other systems that your company develops going forward. On the red team side also, there could be another thing, which is essentially detection engineering, quote unquote, which means standardize some of those detections, some of those red teaming findings through benchmark data sets, through a set of test samples, which can be run as part of the CI/CD pipeline of model development or deployment cycle. that detects future similar issues so that alerts can be sent and mitigations can be run. Again, by that time, hopefully the mitigations have also been standardized so that they can be run along with the detections for future AI pipelines. So that's kind of the idea of these two things. But a question that we do need to tackle, that why do we need this? Aren't there so many adversarial ML papers that have novel attacks? Aren't they sufficient in covering what can go wrong with a machine learning model? Is the algorithmic fairness literature not enough to cover all failure modes? In short, no. The reason being that when a software system or when an AI system, let's move to AI by now, when an AI system gets deployed in the wild, there are lots of places where it can be attacked, where it can be gamed, where it can fail silently, which would be the APIs, which would be the different access points that external actors can access the system. They may not be as closely coupled to the machine learning model, like data poisoning or model poisoning. A good example in the computer vision context is hop, skip, jump versus this very, I'd say, less at this stream of work that has gotten much lesser attention. And a good example of that is this paper by Pinyu, who is going to speak later today, and Jaideep Borkar, who is a grad student in Northeastern right now, which is called Simple Transparent Adversarial Example. This was published 2 years ago, but still remains one of my favorite papers in adversarial ML. So why do I say that? So let's talk about hop, skip, jump for a moment. Everybody knows what it is. You basically start with a noisy version of an image whose label you want to change. You feed that noisy image into whatever system you want to game to make sure that, okay, the label of this noisy image is different than the label of the original image. And then you take gradient-based steps to iteratively try to reduce the noise while keeping the label different. The minimum requirements to implement this hop, skip, jump attack is to at least have some basic knowledge of Python, and also to have some kind of library like the Adversarial Robustness Toolbox installed to actually perform the attack. And the results of the attack is a small example. If you just do download the ImageNet weights in our ResNet50 model, and then try to feed in this image from into that model, try to get inference for that. The original image gives the label Beagle. With a large amount of L2 error, it flips the label. And then after 40 iterations of hop, skip, jump, the L2 error goes down a lot, but the label is also flipped. So this is a successful hop, skip, jump attack. And it takes quite a while to run. In my 5-year-old laptop, it took like a minute maybe to run 40 iterations. So doable. As compared to that, let's see how simple transparent adversarial examples work. What this attack does, and it's stupidly simple. You just add bits of high transparency text into the image. So basically, you just embed a word into an image. In these two images on the two right side images, I put hello world either once or repeatedly, and then just feed that image into whatever model you want to break. You just mess around with the transparency settings a little bit to figure out what works, and voila, there you go. And it literally takes nothing to pull that off. It takes zero expertise. You just need to be able to use computer and maybe the internet to find out that, okay, what free image editing tool I can use. And that's what you need to carry out this attack. And you can see from these examples that the images on the right, they basically look the same than the actual image. They were found out using like maybe 10 seconds worth of effort by me. And there you go. The purpose and result remains the same, but the way this attack is carried out is infinitely simple. So theoretically, the amount of people who are able to carry out such attacks is huge compared to something complicated like hop-skip jump or other adversarial attacks. And so when we think about game-breaking failures of publicly deployed models, in this context, image recognition, but it could be other models as well. We have all heard about, at this point, probably, that ChatGPT is susceptible to prompt injection. So realistically, the attacks that would happen would start from lay people just messing around and finding out failure modes. And this is important because red teaming would start from that, and they would be preventing that. Bug bounties would start from those kind of stupid attacks and prevent against those things. So let's now go into algorithmic bias bounties. This is a very related effort that was started by Dr. Ruman Chaudhary, who was at Twitter back in 2021 when she and her team organized the first ever algorithmic bias bounty, where they opened up the Twitter image cropping model to find out novel vectors of societal bias. And they found out that, yeah, based on the race of the people, based on the gender of the people who are present in an image, those images get cut in non-optimal, inappropriate ways. And there were many novel findings from that competition that came out. So again, crowdsourced way of finding novel attack vectors, which is fairly new in the AI field in general, and more so in the field of algorithmic bias. The next one that I'm going to delve a little deeper into was the second iteration of it, which Ruman and some of our co-organizers, the first bounty, did along with myself later last year. And this was about devising image recognition models that have the best balance between accuracy, unbiasedness, and robustness. What we have had was 15,000 images of synthetically generated faces, 12,000 train, 3,000 test, but there was a wrench in that wheel in the sense that 20% of the training images were actually noises. They were not faces. They were just random samples from ImageNet. And the task was to predict the perceived gender of a certain face, of a certain image. The participants weren't told that which image is face, which image is ImageNet. So prediction problem is predict 3 labels: perceived gender, age among 5 age buckets, and skin tone. Sorry, there's a typo here, but we need to predict skin tone, 10 classes of the Monk skin tone scale. And here the challenge is really multi-tiered because there are a lot of metrics you need to care about. You need to care about accuracy for all of these 3 labels. You need to care about bias, lack, or rather the lack of it, for all of these 3 labels. Also, you need to care about robustness to the image of noise that we are putting in to the training data set. And you also need to care about low inference time, which could be a requirement in a realistic setting. So that's why we thought that this is an interesting setting, which not only is a good competition, it also is an educational opportunity to people who are starting to get interested in this very new field. It is also an educational opportunity for traditional cybersecurity people who do these kind of things to know a little bit more about algorithmic bias, to know a little bit more about the responsible AI culture. So the scoring was fun for this challenge. This is a pretty complicated, not so complicated for this audience, but there are a lot of parts of the score that we had in the public leaderboard. Firstly, accuracy. So accuracy for the 3 classes, we have those. High accuracy, high score. But if there are more number of classes, it is difficult to classify. It is difficult to get a high accuracy. So we gave a higher multiplier to something like skin tone that has 10 classes versus age that has 4 versus gender that has 2. On the other hand, we measured unbiasedness or bias, demographic bias through disparity for each of these 3 labels. We took the maximum class accuracy, so for skin tone among the 10 classes of skin tone, which class had the maximum accuracy versus which class had the minimum accuracy, take their absolute difference. That's the disparity. And obviously, we want low disparity. So that's why 1 minus disparity. And then to account for the classes, we gave like a power multiplier, or rather power, to the disparity itself. So the idea is that if there are more classes, it's difficult to get low disparity. So we want to incentivize that component. So that's why low disparity gets a high multiplier, or high power rather. And yeah, that's what I mentioned right now as well. And finally, this is 1 minus, so that the other side gets incentivized. So that were a few moving parts of the public leaderboard score that took into account all of these things: accuracy along the 3 different classes, disparity among the 3 different classes. For the private leaderboard, 2 more multipliers. Firstly, randomness. Remember that I mentioned some of the images were from ImageNet. So not only do we need to, in a realistic setting, not only do we want to get good predictions for on the actual faces, we also want to make sure that the final model is not based on spurious information from the ImageNet samples. So they should be ideally be statistically random. And the model should be predicting statistically random labels when they predict on non-facial holdout ImageNet samples. So that's what we also wanted to ensure. And basically, if you get random predictions on ImageNet for 1 class, you get 1.1 multiplier, 2 class 1.2 multiplier, 3 classes 1.3 multiplier. That's how we did factor in randomness. And finally, efficiency. Less inference time means high multiplier. Basically, if you score in the top 10 percentile of list inference time, you get 1.2 multiplier. If you score in top 25 percentile, you get 1.1 multiplier, things like that. So that's how we kind of balanced these 4 components. But definitely, there is no single best way to do it. And obviously, as you can probably guess, there are multiple ways to get a high score as well. So bottom line is this prediction landscape is very complex, and that kind of reflects real life. In real life, if you want to deploy such a model, you have to balance multiple things, not only accuracy and biasness, but also business logic and what constraints they pose on model performance as well. So that's how we wanted to mimic that realistic situation to communicate to those who are working on these challenges that, hey, it's good to be aware of algorithmic fairness, but actually it's really difficult to apply these kind of approaches in real life, and this is why. Moving on to solutions. We got very interesting solutions. The first prize and second prize were very much different as far as methodology was concerned, but where they were similar in was here. They used a pre-processing step. Both of them used a pre-processing step to differentiate between face and non-face images. And also, both of them prettily chose a checkpoint at the actual training phase that gives random predictions and scored the highest among all checkpoints. And the first prize solution actually used a machine learning model to do the pre-processing, but the second prize solution used the raw image data, the EXIF information of an image that stays on the disk to detect the non-facial images. So this was specifically a very creative approach. But the solution-wise, they both actually performed really similarly. That was a big surprise. And that actually underlined the fact that if you think about the design process of, if you put thought into the design process of your model pipeline, then actually the modeling approaches that you choose, you can be very flexible on that component. So that was a big takeaway from this challenge, that it is important to focus on the data. And also, if you want to optimize a metric, you have to fix the underlying issue. These 2 challenges and also the third solution, all of them had a mechanism to detect faces versus non-faces, and that paid dividends. Secondly, what I mentioned earlier, it is difficult to determine what good looks like realistically. That's what we wanted people to give a flavor of through the score design. And it was instructive to see that how the participants navigated that. And finally, close attention to the appropriateness of the metric. If you notice, the second prize solution actually used an ordinal or continuous regressor to build the age and skin tone detection model. And that actually makes sense because these are not categorical labels. These are ordinal labels or even continuous labels in the form of age. Finally, I have a few minutes left, so I'll finish with AI vulnerabilities, which is kind of a new concept, but very much in the world of AI, but very much similar, in similar vein to what goes on in cybersecurity. So for that, a little bit of motivation why we need things like that. If you are listening in to the generative AI conversation, you might know of prompt injection, which essentially started in the large language model context in May last year, when a number of cybersecurity experts, they discovered that language instructions can be used to get information from language models that they are not supposed to output. And this was demonstrated in the context of GPT-3.5, I think. After a few months after that, GPT-4 released in March this year. And less than 2 weeks later, the same problem was discovered for GPT-4 as well. And this was only discovered because the concept of prompt injection goes beyond AI security to cybersecurity, like a decade maybe. And cybersecurity researchers knew that, hey, since one system has been found to be vulnerable to this kind of an attack, let's also attack this new system along those lines. But the developers of GPT-4 did not have access to that knowledge that, hey, GPT 3.5 was attacked, so let's fix this. And it's actually still not fixed. A more relevant story may be in the context of generative AI, text-to-image AI, image recognition, is the story of stable bias. So this paper came out by Hugging Face, which was written by Hugging Face researchers back in this March, that essentially stable diffusion shows a lot of different coordinates of societal bias. Nothing was done for 3 months. And I think just last week or 2 weeks ago, an article came out in Bloomberg where a couple of reporters, they also analyzed stable diffusion and found similar vectors of bias. So basically, stability AI did not fix anything in the last 3 months. So these kind of things make us think that, is there a better way to propagate that past information to those who are using these models or to those who are developing these models that can fix problems quicker for future models, that can fix problems for future models proactively rather than reactively? The good news is that we don't need to actually think about new things to devise such a framework. It's already there in cybersecurity. There is a vulnerability database that is maintained by NIST, which does exactly that for commercial software systems. There's an operational taxonomy, which is maintained by MITRE, which categorizes the different failure modes of software systems that are relevant to cybersecurity exploits. There is a system called CVE, which provides open schema to store these vulnerabilities into NVD. So these things can be adopted in the AI world. So the idea is, first, incident reports document the failures, vulnerabilities, what issues in the base model, base data set led to these failures, record those. Taxonomy, codify the significant known weaknesses, map the landscape of that, and finally, store all of this, connect all of these to an authoritative database so that future developers and vendors can learn from past mistakes. That's something that I have started working on from earlier in 2022, maybe Q3 2022. Essentially, same thing, but in the AI world, which is going to be infinitely difficult to more difficult to implement than software vulnerabilities, just because the landscape of exploits for AI failures is much more broader. In addition to intentional exploits, we need to consider silent failures, downstream harms, societal impact, things like that. But this is an open source effort that has been going on and getting pretty good traction that will be hopefully helpful to navigate the landscape of AI failures. Components of AVID, at a glance, there is an operational taxonomy that covers security, ethics, or downstream harms, performance, or internal issues of a model that can propagate to performance degradation or user experience degradation down the line. A database of vulnerabilities, which is a high-level weakness of an AI system, and report, which are occurrences of vulnerability potentially granular and reproducible. That's being built up, which stores reports, which stores vulnerabilities at these 4 granularities, from issues to advisories to measurement to detection, which is increasingly qualitative to quantitative in nature. Finally, going back to the simple, transparent adversarial example, how things would have helped had this thing been there back in 2021, when that paper came out and found out that image recognition APIs like Google Cloud APIs are vulnerable to this kind of stupid attacks, is that the researchers could have reported on that novel vulnerability to AVID, and AVID then notifies the developers and vendors that, hey, there is something wrong with this API, just FYI. Then the vendor fixes the issue in their image recognition API. And then vendor informs AVID of the fix. AVID lets the developers know, and all this information of what the vulnerability is and what happened to mitigate that is persisted in the database as reference to future similar use cases. So that's how, in the ideal world, things should work if we follow the cybersecurity path of looking for failure modes and mitigating them proactively. To end things, I'd end with an uncomfortable truth and also a message of hope that we'll most probably never be able to enumerate and proactively mitigate all possible failures of AI systems. But what we can do is take steps to progressively minimize the likelihood of high stakes failures. The only way to do that is document, codify, and as much as possible automate our development and deployment processes. Not only that, finding out and mitigating the process of finding out and mitigating AI vulnerabilities. Finally, R&D in trusted AI should focus on realistic problems, practitioner enablement and education, fostering a security mindset, and also broad collaboration in learning things from the security folks. If you want to learn more, a great opportunity is coming up, which is generative AI red teaming in DEF CON, which AVID is collaborating with AI Village to organize. AI Villages was mentioned by a press release by White House also like a month ago for this specific event. So that would be a great opportunity to learn more about this new practitioner-focused movement that is kicking off in responsible AI as well. With that, I'll finish and open for any questions. Thank you so much.
Thank you for such a great talk. And let's see if there are any questions from the audience. Yes, one question I had was that your approach, you are kind of trying to catalog all the things. You also rightly say that it is possible to catalog everything. So what will
your voice was echoing a little bit. Is there could you either repeat or write it down in the chat?
Yeah, I guess I had echo on here because of the phone system was employed. So I was just saying that it's like a happening on here, right? Everything in the security world is still cybersecurity attack happening as we speak. So how is that? You are taking examples from the cybersecurity body. How is that going to help us in the AI world? Knowing that we will never be able to catalog everything, but get also derive benefit.
Yeah, if I understand correctly, if I heard correctly, you are asking that what is the best way to kind of adapt cybersecurity vulnerabilities as they are defined into the AI world? That is actually an open conversation that I am starting to get involved with cybersecurity experts, some AI ethics folks as well. The basic idea is that AI vulnerabilities can come from not only intentional exploits, but from design decisions like what data you use or how is this model deployed. And they could be also leading to downstream harms. They could relate to internal model failures like robustness issues as well. So that's kind of the broad notion we have of cybersecurity vulnerabilities right now. That's actually this part, yeah. This is kind of the working definition of an AI vulnerability we have in AVID, which includes bias, physical harm, human rights violation, reliability exploits. So kind of a catch-all of all of this, but this is something that we need to zero in on as a community to characterize that, okay, what kind of failure modes should we care about when we want to persist information about them?
Thank you. Thank you for that answer. And it was really an eye-opener for all of us. Hopefully, we can join you in your efforts to get this, your vision moving forward.
Thanks so much.
We will move on to the next speaker. Let me, for the local audience, let me bring up the introduction to our next speaker. Then we will switch over to the his charts to talk about. So then I already gave you our kind of industry academia. So we had industry, now it's an academia turn. So I guess we have Professor Vineet Balsubramanian, who is going to be our next keynote speaker. And he is an associate professor at Indian Institute of Technology, Hyderabad, but spending now his Fulbright scholar opportunity at CMU. So he couldn't come here, but he has gracefully agreed to give this talk remotely. He is extremely well known in so many of these areas, particularly we've already talked about GradCamp previously. It's a GradCamp plus is what he brings from his group. So he's going to talk today about casualty in explainable deep learning, motivation and methods. Please join me in welcoming Professor Vineet Balsubramanian.
Thank you very much for the invite and for the kind introduction, Professor Ratta. Am I audible, visible, and are my slides seen too?
Yes.
I hope I'm audible too, right? Am I correct?
Yes, we can hear you.
Okay, wonderful, wonderful. Thank you again. I apologize I'm not able to be there in person, but hopefully I'll be able to talk something of value to the workshop. I have been gluing into the workshop whenever I can through the day. And it's been an interesting set of talks. And I think the previous talk to this by Dr. Majumdar is perhaps a good segue into what I'm going to talk about, which is causality in explainable AI or deep learning to be specific. Talk about the motivation for it and a few methods that we have developed too. To some extent, what Dr. Majumdar ended with is the motivation for this is when you have a high risk in applications. I think he also talked about the need for transparent adversaries. You need to know what is causally responsible for the output and act on the causal aspect of the input. And that's what we're going to talk about in this. Let me straight away get into the TLDR for what this talk is going to stand for. Just one moment. Yeah, there we go. So we all know that explainability is becoming an increasingly core requirement of deployed AI/ML systems. But one important thing to note is that explanations need to be actionable and useful in practice to translate to real world use. And the explanations that are actionable and useful are often the causal ones, especially in risk sensitive applications, right? When you have safety critical and risk sensitive applications, what's going to make meaning in terms of your explanations are the ones that are really causal. So what does this really mean? How do the two sit together? How does causality and explainable AI sit together is what the rest of this talk is going to be about. Just a quick precursor. I know I'll be preaching to the choir for just 1 or 2 slides. Please bear with me. Just a broad introduction. I think all of us know that explainability in AI is an increasing need, be it way back from the European Union's GDPR, or more recently its AI Act a few days ago, or US's Algorithmic Accountability Act, or the more fundamental right to explanation. And even countries like India have their own responsible AI strategy, which focuses on explainability significantly. I think we all know that we need explainability in our deep learning models as we go forward. And obviously, there has been a lot of conversation around this for the last 7-8 years, since I think 2015-16 is when a lot of the initial efforts came through. In the last 7-8 years, there have been a humongous body of work covering various aspects. I think there's a nice graphic that I borrowed from this XAI tutorial presenters that brings together the explainability efforts from machine learning, computer vision, NLP, AI more generally, planning, search, robotics, so on and so forth. Right? So we know that this canvas has gotten wide over the last few years. The question that still remains when we talk about explainability is the real elephant in the room, which is, what does it really mean? I think the elephant in the room also seems to be like the proverbial elephant that is felt around by 5 blind people, as they say, where each one who touches a part of the elephant thinks it's a snake or a fan or a tree or a rope or a spear or a wall. Explainability has had that connotation over the last few years. If you're somebody functional who's working with AI/ML systems, explainability could mean very different things. It could mean a business owner wanting to know whether they can trust AI models' decisions, a data scientist wanting to know whether they can improve the model, an IT ops person wanting to know how they can debug the model, an audit or a legal person wanting to know whether the AI systems are fair, or a customer support agent just wanting to know how they can answer a customer complaint. Right? All of these have been subsumed under one umbrella over the last few years. And even technically speaking, there have been a plethora of different ways of looking at these methods, be it post-hoc versus intrinsically interpretable, transparency versus reasoning, model agnostic versus model specific methods, global versus local methods, attributions versus actionable explanations, so on and so forth. In this talk, we're going to focus on one aspect of this, which is the causal versus correlational associations of these explanations. And that's what we're going to focus on. And hopefully I'll be able to motivate why we need this in practice too. In our own group here at IIT Hyderabad, we have been looking at all of these directions because I personally feel that you need holistic approaches, and explainability lies at the human technology interface. And for different situations, for different people, and for different tasks, you may need different kinds of explanations. So I personally do believe that you need different perspectives to explainability. And going forward, probably even have clear user requirements and specifications based on which we develop models and deliver them for deployment. In our own group, we have been looking at it from multiple perspectives. We have been looking at post-hoc explainability. As Professor Atta mentioned, one of our earlier efforts was GradCam++, which is reasonably used around the world today. We've also done some work on submodular ensembles of attribution methods. And more recently, we have been focusing on intrinsically interpretable methods, where the explanation is baked into your model rather than it be dealt with as a post-hoc analysis of a pre-trained model. We've been looking at it both ways. But in particular, we have been looking at both non-causal methods and causal methods in each of these. And I'll focus on our causal efforts in this particular talk at least. I think it's well known from a statistics perspective on the differences between causation and correlation. I think there are plenty of different statistics that you'll find online. But here is a simple example of if you take statistics of, say, ice cream sales and shark attacks, you can see that both of them peak during summer. And if you put this together in a data set and one of them becomes the input variable and one of them becomes the output variable, you're going to assume now that when ice cream sales are increased, you're going to have a higher probability of a shark attack, which doesn't make sense in a real world system. And so how do you dissociate these kinds of correlations from causation is what we ideally need to look at when we look even at neural network, even neural models. One of the standard ways of introducing causality is through the Simpson's paradox, a very popular setting that's done in standard causality classes. And I'll very briefly give you that introduction before going into what we have done for bringing causality into deep learning based attributions. A contemporary example, let's say you were considering vaccines for COVID-19, and let's say there were two kinds of vaccines, A and B, or 0 and 1. And there was a patient condition, let's say mild or severe, 0 or 1 again. And the outcome was the mortality of the patient, whether they ended up alive or dead after taking the vaccine. Let's assume that there is a particular data set that gives us these numbers that you see here, where you see that if you vaccine A has a 16% mortality rate, that's the number of people who passed away after taking the vaccine, while vaccine B has a 19% mortality rate. If anybody was given just the statistic and asked to choose a vaccine that they'd like to take, assuming they had those options, obviously it's natural that somebody would go for vaccine A, right? Because it has a lower mortality rate. But if only you looked at the data more carefully, okay, we go into noticing that if you considered a cross-section of the patients with mild and severe symptoms, you have this kind of a statistic. There's exactly the same statistic expanded with two more columns here. It's the same 16% and 9%. But we notice that for patients with mild symptoms, A had a mortality rate of 15%, while B had 10%. B had lower mortality. For severe symptoms, A had a mortality rate of 30% and B had 20%. If you look at this for both mild and severe patients, it was vaccine B that had a lower mortality rate. But the overall mortality rate for A is actually lower. This is known as the Simpson's paradox. And a closer observation of the numbers will tell you is this is because vaccine B ended up being used for a larger number of severe patients, because of which the overall mortality rate went lower. In this kind of a context, you call the condition variable as a confounder, which is affecting the relationship between treatment and outcome. And I'm quite sure that when we are training deep learning models on different kinds of data, there are several different confounders that we have to deal with on a daily basis while we classify. Even in this kind of a scenario, if somebody asked you which vaccine, I mean, obviously, if you looked at the second table, you would probably say that vaccine B was the better choice. But the truth is that you really need to know the causal graph. If the causal graph was this way, where the condition affected the treatment and the outcome, then treatment B is perhaps better. Whereas if the treatment directly affected the condition, treatment A is still better. Right? So it depends on what are the true relationships or the causal relationships between these variables, which tells us which is the better treatment to go with. Obviously, this is a very statistical example, not really machine learning. Let's step into seeing this from a more machine learning perspective. We all know that the core objective in supervised machine learning is how is data and labels related, right? So we are always looking to approximate that function. So if you looked at this particular example, you see three different causal models. As you can see, X and Y are variables, three different kinds of causal models, all of which have the same distribution. Right? You can see in one case, X goes to Y. In one case, Y goes to X, and in one case, there is a confounder Z that affects X and Y. And you can see the equations here and plot them for yourself if you don't believe, but all of them lead to the same distribution. Now, one could argue, how does that matter to me? I'm anyway going to try to fit the data. Why should I bother about this? Things start getting tricky if you start moving to a different distribution rather than just a different test set, say, rather than this data set alone. Okay. In that particular scenario, let's say you want to evaluate on data from other distributions. If you just change a variable in each of these, let's say you change one particular variable here and set it to one particular value in the first distribution, the second distribution, and the third distribution, a third causal model rather, you see that the distributions start changing at this point in time. So when you start setting values to specific variables, which are called interventions in causality, each of these become a different interventional distribution. And one could consider different domains of data that we see on a daily basis, whether you're dealing with a problem such as domain adaptation or domain generalization. Often you could view each of these domains to be interventional distributions of a true causal model, right? That's the way we really view it too, right? We see that it's the same classes in different domains, but then their appearance is different, which means there's some variable that has been changed and the same object has been captured through a different distribution, which precisely captures what an interventional distribution is in causality. Now, this means that you ideally need a causal analysis for developing models that generalize to especially out of distribution data. The causal model is actually going to be more stable in these kinds of scenarios than a pure correlation-based model. Okay, so I think that hopefully sets a bit of stage for causality in machine learning. Why causality in explainable AI, right? To understand that, let's consider that you are training a neural network model to say predict risk of heart disease from some kind of a data. And let's assume that there is one of those variables which is high blood pressure or hypertension, which is directly connected to the risk of heart disease. Obviously, it's likely that most patients in your data who have had a higher risk of heart disease would have had a high blood pressure or hypertension. Does that mean that the blood pressure caused the risk of high risk of heart disease? Not really so. There could be a confounder such as say BMI or the body mass index of a person, which could be causing both the blood pressure and the risk of heart disease. And when a person has to address the problem, they may want to address the BMI issue more than the blood pressure issue because that's causing both. That's the need to have causality in explainability, because once you know the variable that's causing the output, you know what to actually address to fix your system. I mean, going back to what Dr. Majumdar mentioned, especially if you have risk sensitive applications, if you know the variable that's going to causally affect the output, then you know what to change to make more robust changes in your system. That's hopefully clear on the motivation for causality in explainable AI. More generally speaking, Julia Pearl, who's famous for his reflections on causality, his theory of the entire probabilistic framework for causality over the last few decades, has a nice causal hierarchy, which consists of 3 levels: association, which is P of y given x, that's your standard conditional probability that we do with all supervised models, which is the typical activity there is seeing. If I saw such a symptom, what is the probability of a particular disease, right? So that's what P of y given x would do. But higher levels of reasoning are interventions and counterfactuals. I think counterfactuals is a widely used word in different contexts, but in a causal sense, it means something very specific. So interventions are where you do and intervene and check what the outcome is. So if I had a headache at this point in time, what if I take aspirin? Will my headache be cured? Is an intervention. I have not done it. I don't have that observational data. But then how do I check whether this intervention would give me a cure for the headache is the notion of intervention. And the concept of counterfactuals from a causal perspective is about imagination. Is if I had done something 1 year ago, where would I have been today? So obviously we cannot really find out the answer because I did not do that. I did something else and that's where I am here today. But counterfactuals is about if I had done something else, where would I have been? I can never observe this. At least with intervention, there is a possibility of that being observed. With counterfactuals, you may never be able to observe this in the real world, but you still want to see how that would look under a particular condition. Those are counterfactuals, right? So these kinds of reasonings can be done only using the causal framework and not the standard conditional probability inference that we typically use in supervised machine learning. Okay, so with that out of the way, the question is then, how do you really imbibe these principles in explanations of neural network models? And we have done a few efforts in this direction, which I'll quickly review over the next, say, 15 or 10 to 15 minutes. One of our earliest works in this space was a few years ago called Causal Attributions in Neural Networks. It was in ICML 2019, a joint work with some of my students, Aditya, Piyushi, and Anirban. To the best of my knowledge, it was one of the earliest efforts in bringing causality into explainability and attributions in neural networks. The question that we considered here is if you have a pre-trained model or a trained model, right? Remember that most of the post-hoc explanation methods, including methods like SHAP, GradCam, DeepLift, and all of these methods, they consider a trained model and then they try to compute attributions or the effect of an input variable on output. That's the standard question that we try to ask. So the question that we try to ask in this work is, if you considered a standard trained neural network model, what kind of causal relationships did it learn between input and output? We're not interested in the correlations. We're interested in trying to understand, did it learn any causal relationships? How can you compute or understand those causal relationships? Okay, so I'll come to the converse of this a bit later, but this is one of the earliest things that we did. So to do this, we need to just talk about a bit of preliminaries. The literature on causality starts with assuming that all the data that we see in the real world comes from a structural causal model, which consists of a set of endogenous variables, which are the variables that you observe. Exogenous variables are your latent variables that typically you may not observe, or noise, for instance. F are the causal functions, which is what we want to compute. F are the causal functions that connect each input to the output variable, and that's what we typically want to estimate. And you also have something giving you the distribution of U, such as noise taking a Gaussian distribution or something like that. Okay, this is how a standard SCM would be defined, a set of equations that connect every variable to every other variable in your system. Obviously, if you knew the SCM, there's no need for machine learning itself, because you have the connection between input and output in terms of functions. We often in the real world don't know what the SCM looks like. But keeping aside the true SCM, because we don't know where data was really generated or what functions actually created the data, we assume that a neural network can be viewed as an SCM by itself. You could consider a causal abstraction imposed on your neural network and view your neural network as a structural causal model, where your input variables are your different nodes of a graph, and you have your output variables. You can marginalize over all your hidden layer variables and get only the relationship between input and output variables. We refer to this as a structural causal model, where L1 refers to all your input variables, Ln refers to all your output variables of your neural network, U refers to those latent variables and noise that affect the input that we cannot observe, unfortunately. F prime is not a gradient. F prime is just these causal functions in this reduced SCM after you marginalize your hidden layer neurons. That gives you the causal functions taking you from input to output. Okay, now that a neural network can be viewed as an SCM, we know that there is a causal relationship between every variable and every other variable, and we try to estimate what the quantity known as the causal effect in these kinds of scenarios. Estimating causal effect, or sometimes also called treatment effect, is one of the core problems in causality. And it's studied in different scenarios. For example, the effect of a drug on a particular outcome on a person, or effect of a certain intervention in the economy to how the GDP improves over the next few years, so on and so forth. Right? Causality is studied in many of these scenarios. Coming back to a neural network, you could view the causal effect as, this is a standard definition rather, the causal effect is, if you had binary variables, you give that as an expectation of y, given that you intervene and set x to 1. The do notation refers to an intervention, that's a forced intervention, where you set a specific variable to 1, minus the expectation of y given do x equal to 0. For continuous variables, you have the same thing, where xi, which is one of the variables of x, set to a particular value, minus the same quantity when xi is set to a baseline value. This is very closely connected to attribution, because this is essentially studying the effect of an input feature on the prediction function's output. But this is the causal way of studying that attribution. The question now becomes, how do you compute this quantity for a trained neural network? So what we go ahead and do in our work is we show that this first quantity is the standard definition of an interventional expectation. And the second value, called the baseline, is something that can come from domain knowledge. For example, the example on hypertension that I gave, you know what a standard hypertension value should be. You can set it to a particular value, Or we could do an expectation over expectation to just take the average value across your entire range and set that to be the baseline. I'm not going to go into the math details, but to compute this, we use a Taylor series expansion. We do some linear algebra tricks and use some probabilistic graphical models to be able to compute those quantities and go ahead and compute that average causal effect of a trained neural network model. We show that you can do this not just for feed-forward networks, you can do this even for recurrent networks, which get a little bit more complex because an input variable at time t1 could have a different causal effect on the outcome versus the same input variable at time t2. Right? You have to make that distinction when you compute causal effects in recurrent neural network models. So we show with this work that we get pretty good estimates of causal effect. I'm not going to walk over all the results considering it's published. Some of these have been carefully curated and shown for validation. And we show that such causal effects that we compute can mirror how existing ground truth can be represented too. In fact, we also studied this for a real world data set on aircraft data. It's called the NASA Dashlink data set, where we saw that the causal effect computed using our method actually matches how humans understand the explanation for that particular application with aircraft data. We were looking at an anomalous landing versus a normal landing of an aircraft in this kind of a scenario. If you're interested further, both the paper and the code are available online, but I'll probably just take the next 5 to 7 minutes to talk about the converse of this, which could also be interesting. More recently, last year, we had a work called causal regularization with domain priors, which tried to look at the inverse of what I spoke about so far. Right? In the inverse, what we try to do is, if you had some prior causal knowledge with you, right? So existing neural network models are largely data-driven. What if I had some domain knowledge with me, which means I've carried out some studies, or I am a domain expert, and I know that a particular variable has a monotonic relationship on the output variable. I know that for sure. Now, how do I ensure that my neural network respects that relationship as causal while it learns is what we try to look at in this particular work. So the core idea is this. So in the previous work, we were looking at, for a trained neural network model, how do you learn the causal relationships between input and output? And in this particular work, we looked at the converse and said, if you had access to prior causal relationships, how do you ensure that you integrate them to training of neural network models? And the prior causal relationships can be of any kind. It can be monotonic, it can be a J-shaped curve, it can be a W-shaped curve, it can be any function that you define on that is known rather from domain knowledge. So to do this, the key idea is that we match the causal effect of the neural network that we are learning, with the domain prior function for that particular variable for which we have access to. And we also do this with partial knowledge, which means even if you have access to partial domain knowledge, just the relationship of one variable to the output, and you don't have any knowledge about the other variables, this method can actually be used. I won't go into nitty-gritties here, but you can divide causal effect into things called controlled direct effect, natural direct effect, and total causal effect. I just have a brief definition of each. And one of the core issues in causality is called identifiability, which allows you to measure causal quantities from observed data. Right? So that's what we refer to as identifiability. And we formally show that in neural networks, quantities like controlled direct effect are identifiable during training, and we provide a regularizer to do the regularization of the controlled direct effect. In particular, we show that this entire regularization of the causal effect that ensures that your final attributions match your two domain priors can be achieved by just adding one term to whatever loss function you have. You train your ERM stands for your standard empirical risk minimization loss. You add one loss to it, and that ensures that you can match the causal attributions of your domain prior with respect to your neural network itself, and which simply follows a gradient matching kind of an approach. We show that using this kind of an approach, fairness now becomes one of the subsidiary outcomes of this kind of an approach, because fairness is a flat relationship between input and output. If you don't want a specific variable to have, if you don't want it to have any connotation on the output, you then want a zero relationship or a flat curve between that input and the output. That becomes one of the special cases of such an approach. But if your input had to be monotonic, U-shaped, J-shaped, we show that in any of these cases, our approach outperforms the standard ERM kind of learning by just adding one term in the loss and maintains the causal attribution to what you want it to be based on domain knowledge. If you're interested further, this paper is again available online. We also showed more recently that you can also extend this to go beyond direct effects in neural networks. You can also go to indirect effects by introducing edges between your input neurons in your input layer. Right? Obviously, that's not a traditional neural network architecture. You'll have to train it a bit differently. But if you can introduce edges between your input neurons in your neural network architecture, you can also go and ensure that you match indirect effects that you know in your domain to what a neural network learns from your data. So we show several different examples, and this was the overall algorithm. Once again, if you're interested, the paper is available online. If you try to look at it in more detail. I know I'm probably almost out of time. I'll very quickly take a couple of minutes to talk about our other efforts and open problems, and I'll be happy to then take questions. Some of our other efforts in the space have been around causal counterfactual generation that can help in mitigating biases. This was a work that was done at WACWI 2022. And more recently, also on how do you disentangle latent factors causally when you learn generative models in vision. This was a work that was at AAAI last year. We also developed a vision-based data set for causal analysis, which was recognized at CVPR 2021. If any of you are interested in looking at such data sets, you can see this data set called Candle, relates to causal disentanglement on GitHub if you'd like to know more. To quickly conclude, where are we going with all of this? Is causality really required for explainability? Where are we going with all of this? Just a few thoughts on ongoing efforts and future directions. There is a place for causal relationships and a place for correlations too. Not everything needs to be modeled from a causal perspective. There is a need for causal modeling, but there is also space for just being correlational at times. How do you separate these? And when do you use correlational based modeling? And when do you use causal modeling? I think is a very open question at this point in time, which would be great to discuss and debate. Learning causal models of latent variables in vision becomes a very, very important topic to work on. A lot of work on traditional causality focuses on tabular data, where the reasoning variables and the observed variables are the same. Unfortunately, with computer vision, your observed variables are pixels, but you don't reason in terms of pixels. You reason in terms of concepts or latent variables. So how do you then study causal effects and causal attributions at the level of concepts or latent variables becomes an important question to answer. And more general questions are, how do you balance the trade-off between accuracy and interpretability? Is interpretability always required? It's not required in many occasions. So when is it required? When is it not required? How do you evaluate explainable systems? And also the need for data sets and benchmarks tailored to specific use cases. As I mentioned, I personally believe that explainability and a lot of the topics that we're discussing today sit at the interface of humans and machine learning or AI technology. And when you position something at the interface, there has to be information passing both sides. There has to be a specification and an answer based on the specification. Currently, it's almost like a one-way street where the AI model decides to give information and decides what to give as explanation. But probably we need to provide for more porosity in that interface and allow users to have more interactive experience with these AI/ML systems going forward. With that, I'll conclude with acknowledgements to all the students and collaborators and all our funding bodies that have generously supported us over the years. I'll be happy to take a few questions. Thank you very much again.
Thank you for the illuminating talk. And any comments, questions from audience? I guess I had a general question. has the causality model been that you developed been applied to any practical cases like medicine, computer vision, or similar, or the one that you were showing briefly, the face recognition?
Sure. Yes, very much, very much. So in our own work, we show that if you, instead of reasoning on input variables, if you generated a latent variable model, such as you have a VAE or any other latent variable model, which can also classify other than being generative, now those latent variables become reasoning variables for you. You can compute the causal attribution between the latent variables and the output. We in fact have some examples of this in our paper too. Then you can reason on that. And those latent variables could represent several semantics. For instance, some of them could represent, say, a blob in an image. It could, in medicine, it could just be a blob in a particular chest X-ray, or in a certain other application, it could be a certain texture in one part of the image. In certain cases, it could be color. So you could now reason in terms of those latent variables causally using such a framework.
Thank you. Yeah, yes. The second question I had was that intriguing idea that you had around input layer itself being connected. Some how is that related with in real world?
Sure, because the moment when we train a neural network and we don't connect the input neurons, we are making this implicit assumption that the input variables are independent of each other, even though they are dependent in the real world. You are making that assumption that they're independent. Of course, they do have correlations as you go through the neural network, but they don't directly influence each other from the input. So if you want to measure things like indirect effect in causality, we show that you cannot do that when you have your input layers to be independent of each other. You cannot provably measure quantities like indirect effect. By indirect effect, I mean that, for example, as we talked about, a quantity affecting another quantity which affects the output. Those kinds of things cannot be measured when you have independent input variables. So you need those connections between input variables to measure indirect effect quantities.
Yeah, that's talking about the pixel world. The pixel world, there is a kind of, all pixels are not independent, right?
Absolutely, very much. Yes, yes. So absolutely, yes, yes. I think you want to ideally, I think in vision, when you apply that kind of a principle, you want to have lateral edges in a bottleneck layer of a VAE, for instance. For example, if you take a bottleneck layer of a variational autoencoder, you would have all of those variables to be independent of each other. There are no connections between the variables in that particular layer. But those are your reasoning variables when you reason in terms of the latents, because typically, although, I mean, in post hoc explanations, we do show which part of an image corresponded to a cat or a cancerous region. We do those kinds of reasoning. But I think when we go to more evolved explanation models, we want to reason outcomes in terms of concepts. I may want to say that this is a cat because it has 4 legs, whiskers, and a furry coat. Now, these are concepts that may not directly come from pixels. They come from intermediate layers. Now, in those kinds of scenarios, you typically want to reason in terms of latent layers or intermediate variables of your neural network. So when you do that, if you want to capture indirect effects, you need intermediate connections in that layer of reasoning. Whichever layer of reasoning you want to reason on, rather, you want connections between neurons in that to capture indirect effect. Did I answer that question?
Yes. Yeah. No, I think it is clearer now that when you meant connections, you're meaning not purely at the input layer, but input to the reasoning layer.
Exactly. Yeah. Whichever layer you want to reason at. I think for standard tabular data, it becomes input layer, or standard many other kinds of data, it becomes the input layer. But for vision, it would definitely be an intermediate layer.
Yeah, I guess we have a question here from the audience.
Very nice talk. So I have a question. So it's somewhat related. My research is and some of this sometimes model detects the bad, we apply AI to it and see the model determines correlates to each of that's they use the feature on the bad is the patient to COVID. Now we have moved to generative AI to augment our data set. So I want you to comment on do you have any comments on how can we incorporate those causal relationships into generative AI for data augmentation while not having the model learn unexpected behavior such as generating some artifacts that we do not see as human, such as bad, and then causing the model to still learn the bad to determine that it's COVID instead of the real patient.
Got it. I hope I followed the question correctly. Please do feel free to let me know if I've not done that. I think that's a great question. And one of the works that I did not talk about today was our work on causal counterfactual generation, where we try to do something like that. Ideally speaking, you want the generative models, very broadly speaking, when we talk about generative models, we ideally want to model the inverse process. I mean, we want to go back and capture the original structural causal model from which data is being generated, so that I can now sample as much data as I want. I mean, in truth, that's what we are actually looking for, although we don't state it that way, because we don't know the true generative process, but that's what we're really wanting to capture. And when we talk about causal counterfactual generation, I think there is a standard principle that we follow for, I think it's there in our work in WCV 2022. I think trying to follow standard causal, there are 2-3 things is when you learn a generative model from some latent variables, you ideally want those latent variables, going back to the previous discussion, to capture the true generative process. I mean, in a sense that if you have typically use a bunch of independent variables, but if you think in the true causal model, they need to be connected, you need to have a graph that's similar to the true causal model in your intermediate layer to generate. That's one part of it. There's also a standard procedure that Judy Appel provides for counterfactual generation. It's a 3-step procedure that he provides. I think that also needs to be followed when you generate counterfactuals or generative examples from these samples. So I think it's possible to incorporate some of these directly in some of these diffusion models, in generative models, rather, more generally speaking. I also think the notion of disentanglement among variables, that's the other work that we had here, I didn't get a chance to go into it, is generally when we disentangle, do any kind of disentanglement to generative models, that need not necessarily be causal disentanglement. Trying to ensure that you separate variables in a causal perspective allows you to connect more with the true causal process rather than be waylaid by, say, correlations among the variables. So I think there are a few pieces that you can put together to influence the generative models, like causal disentanglement, following the causal counterfactual generation process, and also trying to have connections between appropriate input variables that are reflective of the true causal processes. Obviously, we have only partial knowledge about some of these, but trying to do that, I think, could give you a more causal grounding for generative models in practice. I hope, did I answer that question?
Yeah, thank you.
With that, let's thank the speaker again.
Thank you. Thank you.
Now we could break for coffee and meet in 15 minutes for our last session.
Yeah, we will resume our session at 3:45. And then while you are doing coffee break, we will have poster session at the poster number 1 to 15 in the exhibit hall. Yeah. So see you later at 3:45.
Okay.
do I need to do? Sorry. What do I need to do? Oh, okay. We'll wait for a few minutes. I can't understand. You are now. Do you have the audio check? Okay. This one set up already, yeah. So we can, yeah. All right. Okay. So let's get started with our final session of the workshop. And we already have the pattern. We have two. Microphone. Yeah, I will. Hey, so as we discussed already, our concept of meeting speakers from academia and industry. So we had the previous one from academia. So now it's a chance for our industry side. So I'm definitely pleased to introduce my colleague. Once upon a time, a colleague. Since he is still at IBM, I'm not at IBM. So I guess he is my ex-colleague. So Pinu, who is very well known in this world of explainability and robustness and adversarial attacks. In fact, the IBM R360 and the AIX 360, all those toolkits are coming with a lot of contribution from Pinu. So Pinu is a very well-known researcher. He has large number of publications in every AI conference. And he is also the chief scientist of the RPI and IBM collaboration. So I guess we can go on listing his, and we will be then cutting out maybe half of the time that we have allocated for his talk. So we will proceed with the talk instead of going through. As I mentioned in the morning, we will release all these introduction charts through our website so that you all can see the credentials, and definitely we are highly privileged to have such a series of high-profile keynote speakers. So with that, let's welcome Pinyu for our talk today.
Yeah, so thank you for having me. It's always a pleasure to give a talk in a trustworthy AI-related workshop, and Nali has been my true mentor and taught me a lot during our IBM time. And Guanchen and I, right, we know each other back in high school times, which like probably 20 years ago. So it's very amazing to be connected. So today I'm going to talk about one topic I'm very excited about, right? That's this how can we reuse the current foundation models, right, to do data efficient, privacy preserving machine learning. So, so I will start by showing you a new technique that I've been advocating called model reprogramming, and how can we use model reprogramming to train efficient machine learning models with differential privacy constraints. And if time permits, I will go into some explanations about why model reprogramming works. Okay, so what is model reprogramming, right? So it has to be tied with the very new era that we all live in, right? Foundation models. Actually, in the morning, I just gave a talk on trustworthy AI, a tutorial on trustworthy AI in the era of foundation models. So we are certainly live in a very interesting time where we are witnessing a revolutionary changes in our machine learning methodology, right? So in the past, we are so used to, training one model for one task, right? Like image classification, convolutional neural nets, so natural language processing, long-term short-term memories, right? And so on. But now with these foundation models coming up, right, we are switching our focus from this one task, one model perspective to like one foundation model for all different tasks perspective, right? But basically featuring pre-training and fine-tuning, right? So foundation models, right, is basically we aim to train a general representation networks, right, that represents every data modality of our interest, including multi-modalities, right, into some universal and generic representations. And once you have that powerful data representations, right, you can take that representation and fine-tune it to any downstream task of your interest using the same model. Right, so one very concrete and successful example, right, is ChatGPT. GPT is the foundation language model, and then ChatGPT is nothing but taking that GPT model and fine-tune on Q&A tasks with more or less of instruction tuning, right, to become a very well-known and powerful application, right? Just one of the many possible applications of foundation models, right? So this is just to give you a context of how we should see things differently with this availability of foundation model and ChatGPT or like Meta's segment anything, right, for feature foundation model and so on. So what can we do, right, with this new era of foundation models, right? So lots of research were worrying about, oh, we are going to be out of research topics, right? Because foundation model can solve everything, every task that we care about. That is partly true, but also I would argue that is not the end of the world, right? So it is true that in some data domains, right, like a language, like a text, like an image, like audio, we do have a lot of data and we have the ability to train powerful foundation models. But also there are other domains, right, that require machine learning to make breakthroughs. But in those domains, right, like biomedical learning problems or industrial sensor data, those data are in a much smaller scale, and then annotation could be very expensive to obtain because that requires like real expertise, right, like doctors or very senior professionalship to be able to provide meaningful labels. So in these domains, right, how can we leverage existing foundation models, right, to do this cross-domain machine learning to solve different problems? This is how I envision model reprogramming can be useful, right? So the idea is to really take a pre-trained model from this well-established domain, and then we fix those models, right, without fine-tuning the weights. And what we do is we insert some extra layers in front and after the pre-trained model, right, to enable this model to reprogram the model, right, to solve a new task. right? You can think about it as a parameter efficient fine tuning or even a prompting for cross-domain tasks if you like. But really, the really interesting thing is like the parameter efficiency, right? With this technique, you only need to fine tune the parameters of the layers we inserted, right? And then so it has a very good data parameter efficiency and then reusability, right? So we can maximally reuse the pre-trained models, right? Available to solve different and challenging tasks. And in terms of this learning efficiency, right, it is certainly very efficient compared to training a foundation model from scratch, right, or compared to training a specific model in that target domain. I actually wrote a survey paper on model reprogramming, but I'm going to go into the high level idea of how this works in this talk, at the first part of this talk. So one analogy I would like to make is that I like to quote Sir Isaac Newton here, right? So he once said, "If I have seen further, it is by standing on the shoulders of giants." Right? So I would use this to describe how parameter efficient tuning is working, right? So the giant here, right, is the powerful foundation model that is available, right? Like GPT language models or vision foundation models. Now, can we build something on top of that, right, to help us solve different machine learning tasks, right, to broaden the application of these foundation models, right, especially in domains where we only have limited label data, right, like the medical tasks, or in domains where there is simply no good models exist available because there's no sufficient data to train a domain-specific foundation model, right? Or in scenarios where we only have limited resource, right, like the average researcher who only have like a few GPUs, right? It's impossible to train a foundation model, but still we would like to leverage the power of foundation model to help us solve downstream tasks, right? So limited resource settings. And lastly, the training constraints, right? Especially privacy constraint, where basically you assume you can only access the private data for a limited number of times, right? So not to break the privacy budget, or you have other constraints like a training time or so on, right? So those are what I call the resource limited settings, right? So I would argue that model reprogramming should be very useful in terms of a resource efficient transfer learning method without model fine tuning. So just to give you a sense of why we should reuse this available foundation model as much as possible, right? I would like to make an example of GPT-3, right? So but in general, foundation models, they actually feature large scale data for pre-training, right? So you take the entire Wikipedia or the entire web text you can extract from the web to do pre-training to obtain the representation network, right? Using like a large scale, I heard high fidelity language models, right? Like billions of parameters, for example. And then once you have that, you will fine tune it for different downstream tasks. So GPT-3, right, which is the backbone of ChatGPT, right? It was actually trained on about 1,000 billion tokens, and then the number of parameters for that model is 175 billion. The memory size, right, simply to load that model in full precision is 350 gigabytes. Right? And if you evaluate the cost of training GPT-3 using the current cloud pricing, it is about 12 million, right, to train such a model, right? So having invested so much, you would like to reduce the model you train as much as possible. That is only for GPT-3, right? Now, if you ask how much does GPT-4 cost, right? So there is no official document, but the OpenAI CEO, right, Eric Altman, he actually admitted that the cost of training GPT-4 is probably above $100 billion US. This is the largest and most powerful language model we have so far. Okay, so I would like to again highlight the difference between the resource limited learning setting versus the standard setting, right? So if you are in a scenario where you have a lot of data, you have limited compute power, right? Then I would say you just do this pre-training and fine-tuning as is, right? Without worrying about the reprogramming. But if you are in a scenario of a resource limited setting, right, limited data, limited compute power, right, limited resource, and so on, right, then you should definitely try out reprogramming, right, which features efficient fine-tuning without fine-tuning the model. And one contrast I would like to make is the difference to transfer learning, right? So transfer learning is a broad term, but I would like to emphasize that the transfer learning as a baseline I talk about here is actually limited to the fact that in standard transfer learning, we will again also take a source model, right, with pre-trained weights. but we are only going to fine tune a subset of the weights in certain layers, right? So that is what I mean by transfer learning. So in contrast, right, in model reprogramming, we never fine tune the source model weights, right? We only train the layers that we inserted. So this is a very big difference compared to what I call the standard transfer learning techniques. Okay, so before I dive into detail, I would like to highlight where this reprogramming idea coming from, right? And actually, I noticed this paper from this universal machine learning literature. So there was a paper back in 2019, right? They actually argued that pre-trained models can be reprogrammed, right, to secretly solve different tasks, right, without the attention of the model developer. For example, they can reprogram an ImageNet classifier to do different tasks like the MNIST classification, image counting, and so on, right, without the agreements of the model developer, right? So, but if you look closely in terms of their test accuracy, they only get like mediocre accuracy, right? So nothing is really special except that you can reprogram a model without letting the model developer know, right? So it was framed as a possible resource repurposing attack, like that in that kind of weird sense. So we look into like, is this the best reprogramming can do, right? Especially if we have a more powerful pre-trained model, right? Like a foundation model. So I'm going to provide example in computer vision, like how we can do use reprogramming to do transfer learning without even knowing the details of the model, right? But in which case we call it a black box model, right? So you can think about a black box model as like an image API, for example. So you can call this API to make a prediction on every sample you have, but you will never know what is behind the model, right? And what is the architecture, what is the weight, right? Similar to how we use ChatGPT nowadays. So we never know what is the model architecture, but we still use it for inference. So the setting is we have a pre-trained foundation model, like presumably a black box model. And we would like to reprogram this black box model to solve specific tasks, right? That it is not designed to do in the first place. For example, some spatial biomedical image classification problems that I did below. So this is the transfer learning setup. So how does this reprogramming idea work, right? So we take a pre-trained model, right? In this case, an ImageNet pre-trained model. So every input to this model, right, will give predictions on ImageNet class labels. And now we have a bunch of the target domain images that we would like to reprogram this model. Right? So what we will do is we will take this target model and put this at the center of the data inputs, but also leave some white space, right? Some gray area that is actually some trainable pixels, right? To allow some additional space to make this input transformation function trainable, right? So eventually we will obtain this transformed input data in the target domain, and then we will pass this transformed data to the pre-trained model. Right? And of course, the model will give predictions on the ImageNet labels in the first place, right? So we will need to do a second thing, which is mapping the source label to the target label, right? So we will say, okay, the class of tench, golden fish, and so on will be mapped to ASD, and then the other set of the class label will be mapped to non-ASD. ASD means autism spectrum disorder, one of the binary classification problems in one of its downstream tasks. So eventually we created a complete end-to-end forward path, right? Starting from a target model, transform into some perturbed data, and then pass it to the source model, obtain the source label prediction, convert it to the target prediction, right? Eventually we have an end-to-end target model, right? Without changing the model weights. And then we can further minimize the training loss on the target task, right? By training the input transformation and those white area, these are borders that we preserve for training the input transformation, or sometimes we can even train the output label mapping as well, if you think about this output label mapping to be learnable. And the training, right, can actually be done if it's a white box model, right? Then we can just use backpropagation to train these parameters. But if it's a black box model, right, we can use techniques like the gradient-free optimization and reinforcement learning, like the zeroth order optimization to optimize these parameters. But notice that in the whole process, right, we never fine-tune the pre-trained model. So this is something very unique to reprogramming as opposed to transforming. So this is just some breakdown of details about how this idea works. Right? So without those of generality, we can call this a model that we are going to reprogram as an F function that takes input scaled between -1 and 1 with dimension d, and then you will output predictions over k classes. And then we are given the set of data in the target domain, right? It's Ti. Also in the same scale input range, -1 and 1. But we assume the dimension of the input samples is d prime, which is smaller than d. So we have this extra gray area, right, to allow the input transformation to be trainable. And this can be easily done if you just simply scale down the target image size. So we then introduce some universal trainable perturbation, right, to allow transforming the input data of the target domain. So how this is exactly done, right, is we take a target domain image and then we zero path this image, right, to allow some extra space. And then in this extra space, right, we are introducing a parameter W that actually controls the perturbations we are going to be added to the image, right? Those noisy frames that you see, right, is one realization of the universal perturbation. And this 10H function, right, is nothing but to make sure the values of the perturbations also lies between -1 and 1, similar to the target image. And this n function is just a binary masking function, right, to indicate which pixel I can add perturbation, which pixel I cannot add perturbation. This is for input transformation, and then for output label mapping, there are a lot of strategies we can do, right? But the simplest strategy, right, is to assign m source labels, right, to one target label, right, individually. Right? So, for example, I can assign the prediction probability of ASD, right, one of the target label, to be the average prediction probability of the 3 source labels, right? Tench, golden fish, hammerhead, right, from ImageNet. I will say, okay, the average probability of ASD is going to be the average of these 3 label predictions from the source model. Right? And this is how we construct one example of output label mapping. But you can also generalize it, right, to consider different types of label mapping. I will talk about that in later slides. And once we have that, right, we can apply our favorite training loss, right, to minimize the loss function on the target data. Right here, we are introducing something more generic, called the focal loss, which is the generalized version of cross entropy, right, by assuming you take into account the confidence of each training sample when you minimize the training loss, and if the confidence is low, you are going to make a larger penalty in the loss function. And in a special case of focal loss is cross entropy, right? So basically, our method is agnostic to whatever training loss you want to assign, right, to solve the downstream task. And then once we specify loss function, what we need to do is to optimize the parameters that we introduce, right? The input transformation function or the output label parameters using gradient descent or gradient-free optimization methods to optimize these parameters. So this is actually a very generic principle, right? So it works in a very model agnostic way. So we can do this for different cases as long as we can specify the input transformation function, what is the output mapping function, and what is the loss function for the target task that we want to solve. So in the paper, the survey paper, we actually show we can reprogram a speech model to solve time series classification problem in industrial sensor data, or reprogramming language models, like English models, to solve protein sequence learning problems. And those are, again, very different domain tasks. And also reprogramming computer vision models, right, to solve biomedical measurement learning problems. So just to show how this idea works, right? So we look into this ASD classification task, right? So this is a test of image classification based on brain region correlation graphs, right? And this is the binary classification task. Each class has about 500 images. So we try two different backbones, or ResNet 50 or instruction V3, and then AR means white box reprogramming. BAR means black box reprogramming. So what you can see is that the reprogramming actually outperforms the state-of-the-art models, right? And so in this case, the state-of-the-art models is actually based on some complicated feature engineering method to extract useful signals from its noisy brain correlation measurements. But in our case, right, we just simply treat it as a downstream task and apply reprogramming, and we can already achieve new state-of-the-art results. And also in this case, right, control learning, right, through this fine-tuning the last few layers, actually even by as much in terms of the accuracy. But reprogramming certainly is more useful, right? If you think about we are basically reusing the source model as a feature extractor and then reprogram the features to solve the downstream task. Okay. And as I mentioned, right, we can also reprogram a true black box API. Right? So this is just one example of how we reprogram a real black box API. Right? So we tried this idea on Microsoft Custom Region API. Right? So this is one of those photo ML tools where you can upload label data set and then you will train a model for you on your behalf and provide inference APIs for you to use, but it will never tell you what is the model, what is the architecture. So in this setting, right, we upload this topic sign classification data set and we obtain the black box API, and then we can simply reprogram this model, right, using some online API codes, right, back and forth to reprogram this classifier for ASP classification, right? So if you spend like $20, right, using this function API codes, you can already get a classifier with 67.8% accuracy, which is about on par with the best sort of baselines that we can get so far. So this is again to show this reprogramming can be done in a very cost-effective way. As a model developer, all you need to do is to pay a small amount of query costs, right, to any API you want to reprogram, and then you can leverage their feature extraction power to help you solve new tasks, and that is not even defined in this black box APIs. That is the very interesting part. Okay, so now I get this question a lot, right? So how is the model reprogramming different from what we call visual prompting, right? So if you know, visual prompting is a very popular term, especially in CVPR, right? So I would actually argue that if the source domain and target domain happens to be both in the computer vision settings, right, then basically model reprogramming is no different than visual prompting, and I will show what visual prompting is exactly. But I would argue that model reprogramming is more general in the sense that it can also enable this cross-domain machine learning, right? In terms of the cross-domain prompting, right? Prompt one model from a source domain to solve a very different task in a different domain, right? So those things, I don't think current prompting has the ability to do that, and I don't think it's reasonable to call it prompting. Okay. So, you know, a few years after the reprogramming paper being introduced, right, actually a bunch of MIT researchers have this idea of visual prompting, right? So if you look at the PUB, right, in their paper, right, it's actually very, it's exactly the same as model reprogramming that we discussed, right? So you have visual prompt, in this case, the input transformation that is trainable, like what we discussed. And then you also need to map the label of the model you are prompting, right, to the downstream label. So for image classifiers, right, visual prompting is exactly the same as model reprogram. But what is interesting in their study is that they also generalize this visual prompting idea or reprogramming ideas, right, to more recent image models, right, like a clip models, which is a joint image text encoder models. So in this case, right, instead of assigning the labels, right, they are assigning the prompts, right? So for example, you can ask, this is a photo of something, right, as a zero-shot inference using text prompt. But to enable this zero-shot inference on the downstream task, you also need to train this input transformation, and then what they call the visual prompt. And also in their paper, they discovered that if you reprogram or visual prompt a clip, you will get a comparable performance to linear probing, which is a very strong baseline in many computer vision tasks. But if you prompt other like classical image classifiers, right, like ResNet, like a BIT, or like Instagram scale trend classifiers, right, you actually get much worse performance compared to linear probing. So there are certainly some new insights that you need to, in order to enable this visual prompting to be competitive and effective, we need a large scale, complicated vision model to do that. Okay, So also in CVPR this year, we are also exploring to improve the full potential of visual prompting, right? So one thing that the original visual prompting paper did not do is that they assume the label mapping to be fixed for the entire time. But what we are arguing is that the label mapping, right, should be dynamic and it should be reassigned, right, when you try to learn these visual prompts, right? So for example, here I'm showing you three different dynamics of how we dynamically adjust the best source label to the target label based on their natural responses. So for example, you have a target label called the marigold, right? So it's actually a flower classification. So during the iterative label mapping process, our algorithm will try to find the best label in the source model that shares similar semantics to the target label, right? So eventually, we will map the orange class in the source label to marigold in the target label, and you can probably see why, because they share a lot of similar semantics, right? And similarly, we will map white lily, right, another target label, right, to this egret, right, the bird class. And again, you can probably understand why by in these examples, because they again share very similar context. Okay, so with this simple technique, right, we can actually improve the clip visual prompting on clip almost for free, right? So in the original paper, right, they are using the same text prompt. This is a photo of something to get the prediction on the downstream task. But in our case, we are arguing you should really think about for each target class, we should try to find the best text prompt for that particular target class rather than using a universal text prompt, right? So you can see that in our case, we actually found that for different target labels, right, like a buttercup, like a blotch, all those different classes, right? The best text prompt, right? There's a pool of the possible text prompt we can use. Actually, the best label mapping that we found can actually vary across data sets, and also vary across the labels in the same data set. And with this simple iterative label mapping process, we can improve the visual prompting on clip by a very large amount, right? Boosting from almost like a 10 to 20% in many cases. And the other thing that is really exciting to me is the data scalability, right? So if we vary the number of training data when we do this visual prompting, right, you can see the blue curve, which is the iterative label mapping, versus the red curve, which is the previous fixed label mapping, right? You actually have a very large gap. And even in the few shot setting where you only have a handful of the downstream data, which is still do a very good accuracy, which means this visual prompting is actually a very efficient, few shot learning mechanism. Okay, so how does this has anything to do with differential privacy, right? So the high level idea is that for differential privacy, we actually want to train the model, but also subject to some constraint in terms of how many times you can expose this private data, right? So there is something in the DP mechanism called privacy budget tracking mechanism. Like basically track if you specify a privacy budget, how many times or how many epochs you can train those models, right, without breaking the privacy constraints. So again, we can compare different fine-tuning mechanisms to specify which one is most favorable to improve accuracy while satisfying the privacy constraint, right? So on the top, we again have model reprogramming as a candidate. And then we compare those three different baselines, right? Full fine-tuning, which means we take the same source model, but we choose to fine-tune every parameter of the source model with the private data. We can also consider training from scratch, which is basically take the same architecture, right, but using randomly initialized weights to train the private data. Or we can consider partial fine-tuning. You take a pre-trained model, like ImageNet, and then you only fine-tune a certain layers, right? And it is very well known that in differential privacy literature, if you train private data with more number of parameters, so you will spend a privacy budget more quickly, and therefore your privacy budget will expire sooner and get a mediocre accuracy at the end. And the differential privacy that we are considering is the standard epsilon delta differential privacy, which is basically saying for any two data set D and D prime, that differ by only one data point, right? And then if you consider a randomized algorithm, right, classifier or a training algorithm, right, we actually want to combine the output of the algorithm D, right, versus the output of the algorithm trained on D prime. It actually needs to be bounded by this exponentiated epsilon plus delta, right, which means the difference of the output between D and D prime when you train this using the same algorithm to train needs to be bounded by this much, and this actually guarantees that as an attacker, it's very difficult to see whether this data point is actually in the training data or not, and therefore you can have some differential privacy guarantees if you can count the difference of these two models. Okay, so we can consider this differential private training with model reprogramming in both centralized and decentralized settings. Right? So centralized meaning you have full control over the training data, and then you just want to get the best model with the best accuracy with satisfying the differential privacy constraints. You can also do the same thing for federated learning. Right? So this is a setting where different banks or hospitals, they have their own private data, right? So, but they want to jointly train a global model without sharing too much private information of their own data. So in this case, right, we can actually ask every client in federated learning to initialize their local model using the same source model, right? But individually, they will also have their own local reprogrammed model, right? It's P-Tower and W1 as the input information and output label map functions in their local version. And through the federated learning protocol, they only need to exchange the parameters of their local green blocks, while they need to train their models using along with these red blocks, the fixed source model. But the actual things they are exchanging is the green blocks. Right? So that's how we can achieve the parameter efficiency in the federated learning case. And you can use whatever DP algorithm you want, right? So the typical algorithm is called the gradient clipping and Gaussian noise, right? So for every client's gradients, we will clip the gradients and also add some Gaussian noise too. And you can show this mechanism can provide some level of differential privacy guarantees. So now with this, right, we can see the advantage of reprogramming. So this red curve is reprogramming, and then the most competitive method is a partial fine-tuning. So these two methods actually requires the least number of trainable parameters. And the other baselines are training from scratch and full fine-tuning because they need so many parameters to train, right? They get very bad accuracy. And then I should have said that the x-axis is epsilon, which is controls the privacy budget. Right? The smaller epsilon means you have a tighter privacy constraint, and the larger epsilon means you have a looser privacy constraint. So you can see that there is clearly a very big gap between the red and blue curve, right? Basically, the difference between reprogramming and transfer learning, standard transfer learning. So which means that given the same epsilon, given the same privacy budget, right, reprogramming always gives much better accuracy and measure in centralized or federated training setups. We can also do something even fancier, right? Using prompting, right, to do differential private fine-tuning, right? So again, this is compatible to another popular DP mechanism called PATE, right, which is a private aggregation of feature ensemble, right? So what they prove is that if you have a sensitive data, right, and then they first segment this sensitive data to uneven disjoint corpora, and then on each corpora they train the feature model, right, on these local partitions. And then they also need another student model in the label data set to do this teacher student training on the student models to obtain some level of differential private guaranteed classifier. So what we can do on top of this, right, is that instead of training these teacher models from scratch, we use a reprogrammer as a teacher, right? So we can again take a source model that is trained on public and private data, and then we reprogram the model to be each teacher, right? And then apply the same setting to update. So this sounds very intuitive, but the result is actually very effective. So if you compare reprogramming or differential private fine-tuning of ImageNet source models on CVPR10, right, we actually obtain the CVPR results, right? And so with a privacy budget of 1.9, roughly 2, right, we can get accuracy of 97.16%, which is actually very close to the best accuracy you can get on CVPR without any privacy constraint. Right? So the gap between private and non-private classification has been reduced, right, to a certain extent. But of course, the source model, right, you use to do reprogramming matters, right? So on the right, we are showing an observation study of using different source models, right, from ResNet to more advanced region transformers. So what you can see is that if you use a more powerful source model to do reprogramming, like a swing transformer instead of ResNet, we do see improvements in terms of their accuracy when we apply this to this prompting-based differential private learning mechanism. And also in this cross-domain setting, right, when we try to reprogram the image model to solve blood and misclassification problem, which is related to like medical data samples, right? We do see a very large gap of the prompt Pate versus the typical like transfer learning-based Pate baseline. So no matter in prompting settings or in standard differential private fine-tuning settings, we do observe this big gap between reprogramming / prompting versus standard transfer learning. So that is the kind of the high-level message and excitement I would like to share with you. Okay, so in the interest of time, I probably need to skip this part, but this is basically showing some theoretical work to explain why model reprogramming works. Right? But if you are interested, feel free to check out our ICML paper. Okay, so I would like to show some takeaways, right? So in this talk, right, I basically walk you through I think a very cool and useful new parameter efficient tuning pipeline that is called model reprogram, right? So it is especially useful for these resource limited fine-tuning setups, right? So it actually has a lot of benefit in terms of data efficiency and reusability. It actually makes the training much easier and more affordable, right, to machine learning researchers. I showed some examples about how successful they are, especially in this privacy constraint fine-tuning settings. So the real takeaway message I want to give is that I hope in the future, if you ever consider using parameter efficient fine-tuning of large foundation models, right, you would also consider reprogramming as a possible candidate, right? I mean, next to other popular methods like adapters, like LoRa, like prompting. Because it is a very useful technique, right? Especially when you are giving a new data set where you don't see immediately what is the best foundation model to apply to those data set. In these cases, right, it is really worthwhile to give reprogramming a try. Okay, so finally, this is the final slide. I'd like to give some references and some open source libraries that we have been built. If you are interested in exploring the potential of the reprogramming and their applications. With that, I will conclude my talk. Thank you.
Thanks for a great talk. I mean, some talks, like the real takeaway is read the paper. You like paste it.
Thank you.
But I'm confused though by how reprogramming works. A little clarity. You add this border of trainable parameters. If you're training something, there's some kind of backprop going on. Yes. The backprop usually modifies weights within some model and not these border pixels. So you can just clarify a little bit the role of these border pixels. Do they change? Are they permanently changed? If so, how does that affect them? What is being trained?
Yes.
All of that.
Thank you. Yeah, so you give me the opportunity to show the slides I skipped. so basically, in a high level, right? So why model reprogramming works, right? So since we are not fine-tuning the model, right? So we are not changing the classification rules of the source model. So this is the first thing to note, right? So I would make an example, right? So if I have a dog and cat classified as the source model, and then I have a downstream text, also a binary text. So what is the best way to reprogram? It will be if we can somehow figure out how do we align our target data set representations, right, to match the representation of cat and dog, right? So if I can match class 0 label to dog and class 1 data to cat magically, right? And then I can use the same class cat and dog classification rule to separate these new target domain tasks, right? Like assuming there is a magical way of massaging the target data representation. So our theory actually shows this is exactly what model reprogramming is doing, right? So theoretically, right, we are adding something at the data input and make this the input this something trainable, right? So when you train this input transformation, right, you are effectively trying to align the target data representation to the source data representation, basically converting the target data representation to be something that can be solvable by the source data, right? Like think about how do we align a new binary classification label data sets, right, to cat and dog classification. So this input transformation we are introducing is actually try to learn how to align this target domain source data representations to be solvable by the same source classifiers. So that is the high level idea. But theoretically, right, we can show the performance on the target task, right? What we call a target risk. Right? You can think about this as the training loss on the target risk. It's actually upper bounded by the two terms. The first term is the source risk, which means how good your source model is on solving the source task. Like this ImageNet examples we are seeing. And there's also another interesting term called the representation alignment loss. This is exactly trying to evaluate how well you can align the target data to the source data. Right? If you can align them perfectly, then the second term will be 0. And when the second term will be 0, you can prove the target task performance is as good as the source task performance because you have the perfect alignment. You learn how to align your target data to cat and dog representations in the same representation space. So that is like the high level idea.
I'm sorry. So you got these border pixels.
Yes.
Do you have a way of modifying, changing this border?
Yes.
Pixels
So yes, exactly. So those border pixels are trainable. Right, so you train those border pixels using the target loss function you assign, like a cross entropy on the target task.
And then if you have a new test image,
yes,
how do you know what border to get?
Yeah, so this is that's why I call it universal input transformation. So at the test time, right, if you have a new test image, you just append this image to the white area, and then you apply the same learned prompt to that image and then pass it to the source model.
So the border,
yes, only one is one border and universal border. Yeah, so this patterns are universal to every image during training and testing. Right, so this is like prompt tuning, right? If you want to think of it that way, right? So if you want to prompt a model like soft prompts, right? You can actually embed some input tokens as soft prompts, and then you train those input prompts embeddings, right, or token embeddings to solve different downstream tasks. So you can think about this. That's why people call it visual prompting, because it's actually input level learnable prompts to help solve downstream tasks.
I think it's the balance. Maybe you don't have the slide number.
Yeah. So but what is the content?
Yeah, so you kind of compare like with, and the second column is it's called the privacy budget.
Okay.
Yeah, that's why I was wondering why it's different. Why it's using the same budget and then you compare the accuracy, or your accuracy actually depend on your budget.
Yeah, so it's very good question. So this budget is very difficult to control in advance because for different schemes, right? You are actually using different parameters or different methods to train the model, right? So in reality, we basically when you specify epsilon value, right, you actually translate to in your training methods, right? How much budget you are going to spend, right, to have access to the private training data. Right, so for example, full fine-tuning, they will consume more privacy budget compared to prompting or differential private fine-tuning. So these numbers seems very ad hoc because we are actually tracking. We have a budget, a budget account, and we're actually computing the accumulated privacy budgets during training time, and we stopped. So in the experiments, right, we keep training the model until we hit the privacy budget, and then we stop there. So each method will stop at a different training epochs or training iteration, depending on how they consume the privacy budget. So we basically stop around 2 or around 1.5 to obtain that checkpoint satisfying privacy constraint.
But if you go to let's say the current it is prompt it's 1.0 and
Yes.
1.5 and
Yes.
1.9.
Yes.
If it's higher, the accuracy lower. or-
Yes, but I would also argue all other methods, like when they say 1 and 2, they are not exactly 1 and 2. There are some numbers close to 1 and 2, they just brought up. Yes. Yes, so yes, I agree. So the most real comparison is probably this epsilon accuracy plot. So this is a real plot. So the way we compute is that we keep training the model, and then we either stop here or stop here, stop there, depending on how many privacy budget you have. Yes, yes. Yes, so but you can see we are basically lazy. We just copy whatever they reported in the paper instead of running those baselines. Yeah, but I see your point. Sure.
Yeah, I had a general
Sure.
question, like, say, what is the intention behind this one? Are we saying, like, let's say in the real world, say radiologist who is able to say cancer is there on the X-ray or not? Now we say the radiologist, you can become a stock predictor. This stock will outperform or outperform, right? I mean, that's basically what they're. So what is the magic? Is it just the border and how I pick those? That's what defines my output. Or if I instead of obviously it has to be from the pre-classification image has said that I have the choice, but I might have lots of choices. Right? If I place the same image all around, will I get the poor results or will I get good results? How do I define that?
Yes, that's a great question. So I think this is the same thing for prompting, right? So people are also exploring what is the best way to prompt a large language model, right? And they are based on like a train of thoughts, right? Oh, you think step by step, right? If you add some magical word, all of a sudden the language model becomes very useful and becomes a better reasoner, right? So we are dealing with the same model, right? So why is that, right? So that means the model, right, actually has at very least those foundation model, they have the capability to do something great, but you need to invoke those capabilities through these magical prompts, right? So that's why it becomes a very interesting topic for the prompt engineering. Right? You need to figure out what is the best way to prompt those models, right? So I would argue this is probably the same thing for model recruitment or prompting, right? So as a radiologist, I have some like private analytic data I want to train a classifier to help me do automatic diagnostic, right? For example. But when I search online, right, all those foundation models are for language, are for general image, right? How then it is not for my task, and zero shot inference probably won't buy as much, right? So in this case, I think this the best scenario is to use this reprogramming as a cross-domain prompting, right? To connect, to bridge the gap between those available foundation model for different domains, right? To help you solve your own task using your own private data, that kind of thing. But how do we figure out the best prompts and so on? I think that is also an ongoing challenge. And we have some recent effort. We try to automate this pipeline and basically another AutoML methods for automatically figure out what is the best model, what is the best way to prompt, right, for our visual prompting and so on.
So yeah, so then you had this thing where you went to the epochs and the miracle became the thing was more and more like a miracle.
Right. Yes.
And so what do you do with you have that same source set, and then your training set is X-rays or it's ultrasound.
Yes.
Is there something that's kind of otherworldly compared to that?
Yes.
In your experience, I mean, there would be no presumably correlative picture like this. So is that
right?
How do you know if it's like not doable? Is that the term in your or is it?
Yes, yeah. So if they cannot be perfectly aligned, then the second term loss will be very high, which means you probably won't get a very good reprogrammed model, right? But if the second term is small, which for example in this case, we can map very good to orange class, right? We find very good matching labels, then we can probably make the second term loss very small. Yeah, but the interesting is about nowadays foundation models, they are very generic and they are trained on massive amount of label data, and even without label, right? It's self-supervised learning, like a clip, right? Basically, you don't know how many image labels it can predict, right? So I would argue, as long as you are using a powerful enough vision transformation models, right? When you solve the downstream task, it's probably all you need to do is to figure out how do we map the text prompt or image labels, right, to the target label you want to solve. And once you found that, right, it should give you a very good accuracy using prompt.
And that is the mechanism you're describing. Is that that's the
yes, yeah. But the auto machine learning pipeline I was describing actually involves, right, how can we figure out the best input transformation function? How can we figure out the best source model, right? Given the target task, what is the best input transformation? What is the best source model, and what is the best way to do label mapping, right? So all those things together is what I call the automated visual prompting pipeline.
For multiple pieces you have to
Yes.
prompt and the
Exactly. Yeah, but that being said, it is still more efficient than just fine-tuning the entire 7 billion or 100 billion parameter space.
Let's thank the speaker again.
Just unblock it.
Yep. So our next on our schedule, the author of this paper entitled "Synthetic Sample Selection for Generalized Zero-Shot Learning." He got the visa for the last minute, so he is traveling right now. So unfortunately, he cannot do a live Q&As, but he graciously sent us a video. And we think we can we'll put that video online for the sake of the time. So we'll directly jump to the next live session. So next on the schedule, you will be the paper entitled "Estimating and Maximizing Mutual Information for Knowledge Distillation." So we have here.
Anybody has a piece with a
USB port to HDMI.
Apple to HDMI?
No, or can you send me the slide? Yeah, thank you so much.
So I'll be presenting our work estimating and maximizing visual information for knowledge distillation. This is I am Amit Rasov, and Professor Yanucci is my co-advisor, and also Professor Vicente is a co-advisor. So the motivation of the paper is to present a new way of knowledge distillation, where let's define what knowledge distillation is. So knowledge distillation is just transferring knowledge from one language, from one model to another model. And generally this is done to achieve one of these tasks. Like if you're trying to do model compression, you take a large model and you try to distill some knowledge from that large model to a small model, so that the small model can perform better than it would have performed without the help of that large model. Or you can do cross-model knowledge transfer, where you take one modality and you train a model on that, and you sort of want to distill some information from that modality to another modality. So that is where distillation can be used as well. Or you are trying to do ensemble distillation, where you train multiple models and you sort of want to combine the knowledge of all of those models into one model. So you ensemble them, and that way distillation isn't useful in that case. So recent advances in knowledge distillation have sort of followed two main threads. So the first one is where you do output distillation, where essentially the distance metric is optimized between the final representation of the student network and the teacher network, so that both of them output the same kinds of quality distribution for similar objects, so that you sort of make sure that both of them are outputting similar things for similar inputs. You can also extend this to feature level distillation, where you sort of are trying to make sure that both the networks also are having same types of activations at the intermediate layers of the models. And this is done by minimizing like a loss between intermediate features, as you see in the feature distillation figure. So overall, the motivation of our work is that these methods which apply loss between intermediate representations, all the final representations, have certain caveats. And some of them are that the output probability distribution matching matches the output probability distribution of what that object is, but not the representation of the object generated by the model. It's just matching how likely that object is belonging to one class, and it's trying to map that with the output of another model instead of matching the representation that both of the models are generating. So that's essentially one of the caveats. Another caveat is that if you like sort of minimize the distance between the intermediate representations and you sort of try to structurally impose that these two networks have like similar activations of the filters at same points of the network, you sort of are imposing a data abstraction flow, which may or may not be correct for both of those models, because different models have different data abstraction flows and might be capturing different complexities of information at different levels of the model, and it's hard to identify which level to match which another level in a different model. Also, if you're sort of minimizing, let's say, an L1 or L2 loss between the features, you ignore the interdependencies between the dimensions. Like maybe the last three dimensions of your feature representation sort of inform the first dimension of your student representation, but such complex interdependencies are not mapped because you're doing feature by feature L1 minimization or L2 minimization or any distance metric. So we sort of look at this problem from an information theoretic perspective. So to do that, let's just define what mutual information is. So mutual information is just a fundamental quantity that measures the mutual dependence between random variables, and it can be used to model complex relationships. For example, in this figure, you can see this I found on Twitter, so it was very informative. Like you can see that in the figure that even if there's a complex relationship between the variables, normal metrics like the covariance is not able to capture that complex relationship, whereas a mutual information metric would be able to capture more complex and non-linear relationships between your distributions. So how do we estimate this mutual information? It's also a big problem because it's notoriously difficult to estimate mutual information, especially between high dimensional variables, which is what these neural networks operate at. So there was a paper in 2018, which is a very fundamental paper, and they presented that if you sort of train a neural network, which is able to distinguish between samples from a joint distribution and a product of marginal distributions, which means that if there's a neural network which is able to tell the difference between two pairs which are positive samples and two pairs like two images which are a negative sample. For example, I give you two versions of the same image. The model should be able to tell, irrespective of what the transformations in the image are, that these two have the same information, whereas two different images, a dog image or a cat image, even with the same transformation, should have like different information. So if there is a neural network which is able to tell this difference, you can sort of use that neural network to optimize these lower bounds on mutual information. So that way, instead of directly capturing what the mutual information between two random variables is, you sort of try to minimize or maximize the lower bound on the mutual information, and that way you're able to sort of optimize the mutual information between objects. And essentially, this is how like all kinds of self-supervised algos also work, because influency bound is also mutual information bound, which sort of maximizes the mutual information between two modalities. And this has found success in all kinds of like CLIP model also uses influency bound. But now the caveat with such bounds is that an influency bound is dependent on a large number of negative samples, which is the problem with a lot of these models, that you'll see that they use a large memory band or they use a large number of negative samples to be able to estimate this bound and then maximize on it. So, and this is a problem for knowledge distillation, because in knowledge distillation, if you're trying to maximize the mutual information between, let's say, the intermediate representations could be multidimensional, and to keep like a large memory bank of multidimensional features is more expensive than just keeping like 1D representation, a large number of negative samples in that case. So we want to still be able to optimize on mutual information, but not use a large number of negative samples. So how do we do that? So we found that so what is mutual information? Mutual information is just the k evidence between a joint probability distribution versus a product of marginal distributions between two random variables, right? So this is just a k divergence is just a divergence metric between two distributions. So what if we just replace the scale divergence with the Jensen channel divergence, which is also a divergence metric and is also symmetric. So I mean, it's not really essentially adding like any additional properties, but it's also a quantity that could be that is directly proportional to the mutual information also, because it's the divergence between the product of quantity distributions and the joint distribution. So when you solve that equation with the Jensen channel divergence, instead of using the Taylor divergence, you find like a lower bound, which is insensitive to the number of negative samples. Unlike the influency bound and the Donsker-Van bound, which come through the Taylor divergence path of mutual information maximization, these bounds do not really depend on the number of negative samples at all. So and also instead of directly modeling mutual information, they're modeling a quantity which is monotonically related with mutual information. So essentially our idea is that we don't really want to exactly find the value of mutual information or maximize exactly what mutual information is. We are sort of maximizing a quantity which we show is monotonically related with mutual information, but can be optimized with just one negative sample. And this is useful because intermediate features we cannot have like a large number of negative samples. Okay, so now is this bound better than the influency bound, because you can use one negative sample and do as well as an influency bound, but that's not essentially true. What happens is that at lower batch sizes or when the number of negative samples are very low, you will see that the Jensen channel divergence bound does not lose its potential. Like it's always performing at the same level, irrespective of what the number of negative samples is or the batch sizes. Whereas the other bounds, you will see that will start performing much better as you start increasing the batch size, which essentially is increasing the number of negative samples. So as you increase the number of negative samples, the influency bound will overtake the Jensen channel divergence bound, but only after a certain number of negative samples. And this threshold is different for different data sets, different models, and different problem settings. All right, so how do we use this for mutual, like for knowledge utilization in this world? Is that we take, let's say, for example, two networks, the teacher network and the student network, and these are the intermediate feature representations and the final feature representations. So we formulate three types of information maximization frameworks. The first one is global information maximization, where we sort of enforce that the teacher generates a representation and the student's representation, the final representation that the student generates, has maximum shared information with the teacher's representation. So what we do is that we take the positive pair of information generated from the teacher and the student, which is the orange feature, and the light orange feature is a positive pair, whereas this fx x prime is a negative sample. So what we do is we pass a positive pair and negative pair to this neural network, which is what is distinguishing between a positive pair and negative pair. And the outputs of the neural network are then used with the lower bound that we derive, and that estimates a mutual information between these two values, and which is because it's differentiable, we can optimize on this metric. So this is global information maximization. Right now, how do we do local information maximization? Because now we are able to do it with just one negative sample. We can also impose these structures within the intermediate features. So what we are trying to do here is that the final representation that the teacher generates, we want that all the intermediate representation that the student generates also shares the maximum amount of information with the final representation of the teacher. So what we do is that we duplicate the teacher representation the same number of times as the size of the intermediate feature representation, and then maximize the mutual information locally with that representation. That way, we sort of are enforcing that the student model at all levels of its data abstraction flows is sort of extracting some information that is finally useful for generating a representation that is used for downstream tasks. So that is the idea between this framework. And here we use the Jensen channel divergence bound because one of these negative samples or the positive sample pairs is like multidimensional. It's much harder to keep large number of negative samples there. And the third one is just simple feature information maximization, where we find intermediate feature representations from the teacher network and the student network, which have the same size. And then we sort of maximize the visual information between them. And this is done by similarly concatenating or taking a dot. So there are two types of visual information discriminated networks. These T omega, which are described in the paper, you can look at it in detail, but simply put, one of them is the concat-based architecture and the other one is the projection and dot product-based architecture. And we found that the projection one works slightly better. All right, and here is a very extensive ablative study to sort of demonstrate that these frameworks actually do work. So what we do is that we fix the value of one of the maximization frameworks to a constant value, and then on the x-axis we increase the value of one of the other maximization frameworks, and the y-axis is the third maximization framework. So you'll see that irrespective of what the value of one of the maximization frameworks is, both of the other ones will always do better if the values are higher for both of the lambdas. Like you'll always see a darker picture towards the right of these plots, and this is replicated for all values of like lambda. Like if you fix all of the features, like for example, the top left figure is when lambda g is set to 0, which means that there's no global information maximization, whereas lambda f and lambda l are really between 0 and 1 with an increment of 0.25. So you'll see that if you start increasing the value of lambda f, the model will start performing better. And if you increase the value of lambda L, the model will start performing better. And this trend is sort of replicated in all kinds of plots. So we sort of established that all three of these mutual information maximization frameworks are working and contributing towards the better representation. Okay, so then we sort of apply this for model compression. One of the tasks that we highlighted is an important task for knowledge distillation. And we show that you can increase the accuracy of a VGG8 by 3.6% on the C400 dataset if you use a VGG19 as a feature. And this is between similar architectures. We demonstrate that we are able to do it between similar architectures, dissimilar architectures, and also very shallow networks, just to show the flexibility of the method, because other previous methods, if they interfere with the data abstraction flows, are not able to do well with dissimilar architectures at all. Like they do very well with similar architectures, but are not able to cope with dissimilar architectures because the abstraction changes. But here we show that our method is able to do well in all kinds of settings, irrespective of whether the architecture is the same or not. On the right, you'll see a plot where on the x-axis we have the inference time in the number of milliseconds of how long it takes for a model to run inference on one sample. And we show that if you have like a model, which is a very simple model, you perform knowledge distillation on it, and you can reach an accuracy which is equivalent to a much larger, much slower model. But you can already do that if you perform distillation on a smaller model. So you already reach that accuracy without using the extra time, inference time. Yes, and that's all for our presentation. Thank you. Any question? Yeah. Okay. Sure. Yes. Yes. So there are two reasons. Number one is that we were able to show, and other papers have also sort of shown that this one gives a quantity which is monotonically directly related to the mutual information also. Like if you take like a toy example and sort of measure the mutual information because you know what the mutual information should be in that case, and also measure this quantity, you will find that there is a direct relationship between these two quantities. Yeah, I know. Yes.
Maybe other, I mean, also.
Yeah. That could be true, but having like what we have seen is that in the past literature they have shown that the Jensen-Tanner divergence leads to a bound which has these properties, but I have not seen any other divergence metrics that lead to a bound that also have these problems.
Our question maybe like rounded up about the global competition.
Yes, yeah. So because for the global information maximization, you see that the negative features and the positive features are only in one dimension. So in this case, it is possible to even keep a large number of negative samples and perform like maximization on the final features using an influency bound, but only do the Jensen and divergence bound on the intermediate features because it's required. Because as we see that the influency bound always does better if you can keep a large number of negative samples. Yes, but because in the case of when we are doing global information maximization, because the features are one dimensional, we can actually, it's easy to keep a large number of negative samples in that case.
Yes.
So in that case, the B already increases. This B is very
Okay.
yeah, so you are able to like harness the capabilities of an influency bound in that case because the features are very small. So you already are able to artificially increase that size and use that one. Yeah, MK is just an arbitrary size of the kth feature, intermediate feature. So the kth intermediate feature in this figure, it has an MK cross MK size, and that's just the notation. Because we find there are, for the intermediate features, we pick capital K intermediate features on which we do this local information maximization. Like for the teacher network and the student network, we pick, let's say, a certain number of intermediate feature maps to do this one. And let's say we set K equal to 3. So 3 intermediate representations are picked. And let's say for K equal to 1, the first intermediate representation will have M1 cross M1 dimension, which could be 6 cross 6 or 9 cross 9 or 3 cross 3. And the third one, like the kth one will have MK cross MK dimensions. So whatever MK cross MK is, we replicate the teacher representation the same number of times so that the size matches. Yes, exactly. Correct. Thank you. Yes.
So yeah, super interesting. So the JSD, could you give a little intuition there? So it's kind of strikes one as miraculous.
Yes.
JSD can do everything MI can do without the negative, without characterizing a distribution, right? It seems like that's mutual information characterizes this negative distribution. And so how is it, is there intuition why this other, whatever JSD is, can do that with characterizing a negative distribution, I guess, with one sample, or is it not? How does it do that? That seems like a magical, amazing thing.
So if you look at it from just one step, like if you do one step of influency versus one step of JSD, the one step of JSD will always be less efficient than the influency step because that is much better modeling the distribution, sort of doing the contrastive learning actually better than a JSD based step. But if you do large number of steps, an equivalent number of steps on the same data set, and if the data set is very small, the Jensen and evidence is able to extract the maximum amount of information from it.
Or you change the name content?
The number of negative samples is not the number. Oh yeah, so the negative changes every time, exactly. So yeah, so because if you do multiple steps, every time a new negative sample will be picked. And that way, because if you're able to do one step with just one negative sample, you're able to do more unique steps within the same data set.
Oh, so you're still thinking wide range of negatives.
Exactly. Yes.
Computational.
Yeah, it's just, yeah, and just because one step in an influency bound is taking like 1000 negative samples. So the number of unique negative batches that you can pick for every positive sample is limited because you're picking 1000 at a time. But if you pick one at a time, then this sort of balances. Mm-hmm. Yeah, yeah.
For your nice presentation. I guess that brings us to the end of our day. and the fourth workshop today. And we, as our title says, we had the last talk in at a limited zone that's for the efficient data side. We talked about fairness, we talked about trust throughout the day. So I guess we covered all the three things. Yep.
Applaud people. So fairness, visas are an incredible barrier. You can go to Canadian, it's a website, and one web page will say what countries do not need a visa. All European. And the next page, if you need a visa, type in your country and how many days. Type it in country. In South Africa, you type it in, and it's 739 days. So if you are a researcher who's not here in North America, you will never go to a conference in Canada. Because you could be the world's best researcher, but you can never get to a conference. It's comparative and fairness is huge. Very that I don't know how to fix it.
Yeah, I guess that's exactly the point, that we don't know how to fix it. That's what we have to live with. And whereas all our biases in our learning models or AI models or computer vision models, at least we have some say in and control. Hopefully we will change that in our life, whereas the other one, I guess if you want to change, you have to have a different role than a computer vision researcher. So definitely we had a very exciting day, and some of the things that you did not see what happened in the background is, I guess, my co-organizer sitting here glued to the machine, he has been trying to make it look smoother throughout the day without, I guess, barely he went to a bio break only. That's the only break that he took. So thank you again. And then we had several people on the organized committee, and through that one, they have been correcting all of us, whatever mistakes we have been doing. So they were all seamless to you if you didn't notice it, right? So thank you all for staying this late. And we look forward to papers and